Yes, I am serious. Today, we'll be doing 100 derivatives, and we'll be doing them in one take. However, this is not the first time I'm doing this though, because I actually did this 10 years ago already. But let me tell you guys this first. I would like to dedicate this video to all my upper bound students, especially the ones in 2009 in the summer at UC Berkeley campus. And let me tell you guys, my upper bound students, I still remember everyone. I still remember you guys. It was such a wonderful experience that we had. And that was the second time that I had my own class. I taught my own calculus class during the summer. And the upper bound, it's a program that helps high school students who are from low-income family, just like myself as well. And I, of course, have to thank my director, my main man, Mr. Muniga Lamumba. Moon, thank you so much for believing me. Thank you so much for giving me so many chances to teach the class. Without you, of course, I cannot be who I am today. I cannot thank you enough. Thank you. All right, so 10 years ago, I actually did a PDF because I had to teach my class, right? And I decided to produce, enough examples for my students. And how many examples are enough? It came out with 100 derivatives, questions, and also solutions. And typing them up, you guys can find the link to the PDF. I will have that in the description for you guys. But today, though, we'll be doing something different. I have this right here for you guys. And notice that the questions here, they are in the multiple choice format because I believe it's the best when you have derivative questions with multiple choice format, because sometimes you don't know how much more you have to simplify or how much more you have to keep going or when to stop. So multiple choice format is the best for derivative questions. And for the people who would like to know this, yes, of course, how can we have derivatives without the definition, right? So if you guys would like, the last 10 questions or so, yes, derivative by using the definition. But the first 90 questions would be just, we use the rules that we have known already, okay, all that. So this is going to be good for Cal 1 and Cal 2, and hopefully you guys all enjoy this. And in fact, today I have something fun. Let me just show you guys this right here. I bought this recently. Alright, so I bought this recently and I opened it. This is called the Ninja Milk, right? M-E-L-K, so Ninja Milk from Ryan Higa. And I will be trying his energy drink for the first time. So you guys can see, I have this package right here, right? So I haven't opened the package yet. So I will tell you guys how it tastes, but not now because right now I have enough energy, so I don't need it yet. I don't know how long this will take me though, so I don't know how many I'll be drinking, so I don't know. And of course, I have my marathon medal. This is the one from 2007, and in fact, PR this, meaning personal record, during this year. And you might be wondering, why don't I bring the one that's from 2009? Unfortunately, I didn't run that one in 2009. All right, anyway, you guys can find the PDF in the description right here. All right, so yeah. All right, here we go. First question, we are going to be differentiating x squared plus bx plus c. Notice that a, b, c are just constants, right? So for the first one, we'll just start something easy. It's just the power rule. And the idea is that whenever you're adding or subtracting, right? But this is just all adding. You can just differentiate the first, and then differentiate the second, and differentiate the third, and then just put the results together. That's it. So for the first one, for this right here, I will just bring the 2 to the front, and then minus 1. That's the dual product power rule, right? So the first term we'll get 2a, and then x to the first power. You don't have to put on the 1. And then the next one is plus. When we have b times x to the first power, well, you can put on the 1 right here. You can bring the 1 to the front, and then minus 1. 1 times b is just b, and then x to the 0th power is just 1. So it's just b. It's just the coefficient of x. Lastly, this right here is just a constant. So when you differentiate constant c, when there's no x, the derivative of this is just going to be 0. So you don't even have to put that down. So for the first one, the derivative of a quadratic is just 2ax plus b, and that's it. Start with something easy, right? And I'm not going to give you guys the answer key. Hopefully you guys can all figure this out. So there's a nice pattern. Okay? You guys can let me know in the comment down below and let me know what the pattern is. Anyway, second one, we'll be differentiating sinx over 1 plus cosx. Notice that this is a quotient, and we'll be just using the quotient rule for this. So here we go. Before we forget, let's go ahead and square the denominator. So we will have 1 plus cosine x, and we will raise that to the second power. And then the quotient rule says we will have to put the denominator to the top right here. So let me just write down 1 plus cosine x. And then we multiply by the derivative of the top. The derivative of sine x is just going to give us cosine x. And of course, you have to know all the derivatives of the functions, right? Yeah, so you have to know that. All right, so you have all this, and then you have to subtract the top function, which is sine x, and then multiply by the derivative of the bottom function. The derivative of 1 is 0. The derivative of cosine x is negative sine, so we have negative sine x right here. And now, this is the time that you have to think about how we can simplify all the expressions right here. Well, of course, we can just distribute the top right here, so we'll do that. So cosine times 1 is just cosine x. Cosine times cosine is cosine square x. And we put the power 2 right here, right? Cosine x, and then square. And then negative becomes positive, and then sine x times sine x is, of course, just sine square x over the denominator right here, which is 1 plus cosine x square. And now, check this out. Here we have cosine square x plus sine square x. Guess what? Yes, we can use a nice trig identity for this. This right here is nicely equal to 1. So we just have a 1 right here. In fact, on the top, we have 1 plus cosine x over 1 plus cosine x squared. Therefore, what we can do is, we can actually cancel the top. Perhaps I'll just write it down again for you guys to make it clear. This is like saying 1 plus cosine x. And then we divide it by the bottom is parentheses 1 plus cosine x, and then to the second power. So, of course, we can cancel this one out with 1 of it on the bottom. And therefore, all in all, the answer is just 1 on the top over 1 plus cosine x to the first power like this. And after that, we are done. We don't need to put down the plus c because this is derivative. This is nothing to do with integration, right? So find the answer in the answer choices right there. All right, number 3, I will also fit in here right here. So we will be differentiating. It's just the flip of this. This right here, we have sine x over, Number 3, I should have written this down earlier. Number 3, we have 1 plus cosine x over sine x, like this. Well, for this question, in fact, we don't have to use the quotient rule because we only have one thing on the bottom. And we have 2 things on the top, right? 2 terms. We can just split the fraction. It will be easier this way. So now check this out. I'm not doing derivatives yet. I will just put down d dx to mean that we will be taking derivative and we'll split the fractions. 1 over this, 1 over sine x. And then the second one is plus cosine x over sine x. And then, of course, 1 over sine x. Do we know anything about that? This right here, yes, it's just cosecant x. Likewise, this is just cotangent x. So check this out. This right here is just to differentiate. We haven't done the derivatives yet, so we still have to write this down. We have to differentiate. This is cosecant x, and we will have to add the result with this right here is cotangent x, like this. Oh my goodness, I will have to remember what the derivative of this and that are, huh? I think I know. The derivative of cosecant x is negative cosecant x times cotangent x. And then the derivative of cotangent x is negative cosecant x squared, where you put a 2 right here, right? And that's it. You don't have to factor out the cosecant x. And you can find the answer in the answer choice right over there. So that would be good. I just realized I make a typo on my answer choice. And I'll fix that later, but yeah. So yeah, if you guys saw the answer earlier, but just look at the file in the description. I'll fix that before I post it. So anyway, these are the first 2 questions. I don't know how long this will take me. Derivatives usually aren't so bad until we hit the definition, right? When we have to prove the derivative of what and what with the definition of derivatives. All right, so 3 questions down and many more to go. And hopefully you guys all find this video to be helpful, right? All right, number 4, we have the square root, right? So here we have number 4. We will have to differentiate the square root of 3x plus 1. Derivative of square root of 3x plus 1. Now, this is how we can do it. First thing first, you have to know, right? You have to know that the derivative of the square root of x, like this. This right here will happen a lot, so you just might as well remember it. The derivative of square root of x is 1 over 2 square root of x. And to do this, you will have to write the square root as the 1/2 power, and you bring the power to the front, and then minus 1 from the power. So you end up with 1/2 x to the negative 1/2. X to a negative 1/2 is the same as putting the square root in the denominator. But as I said, you should just remember this and then use that to do the questions like this. So here we go. To differentiate square root of 3x plus 1, we will just have to look at the big picture, which is the square root. We will have to do 1 over 2 times the square root of the inside, which is 3x plus 1. Right? It's pretty much the same idea over there. However, don't forget the chain rule. We have to multiply by the derivative of the inside. The derivative of 3x plus 1 is just a 3, so you multiply by 3 right here. Right? So this is the chain rule. And some textbooks, they like to call this step the chain rule. So one way or the other, they both work pretty nicely. In the end, of course, 1 times 3, you can just put the 3 on the top. So 3 over 2 square root of 3x plus 1. And guess what? We are done. So this right here is it. All right, now, number 5. So here we have d dx. This again means to take the derivative. And we have these 2 notations. Sine, and you put the 3 right here, of x. And then we add sine x like this. With the 3 right here, parentheses. And technically, I also have the parentheses right over there. Here is the deal. This right here, right? This right here, it means we will have sine x, right? Raised to the 3rd power like this. And then, of course, we will have to differentiate this guy, right? So it's just the notation. Whenever we have the 3 right here, it means we have sine x times sine x times sine x. Of course, we write it like this, all right? But when we have sine of x to the 3rd power, this means we have sine of x times x times x, like that. Parentheses matters. Parentheses matters. They are totally different. Be sure you are familiar with the notations, right? So this is how I would recommend you guys to do these questions. We technically have 2 questions to do, right? 2 parts. All right, here we go. We have to differentiate. For the first one, let's write it as sine x to the 3rd power. And then for the second one, I'll just keep it like this. Just remember to use the chain rule a few times whenever we need to. Okay, here we go. For the first one, sine x is the input, and then we have this raised to the 3rd power. So do the big picture first. Bring the power to the front, and then minus 1. So we end up with 3 parentheses, and the inside stays the same for now. So you just write down sine x. And then 3 minus 1, that's a new power, which is 2. And now it's the time to use the chain rule. you look at the inside, which is sinx, and you ask yourself, what's the derivative of sinx, which is just cosx, right? And you multiply this part by cosx. This is the chain rule. And then right here, let's go ahead and add. For this part, well, this time though, the big picture is sine of this. So you differentiate sine, which is cosine, and the input is x to the third power. It stays the same right here, okay? And then we look into the parentheses. The derivative of x to the third power is what? Well, it's 3x squared, right? Just use the power rule, so you get 3x squared. So this is it, right? This is it. And finally, we'll just write this down the usual way. So here we go. I will put down the 3 right here, and I will put down the cosine first. Did I put that down? No, I didn't put down the cosine first. I'll just write it down. This right here is the same as saying sine with a 2 right here, right? And then the cosx. And for this one, usually we put the polynomial part in the front, so I will write this down first, which is the 3x squared times cosine of x to the third power, like this. And with that, we are done. This is going pretty well, unlike the integrals. So this is number 5. Okay, number 6. I will just put it down right here. I'll just erase this a little bit so I can. Number 6. Here we go. We have to differentiate 1 over x to the 4th power, like this. Okay, so x to the 4th power. This is easy, huh? So, of course, we can just look at x to the 4th power, bring the 4 to the front, which is just 4x, and then minus 1, which is 4x to the 3rd power, and that's in the denominator, just like that, right? No! Don't do it like this. No! No. This is not the answer. Not the answer. Why? Because the 4 that you see right here, it's not really a 4, because it's in the denominator. Therefore, this right here, it's really asking to differentiate x to the negative 4th power. In order for us to use the power rule, remember, we have to have x to some number, right? Well, 1 over x to the 4th power, unfortunately, this 4 is actually a negative 4th power. So you have to know your rule of exponent really well. This is very similar to the square root example. You have to write the square root with 1/2 power. Anyway, look at this right here, and then do the power rule. Bring this to the front, and then minus 1 right here, and we end up with negative 4 times x to the negative 5 after you subtract them. And that's pretty much it. Finally, negative 5, that's the power for the x. So we can bring this down to the denominator. Therefore, we end up with negative 4 over x to the positive 5 power, like this. So this right here, it's a correct answer. This right here, it's a common mistake. Don't do it like that, right? Don't do it like that. All right. Continue. Number 7. Here we are going to differentiate, and we have 1 plus cotangent to the 3rd power, cotangent x, and then to the 3rd power, like this, right? So here we go. Of course, we have the inside, and then raised to the 3rd power. So again, we have to do the big picture first, which is the outside power rule, right? Bring the 3 to the front, and then minus 1. So here we go. Bring the 3 to the front. Inside stays the same. Just write down 1 plus cotangent x. And 3 minus 1 is 2, of course. We're not done yet though. Look at the inside and ask yourself, what's the derivative of 1? Which is 0. What's the derivative of cotangent x? Well, that's negative cosecant square x. Remember the chain rule, right? And of course, this right here, it looks like subtraction, so be sure to just put parentheses. This is the derivative from here, and we have to multiply this with that. This right here is pretty much it, and in the end, we just have to write it down nicely, put the negative all the way in the front, that's all. So finally, we have negative 3 times this, which is 1 plus cotangent x, and then square. And then in the end, I have the c(x), which is the cosecant square x. Just like that. And that's it. All right, now number 8. I need more space, so I will have to erase this now. So the first couple questions, I think the first 20 questions are more for like warm up, and I put it like according to the difficulty and also the things that you have to know in the usual order. Later on, you will see the inverse trig functions, natural log, exponential, and hyperbolic functions, all that stuff. All right, now things are getting slightly trickier and also slightly more complicated. Anyway, here we go. Number 8. We are going to differentiate, let's see, x squared times 2x to the third power plus 1 and raised to the 10th power like that. All right, this one compared to the earlier one, well, we have x squared right here times this quantity to the 10th power. So it's not just a simple chain rule question, because right here we will actually have to use the product rule because we have x squared times this. And this is how I like to set up the power. This is how I like to set up the product rule for my students. For the first, I'll show you guys at least one time right here in this video. So here we go. Well, this right here, it's the first function, so I'll just write down x squared, and I will call that to be f. This is just the first function, x squared, like this. And this is the second function, so it's g, which is 2x to the third power plus 1 to the 10th power, like that. Well, separate this, and I will differentiate them individually. For the first one, the derivative of this, which is just 2x, and then the derivative of this is g, right? So g prime is going to be the following. The derivative of this, of course, you bring the 10 to the front, minus 1, and we get 10, and the inside stays the same, 2x to the third power plus 1 to the 9th power, like that. And then we multiply by the derivative of the inside because of the chain rule. The derivative of the inside is just pretty much this part. We need the 6x right here because the derivative one is just 0. So it's just like that, and of course we can simplify this a little bit. 6x times 10, so it's 60x, and this is 2x to the third power plus 1 to the 9th power. So you can just set it out like this, and then we just kind of cross multiply to construct our answer. Product rule in action, f times g prime. So we will have x squared times this, right? So let me just put this down right here, which is 60x times 2x to the third power plus 1 to the 9th power. And then we go the other way, which is this times that. We add this times that, which is the original in blue. We have parentheses 2x to the third power plus 1 to the 10th power, and we multiply by 2x. So this is the right out, right? By using the product rule and also the chain rule. So you just have to do it carefully. And later I'll show you guys without these things, right? But I think this is helpful, especially if you're doing derivative, if you're taking calculus for the first time. All right, in the end, we just have to simplify this. Let's see. First of all, we notice that both terms, they have this factor, right? 2x to the third power plus 1. And this is 9th power, and this is the 10th power, so we can factor out the smaller exponent. So perhaps let's do that. And in fact, we can also factor things out. This right here is 2x, and this is 60x. Both of them have x, and both of them have a factor 2. So perhaps let's do this first. Let's put down the factor of this, right? So let's factor out 2x. Let's factor out 2x. Okay? In the meantime, we can also factor this out, which is 2x to the third power plus 1 to the 9th power, like this. And now let me show you what the leftover is. Well, if you look at this part, we factored out the 2x, so 60 divided by 2 is 30. This x is out, but we still have x squared, so we write down x squared right here. And you see this part, we factored it already, so this is all we have. namely 30x squared. Now, if we look at this part, first we have to add. Notice the 2x is all the way in the front already. And then for this part, we see we took out 9 of the factors already. That means we have one more. So we just have the inside, which is 2x to the third power plus 1 to the first power, just like that. And in the end, I just kind of leave it like that, I think. Yeah, I didn't do any. No, I make a small mistake. Man, okay. 2x to the third power, the derivative of 2x to the third power is 6x squared. My bad, right? And then this right here should have been a 6tx squared right here. 6tx squared right here. And let's see. So this right here should have been 6tx squared. And let me just do this part again for you guys. Right? Let me just do this part again for you guys. All right, so 6tx squared right here. Again, same thing. We can factor out the 2x, right? So we can factor out 2x. Let's do that. And we can also factor this out, which is 2x to the third power plus 1 to the 9th power. And now, actually, I put this down in blue earlier. So I'll put it down in blue again. Anyway, 2x to the third power plus 1, and then to the 9th power. And parentheses, you see, I make mistake too, okay? Parentheses, okay, for this part, again, we took out the 2, so we have 30. And then we took out an x. So this right here is just x to the first power. X times x squared, though, is x to the third power. Again, because this right here is x squared, so it's like x times x. So you took out one of them, you have another x. This x times x to the second power, we get x to the third power. All right, and then that's it for the first part, because this is out. For this part, this is out. We have this left to the first power, so we add 2x to the third power plus 1 to the first power like this. In the end, we can combine this and that together, so we'll do that. And finally, we see the answer is, where's my equal sign? There we go. The answer is 2x times 2x to the third power plus 1 to the 9th power times this plus that, which is 32x to the third power, and in the end we have the plus 1, and that's it. So it simplifies pretty nicely, right? And yeah. All right, now number 9. And by the way, it took me a lot of time to come up with the answer choices as well, not just the question. I want to make it rather legitimate. I can just give it to my students for them to practice. And for the actual exams or actual quiz that I give out to my students, I usually have about 5 or 6 answer choices, but this is just for practice. That's why I only have 3 choices. Anyway, number 9, here we go. We have this. We have to differentiate x over, and the bottom here is parentheses x squared plus 1 to the second power, like that. Well, why don't I show you guys this right here as well? I call this the memory device whenever we have to do the product rule, quotient rule, and chain rule and all that. Especially if the question is complicated, I like to show my students this, especially for the first time. Anyway, here we go. This right here, it's a quotient, x over this, right? So we have to use the quotient rule. And the quotient is just the opposite of the product. So what you do is, on the top is the f function, on the bottom is the g function. Well, earlier you see the first one is f, the second one is g. Well, for the quotient rule, we actually write down g first, and then f right here. So the g function is this, which is x squared plus 1 to the second power. And then the f function is just x on the top. Once we put them down individually, we can just differentiate them individually. For the first one, we will just get g prime. And this is going to be, okay, put the 2 to the front, minus 1. And we will get 2, parentheses, x squared plus 1 to the first power. And we multiply by the derivative of the inside. Because of the chain rule, the derivative of this is 2x. So just like that. Well, for this one, of course, differentiate this real quick, we just get 1. So that's pretty nice. And let's simplify this a little bit. This is just 4x times x squared plus 1, if you would like, right? So I think we'll just leave it like that. Now, the answer to this, to construct the quotient rule, you do this times that still, right? But before we forget, we have to square the denominator right away. So I will put down parentheses with this inside, x squared plus 1 square. This had a square, that's the original, but we still have to square it because of the quotient rule, right? Okay, for the top, this is where the top comes in. I'm going to multiply this with that. So this right here is just that, which is, I'll just put in red, why not? X squared plus 1 to the second, I'll just put in black. This times that, so x squared plus 1 square, and we multiply by 1 right here. And then for the quotient rule, remember, it's subtraction. So we subtract, and we go from here to here. So we subtract this times that. All right, we have x times this part, which is parentheses, let me just put on dot, times 4x times x squared plus 1, like this. And of course, this is the good old way. You can just square the denominator, and you put the bottom function right here, and you multiply by the derivative of the top, and you minus the top function times the derivative of the bottom. And later on, I will really just be doing that steps without showing this right here. Okay, let's see if there's anything we can do to simplify this. Notice on the top, we can again factor things out, because here we have x squared plus 1 to the second power, and here we have x squared plus 1 to the first power, so we can factor that out. Parentheses, x squared plus 1. And let's see what we have left. Originally, this was to a second power. We took out one of them, so we still have x squared plus 1. Good. And then we have to minus. Well, this is out, but we still have to have this and that, and we multiply them together. 4x squared right here, so we put that down, of course. And then all over, of course, when we have this square and the square, we multiply the powers. So we end up with x squared plus 1 to the 4th power. And now check this out. This and that can reduce. So we'll cancel this and that out, and this becomes the 3rd power. And that's pretty much all we can do. And of course, we will also combine this and that. So finally, this minus that is negative 3x squared, and then we have the plus 1 over this to the 3rd power. So x squared plus 1 to the 3rd power, like this. And with that, we are done. That is it. And very nice. We did the first page already. Let me just show you. That was the first page. But the problem is, there are 13 pages. So, I don't know, man. Anyway, 10 questions took me this all 5-6 hours again. It's okay though. The more we do it, the faster we get. Anyway, number 10, right? But I will have to erase this. Okay. Maybe I will drink the ninja milk. The ninja milk. Once I reach question number 30. Yeah, I think that's a fair thing for me to do. All right, number 10, differentiating the following. So, we will be differentiating. On the top, we have 20, and on the bottom, we have 1 plus 5, and this is e to the negative 2x, like this. Right? Like that. Alright, good. Well, let me just tell you guys a little thing. This right here, right, this function right here, you can see it from the logistic growth function. So it's not quite exponential, but it's logistic. So it's really legit, okay? Well, how do we differentiate that though? you don't necessarily have to use the quotient rule. You can, but you don't have to. And the reason is because, notice, on the top we just have 20, which is just a constant. This is the function part right here, right? It's easier to do it this way. We can just write it as, to take the derivative, 20 is still 20, but we can write this, the denominator, bring that up, and raise that to the -1 power. So 20 times 1 plus 5e negative 2x, like this, to the -1 power. And the reason to do that is because we don't have to use quotient rule this way. We can just bring the -1 to the front and then -1 to the power and do the chain rule after that. All right, 20 times -1, we have -20, and this right here again stays the same. 1 plus 5e negative 2x, -1, -1, so altogether you get -2. But not done yet. Use the chain rule, multiply by the derivative of the inside. Derivative of 1 is 0. Derivative of 5e to the -2x is the following. Whenever we have e to the whatever, this part just repeats itself first. So we multiply by 5e to the -2x. But we are not done yet, because we have to look at the derivative of the inside, which is this part. The derivative of -2x is -2. So we have to multiply by -2 right here. So we have to use the chain rule twice for this part, right? So this is from here, and then to differentiate this part, we have to multiply by the derivative of -2x, which is the -2 right here. Okay. Now we will just put everything together. Let's see. Negative, negative, we get positive. 2 times 5 is 10, times 20 is 200. And I will just leave this on the top as well. So we have 20, and 200, and we have e to the -2x, like this. And then I have this all over. We can bring this down to the denominator, which is 1 plus 5e to the -2x. This -2 is the second power, like that. And that's the answer choice right here. And I just stop it right here. Sometimes maybe we'll write this down here, but it depends. I think this is more clear on using this method or maybe using the quotient rule. But as I said, whenever you have a multiple choice question, of course we choose the best answer. So that would be it. Now, number 11, we have to differentiate. Here we have e to the x in the square root. And then for the second one, we have to add e to the square root of x. We are not using the product rule right here. This is just addition. So we differentiate the first and then differentiate the second. Well, check this out. Whenever we have square roots, in calculus, we almost always look at square roots as 1/2 power. So in fact, for the first one, we can look at this. And we're just doing algebra. So the idea is that we should be doing algebra first before we do calculus. So if you look at this part, we just look at this to the 1/2 power, and this is e to the x inside. This part states how it is. And the reason I want to point this out is because this right here, we can just do x times 1/2, and we can rewrite this as to take the derivative of e to the 1/2 x plus e to the square root of x, like that. Do algebra first before we do calculus. And then, right here, we can just do the calculus. Okay, here we go. Let me actually just probably put it here, like that. This is not integration sign, this is just an arrow, right? Anyway, here we go. Differentiating e to the something, we first just repeat the whole thing, namely e to the 1/2 x. And then we do the chain rule. Look at the exponent right here and ask ourselves, what's the derivative of 1/2 x? And the answer to that is just 1/2. Good. Now we do the second part. And notice, again, we're just adding, so we just have to add the result for the second. We are not doing the product rule, right? the derivative of e to the square root of x, we can just first repeat that. And then, again, I'll look at this right here and ask myself, what's the derivative of square root of x? We talked about this earlier, so that's why I didn't write that as the 1/2 power. Derivative of square root of x is just 1 over 2 square root of x, like that. And that's pretty much it. In the end, perhaps we'll just write this down nicely. Check this out. E to the 1/2 x, this part is this, which is that. So this part is just the square root of e to the x inside. Over 2, so I'll put down the over 2 right here. And then for this part, I can just put this on the top, this times 1. So we put down plus e raised to the square root of x power divided by 2 square root of x, like this. Of course, you might want to get the common denominator if you want and all that, but again, I left the answer like this in the answer choice. So that's it for the question. So that's, yeah. Okay, now number 12. What do I need to do? Oh, this is a good one, number 12. Differentiating. Here we are going to differentiate secant to the third power of 2x. Secant to the third power of 2x. Well, it's a good idea to look at this as to take the derivative of parentheses secant of 2x inside like this, and then to the third power. Especially if this is the first time that we are doing derivatives, it's always a good idea to put the power right here. And don't forget to use the big parentheses to group the expressions. All right, here we go. We have to look at this to the third power, so we can just put down the power to the front and then minus 1. So the first part, we have 3, and then we have this right here, which is parentheses secant of 2x. The inside stays the same for now, right? Stays the same right here. And 3 minus 1 is 2. That's a new power. And we do the chain rule. Look at the inside. This is the time that we have to do the derivative of the inside. Derivative secant is secant of the inside times tangent of the inside, right? So we will have secant of 2x. Again, the inside stays the same. And we also have to have the tangent of 2x, like this. But what's the inside of the inside? It was a 2x, isn't it? Well, we have to do the chain rule again. What's the derivative of 2x? Just a 2. Very nice. Multiply by 2. Now, we'll just put everything together. 3 times 2 is, of course, 6. So, altogether we have 6. And check this out. This is secant to the second power and secant to the first power. They have the same input, right? This times that together, we can write it as secant to the third power, and the input stays the same. And we multiply that with tangent of 2x. Just like this. So this right here is the answer. Second power, first power, together we have the third power, and we put the power right there for the final answer. Just like that. Okay, number 13, it's one of my favorite ones. You'll see why. So, number 13, we will be differentiating 1/2 secant x tangent x plus, and this is the first time that we have the natural log, so I'll talk about the natural log function. 1/2 natural log of secant x plus tangent x, like this. So parentheses and another parentheses for that. All right, here we go. There's nothing that we can do to rewrite. Unfortunately, yeah, this is instead of the natural log, so we have to just deal with these two parts individually. For the first part, we have to use the product rule because we have the first function times the second function. So let's get this part done first. Well, product rule in action. We have to keep the first function, which is 1/2, and we have secant x. This is just the first function. Times the derivative of the second. The derivative of second, derivative tangent x is secant square x. And again, you have to know your derivatives really well for all these kind of questions. And later on in Calc 2, or maybe when you're doing integrations in Calc 1, you have to know the derivatives backwards. Anyway, first 1 times the derivative of second plus the second function, which is tangent, times the derivative of the first. And notice I have the 1/2 secx as my first function, so I need to have the 1/2. Whenever we have a constant multiple, just go ahead and put it down. And then you focus on differentiating the secx, which will give us secx times tangent x. So this right here is the first part, okay? Now I will do the second part right here in blue. We will have to add, well, again, 1/2 times this thing, so we will have to just maintain the 1/2 as 1/2. And this right here, as a reminder, whenever we differentiate natural log of x, natural log of the inside, we just get 1 over the inside like this. And of course, we will have to use the chain rule, right? Okay, so we have the natural log of this, so we do 1 over this thing, which is secant x plus tangent x. Well, chain rule right here, isn't it? We have to multiply by the derivative of the inside, right? Okay, this right here, it's a plus. So you just do the derivative of the first, and you add the derivative of the second. You have 2 things, so be sure you put the parentheses. The derivative of the first is secant x plus times tangent x. The derivative of secant x is this. And then you just need to add the derivative of secant x. Sorry, the derivative of tangent x is secant square x, like this. Wow, such a long expression, isn't it? So again, the derivative of secant x is that. We add it with the derivative of tangent x is that. So this is what we have. But do not leave this as the answer, because we can do better than this. Check this out to see what we can do. This is kind of weird. I'll show you. Check this out. Here we have secant square, so we can factor out secant, isn't it? So we can factor out secant x. And then here we will have tangent x plus secant x, right? If we factor it out. Hey, look at that. Here we have secant x plus tangent x. Here we have tangent x plus secant x. And of course, the order of addition doesn't matter. Therefore, we can legitimately cancel this and that out. So for the second part, we actually just end up with 1/2 secant x for the derivative. That's very nice. And perhaps let's look at this first part as well. We have, okay, for this part, we will just write this down in blue, okay? I will just put this down right here. We add 1/2 secant x. Again, that's just the second part. And now we still have to take care of this part. We still have to take care of this part. And it seems like we can also factor things out, huh? Because this right here has 1/2 x, well, 1/2 secant x, and this is also 1/2 secant x. So let's factor it out and see what happens. 1/2 secant x. Right? In fact, we can also factor this out, but let's do that later because it's kind of slightly too confusing a little bit. Left over, here we have secant square x plus left over tangent. So we have tangent square x. That's it, okay? So that's pretty much the factorings that we have at the moment. And now, of course, we can factor this out together. So we see this and that can be factored in. Put it outside, right? Put it outside. Take the secant outside. Multiply with the leftover. Here we have secant square x, and this is plus tangent square x. And we have to add, well, we factor this out in the front already. So for this, we have a 1 left. So that's what we have. But now, is there anything else that we can do? In fact, this is not one of the answer in the answer choices. This is the time that we have to know our trig identities. Unfortunately, secant square x plus tangent square x, we cannot combine them nicely, but we can actually combine tangent square x plus 1 nicely, because this right here gives us nicely secant square x as well. I'm serious, this add up to be secant square x. So check this out. All in all, we have 1/2 secant square, we have 1/2 secant x in the front order, right? And for the inside, we have secant square plus another secant square, so we have 2 secant square x, like that. Again, this plus that. Finally, you see 1/2 times 2. Well, of course, they cancel. And lastly, secant times secant to the second power is, of course, secant to the third power. So congratulations, this right here is simplifies to secant to the third power x, like this. Yeah, see, if you differentiate secant to the third power, you get that for the answer, right? It's a 2x inside. If you differentiate this, you get secant to the third power x for the answer. And let me tell you, in Cal 2, you actually have to know how to go backwards. Meaning, you start with secant to the third power, you have to figure this out right here. So that's it. And then as you can see, I dropped my marker. So hold on. I got too excited. But anyway, this right here is it. Secant to the third power x. Right? Okay, that was question number 13. So hopefully you guys can see some of the questions are going to be slightly trickier than the others. But some of the questions is just that if you know all the details, you should be able to put the answers together nicely, quickly, simply, yeah, and all that stuff. All right, that was question number 13. Okay, here we go, number 14. So, differentiating, on the top, we have x times e to the x. I noticed that this is on the top because we have 1 plus e to the x on the bottom. Oh my god, like that. Anyway, we can do it, don't worry. Now, this question requires both the quotient rule and also the product rule, because this is a quotient, right? This over that, and on the top, x times e to the x. It's a product, so we have to do both. Anyway, check this out. First of all, before we forget, let's just square the denominator, and I will just give myself a little bit more space. Let me just put the parentheses down right here, and 1 plus e to the x inside, and we square that. Now, the quotient rule says I will have to put the bottom function right here, which is 1 plus e to the x. And we multiply by the derivative of the top. So here we go. Open the parentheses because we have to use the product rule and we have to have two terms, right? So, product rule in action for the top. We keep the first function, which is x, and we multiply by the derivative of the second. Derivative e to the x is just e to the x, so we have that. And we add the second function, which is e to the x, times the derivative of the first. Derivative x is just 1, so we multiply by 1, like that. But we're not done yet. Minus, okay, I need this to be longer. Put this slightly more in the middle. 1 plus e to the x. Okay, anyway, minus, we write down the top function, which is x e to the x, and then we multiply by the derivative of the bottom. Derivative of 1 is 0, derivative e to the x is just e to the x, so we multiply by e to the x, like that. So this right here is a write out. It's not so bad, and we just have to simplify this. Yeah. Okay, let's see what we have right here. So, just kind of don't panic, just do it. Anyway, we do 1 times that. I will put down the result on the top. It might be easier this way. So 1 times this is just x e to the x. And then 1 times that is just e to the x, right? Next, e to the x times this. We add x, and e to the x times e to the x, we add the exponents. So we'll get e to the 2x. Right? So e to the 2x. Lastly, this times that. So again, plus e to the 2x. Good. Then we minus this times that. Well, we have the x right here. E to the x times e to the x is just e to the 2x. So that's pretty nice. Well, is there anything that we can do to simplify? Yes, because this right here and that, they are exactly the same but opposite signs, so we can cancel them out. And that's it. So that's pretty much on the top. So in the end, we have x e to the x plus e to the x plus e to the 2x. You can factor things out, but the answer is just in this form, so we'll leave it. On the bottom, just that. 1 plus e to the 2x, 1 plus e to the x raised to the second power. Just the bottom. And with that, we are done. All right, number 15. dx. We will have to differentiate e to the 4x times cosine of x over 2. Right, so notice that this is a multiplication, so be sure we use the product rule, and this is number 15. Number 15, you guess. Number 15, okay? Number 15 is not number 5. There we go. Okay, here we go. This is just going to be a product rule example. Well, we of course keep the first function, which is e to the 4x, and we multiply by the derivative of the second. Well, we have to use the chain rule right here as well, so don't just be careful with that. Anyway, the derivative of the second function, derivative of cosine is negative sine, so we multiply by parentheses negative sine. And the input stays the same, so x over 2 right here. But we will have to multiply by the derivative of the inside. What's the derivative of x over 2? It's just 1/2. Good. Why? This is just a small note, okay? Because I have experienced some students, they would like to just use the quotient rule right here. You don't do the quotient rule for that. Because when you have to differentiate x over 2, you have 2 ways to do it. You can just look at this as to differentiate 1/2 x, right? 1/2 times x, and of course you will just end up with 1/2 like that. So differentiating this is just 1/2. Do not do quotient rule. Whenever you have a number on the bottom, just focus on the number. One other thing you can do is bring the fraction 1/2 in the front, and then differentiate whatever function is left, just like that. And you see, this is 1/2 times the derivative of x is just 1. So it's just 1/2 times 1, which is just 1/2. Right? Just all that stuff. Yeah. So, yeah. All right. I'll have to close the parentheses right here. Not done yet. Not done yet. This is just the first function times the derivative of the second. And then we add a second function. So we put on plus. And the second function is cosine of x over 2 times the derivative of the first function. So we multiply by e to the 4x, right? Because the derivative of the first function, derivative e to the 4x, we first write it down. And then we multiply by the derivative of 4x, which is just a 4. So this right here is the chain rule part. So this right here is pretty good. And there's nothing too much we can do to simplify. And I didn't factor out e to the whatever, so I will just pretty much write down the results as how it is. So finally, the answer right here is negative 1/2 e to the 4x times sine of x over 2. And then 4 all the way in the front, so plus 4, and then let me put on e to the 4x and cosine of x over 2, like that. So this right here is the answer for that derivative. All right, number 16. I will just write it down here, number 16. Here we are going to differentiate 1 over the fourth root of x to the third power minus 2, like that. Shall we use the quotient rule? No. Because on the top, again, it's just a number, it's just a 1, right? So it's a much better idea to write this as a negative power. And this right here, it's like the same as a 1 over 4 power. So here we go. This is the fourth root. It's like 1 over 4 power, but it's in the denominator. So when you write it on the top, we will just write it as parentheses with x to the third power minus 2 inside. And then we raise this to the negative 1 over 4th power, like that. And when we are looking at the expression in this way, we can just use the power rule and also the chain rule. And we will do that, of course. So here we go. I'll just put this down. Blue, why not? All right. Power rule in action first. So we have the negative 1 over 4 all the way in the front. Inside stays the same, so x plus third power minus 2. Negative 1 over 4 minus 1, just do your fraction, you end up with negative 5 over 4. And we do our chain rule. The derivative of the inside. The derivative of x to the third power is 3x squared. And just one term because the derivative of negative 2 is just 0. So this is all we need. Lastly, we put things down together. Negative, and this is on the top, so let me write down as negative 3x squared over, we have this 4 right here. I'm going to bring this down to the denominator, and because that's a negative power, right? So we'll just write it as x to the third power minus 2 times, 2, and then raised to the 5 over 4th power, and that's a positive 5 over 4. Well, I didn't leave the answer like that. I changed the answer to the radical form. So remember, whenever we have a fourth, like if the power has an over 4, that turns out to be a fourth root. So on the top is negative 3x squared over, this is 4. This little fraction, no denominator, is the fourth root. And then we just write inside as x to the third power minus 2 and raised to the 5th power. And some people might be wondering, should I factor out, should I take out x to the third power minus 2 to the first power and then times, doesn't matter, this is the answer already, okay? You can simplify the radical if necessary, but in calculus, this right here is totally acceptable. All right, number 17. I will do it here, maybe. Let's see. Let me just write it down right here. I don't know why I want to do this, but like, I think I can fit in number 17 right here before I erase. So let me just do that. I will erase this part, and then I'll put in number 17 right here. I know I just feel really satisfying if I can fit a lot of math on one board. No. Anyway, we are going to be differentiating. This is the first time that we are doing the inverse tangent. So we have the inverse tangent. And this notation, I know it's one of the most disliked notation in math. Some people like to write it as the arctangent, but it's the same thing, right? So just get used to it. This doesn't mean 1 over tangent, so just keep that in mind. Anyway, we have the inverse tangent, and the input is square root of x squared minus 1, like that. And of course, if you write it as the arctangent, you just write arctangent of square root of x squared minus 1, like that. Right? Anyway, first of all, this right here is not 1 over tangent of whatever. You don't do the power rule for this. You just have to know the derivative for inverse tangent. So I will put down a quick note right here for you guys. Today, if we differentiate inverse tangent of x, this is the one that you definitely have to know really well. You get 1 over 1 plus x squared, right? Well, how do we prove it? You'll see by the end of the video. Numbers, I don't remember. Anyway, here we go. So whenever we're differentiating inverse tangent of the input, you see that we will do 1 over 1 plus the input being squared. So we'll do that. Right here, we do 1 over 1 plus, we put the inside right here and we square that. So I will put down parentheses with square root of x squared minus 1 inside, and I'll square that. Right? So that's the general form for the inverse tangent derivative. But again, we will have to do the chain rule. Here we go. The derivative of square root of something is 1 over 2 square root of the inside. You keep it again, right? Just keep it. But we do the chain rule again because the derivative of the inside. Derivative of x squared minus 1 is 2x. So we multiply by 2x like this. Alright, so this is the idea. This is pretty much it. And now we just simplify. I noticed that we have the 2 over 2, so we can cancel them out. That's very nice. And we also see that this square and the square root cancel each other out. That's also very nice. When we cancel this out, we get 1 plus, this is just x squared minus 1. 1 minus 1, cancel it out. That's pretty nice. So that's what we have. And is there anything else that we can cancel out? Yes, because we see that this is just x over x squared, right? So let me just write it down nicely for you. X over this right here is x squared, and we keep it square root of x squared minus 1. This and that, we can cancel them out. We'll just get 1, and this becomes the first power. So finally, the answer is 1 over only x to the first power in the front, and then square root of x squared minus 1. That's the answer right here. Right? Cool. Now, number 18. Number 18, number 18, number 18. Man, number 18. This is going to go on for 6 hours for sure. Hopefully at some point I can do like I can speed up the process. But as I said, the first 20 questions were so I just want to make sure I give that detailed explanation and all that. Anyway, number 18. Here we have to differentiate. We have natural log of x over x to the third power, like that. All right, here we go. X to the third power in the denominator and the natural log of x on the top. We have to use the quotient rule. Two functions dividing quotient rule. Some people will tell you to write this as x to the negative 3 power times natural log of x and do the product rule. That's fine. Up to you though. I'll just do the quotient rule. Why not? So let's go ahead and square the denominator. So we have x to a third power, and we square that. On the top, we keep the bottom function, which is x to a third power, and we multiply by the derivative of the top. The derivative of natural log of x is 1 over x. Good. And then we minus the top function, which is natural log of x. I would like to use a parentheses right here, natural log with the input x, because I will have to multiply by the derivative of the inside, the derivative of the bottom. The derivative of x to the third power is 3x squared. Without the parentheses, it seems like you can just multiply the x and 3x squared together, but no. This x is an input for the natural log. This is just like 3x squared being multiplied with the whole function. You cannot multiply the x and the x squared right here, no. Right? Anyway, this is pretty much it for the derivative. Now simplify this. X to the third power over x. We get x to the second power. Let me just cancel things out for you guys. This right here, cancel out. So we get x squared, and this is minus, and perhaps I'll just bring that to the front, 3x squared, and then we have natural log of x. Whenever there's nothing after the natural log, and there's only one input for the x, for the natural log, you don't necessarily have to put on the parentheses. So this is okay. On the bottom, x to the third power square, we get x to the 6. That's the answer, you'll see, x to the 6. Well, we can do more, because notice that we can factor out the x squared and then cancel things out, right? So we will do that. We have the x squared in the front, and then 1 minus 3 natural log of x over x to the 6th power. We can reduce. That's how I know this is a 4. Anyway, finally, we get 1 minus 3 natural log of x over x to the 4th power, and we are done. That is it. Okay, number 19. We are going to be differentiating x to the x power. I see x to x power. Does it have the power? I can just bring the power to the front, and then this is x, and then 1 minus 1 for the power x minus 1, like this. Of course not. You know it. You know it, you know it. Otherwise, I have to change that to blue, Alright, here is the deal. This right here, it's not a power function, and it's also not an exponential function. It's kind of like both. Because you have x for the base, and you also have x for the exponent, right? So it's like both. I will show you guys how you can take off this without doing the implicit differentiation. This is the deal. The idea is that you want to work with space e, right? Whenever you have an exponential function, but this is not really an exponential function yet, because again, the base is x. You don't want to work with space x. This is how you can do it. Look at x, and I'll put on a note right here for you guys. What we can do is, we can write x as e, as I said, because we like to work with base e rather than any other base. And well, if I want to get back to x, I can just put e to the natural log of x power. Because they cancel, you just get x back. Now, we'll just change this. We will be looking at e to the natural log of x, and then raised to the x power, right? Well, however, you see that this to the x power, we can just multiply the powers together, so we just have to differentiate e for the base, x times natural log of x for the power. So this is the idea. You want to work with space e whenever you have a function to a function power. This is one of the ways to do it. I will show you guys the implicit differentiation once we get to that part. Anyway, here we go. To differentiate e to the something, first of all, just repeat that, which is just e to the same thing, x natural log of x. And then you multiply by the derivative of the input because of the chain rule, right? Derivative of this, I will keep the x, keep the first function, and we multiply by the derivative of the second. Derivative of natural log of x is just 1 over x. And then we add the second function, which is natural log of x, times the derivative of the first. Derivative of x is just 1, so we multiply by 1, like that. So that's pretty much the idea. And now, check this out. What's e to the x to the natural log of x power? This is the same as that, yeah? Which is the same as that, which is the same as x to the x. So all the way in the front, we have x to the x power. And then x times 1 over x, of course, is just 1. And this right here is just natural log of x. And we're done. That's it. X to the x times 1 plus natural log of x. That is the answer. Pretty good, huh? And now, as I said, we are getting to the implicit differentiation part. For question number 20 to 29, I believe that's my setup for that. I know my hands are really dirty because of all this is pretty dirty. So yeah. Let's see, I shall be able to do it here. All right, question number 20. Okay, we have to find dy dx, right? So our goal is to find dy dx, which is the derivative. But the problem is that the y is not by itself. We will have the equation x to the third power plus y to the third power, and we have that equal to 6 times x times y. Right? So we're given this equation. The y is not by itself, but it's okay. This is how we can do it. Let me just put down d dx all the way in the front to tell people that we are differentiating with respect to x, right? And with that being said, that means y is a function of x, and you have to do the following carefully. Anyway, here we go. Differentiating x to the third power, we get 3x squared, and that's it. Differentiating y to the third power, we get plus 3y squared, but you know this is like saying y to the third power, so we have this, and then you look at the inside. The derivative of y to the third power was 3y squared, but since y is a function of x, we will have to multiply by dy dx, the derivative of the inside. The derivative of y is dy dx. And you might be wondering, how come we didn't do that? Well, if you would like, you can just think about it like this. X to the third power, so you have 3x squared, and you should multiply by dx, huh, isn't it? Well, what's dx over dx? It's just 1. So you don't have to do that. So be really careful with this idea. So this is just that, but this will give you this right here. Right? Now, for the right-hand side, this is 6x times y. So let me just say this is the first function, that's the second. Product rule in action, keep the first function, which is 6x, and multiply by the derivative of the second. The derivative of y is just dy dx. And then we add the second function, which is y, and we multiply by the derivative of 6x, which is just a 6. Whew, my God. This right here is a write-off for the implicit differentiation. And now we have to isolate dy dx, because that is the derivative. And to do so, well, I'm going to move this to the other side. I'm going to move this to the other side, right? Because I want to collect all the terms that have the dy dx. So we can factor out the dy dx, and then can isolate that. Well, let me just write this down for you guys. I'm going to move this to the other side, but I will also factor the dy dx in the meantime. And when I factor it out, I would like to put the dy dx at the end, and then open the parentheses in the front. And the reason I want to put the dy dx at the end is that this right here, it's the object, it's the derivative. It looks similar to d dx, but d dx means to take the derivative, right? This is what we are trying to find already. This is the things that you have to do, the operator. So I prefer to have this at the end of the parentheses rather than in the front, because otherwise it might look like we still have to differentiate, which is not correct. Anyway, this right here was positive, 3y squared. I brought this to the other side, so it will be negative with a 6x. And we factor out the dy dx at the end right there already. This is equal to 6y. Let's keep the positive first, and then we bring this to the other side, becomes negative 3x squared, like that. So that's pretty much it, huh? And then of course we can divide. So we see that dy dx equals, here we have 6y minus 3x squared, and over, right here we have 3y squared minus 6x. Well, we can actually reduce this a little bit, and I'm just checking that my answer key is legit. Yes, it's good. My answer key is good, because as I said, I come up with all the answer key. No, I come up with all the answer choices myself. I just want to make sure that I didn't mistype anything also. Anyway, we can factor out 3 on the top. So here we have 2y minus x squared, and then we can factor out 3 on the bottom as well. So this is y squared minus 2x. Cancel, cancel, and in the end, dy dx equals 2y minus x squared over y squared minus 2x. I just noticed if you differentiate this, you get that. If you differentiate that, you get this. I don't know, coincidence. Yeah, that's it. Oh, interesting enough, I actually have this right here, right? Number 20, if you can see it right here. I have the answer key backwards. On the answer key, the reason I did it is I just put the x first and then factor it out. So in fact, this right here, it's the same as saying we can factor out negative and then put the x squared minus 2y and then over negative, and we'll put this first, which is 2x minus y squared, and cancel out the negative. And it depends how you move the things around. So it's either this one or this one. And you should be able to see that the answers are equivalent. So that's just the algebra part that you have to know. So this and that are the same, right? So yeah, just like this. So take a look, take a look, take a look. All right. I was expecting to, I think to do 100 derivatives will take longer to do compared to 100 integrals, because it's just like so many things I have to go through. I don't know, man. I don't know which one will take me longer. I don't know. Anyway, next one, another implicit differentiation. I will just write down the equation for you guys though. So here we have number 21. Should I retire this marker? I hope not. Good job. You can still work. Okay, we have y sine y equals x sine x. All right? Okay, y is not isolated, and in fact, you cannot isolate y in this situation. It's okay. Just go ahead to d dx, implicit differentiation. Here we go. This right here requires the product rule. So I will keep the first function times the derivative of the second. Derivative of sine of something is cosine of the input, and then the input is y. So we have to multiply by dy dx, because that's the derivative of y, and this is the chain rule. And then we have to add the second function, which is sine y, right? Second function is sine y, so just put on sine of y. And we multiply by the derivative of the first. The derivative of y is dy dx. So we multiply by dy dx, like that. So this is the left-hand side. Now for the right-hand side, same thing, but with x instead of y. Product rule again, keep the first function times the derivative of the second. Derivative of sine is just cosine, and notice that the input is x. And we are differentiate that with respect to x. So it's just cosine x like this, and we're done for that, okay? And then we add the second function, which is sine x, and we multiply by the derivative of the first, which is 1. So I should also put down the cosine x in red. First times the derivative of the second, plus the second times the derivative of the first. This is it. And now we can just factor out the dy dx on the left-hand side and then divide it. That's pretty much it, right? So we'll do it in one step. Because we see that this is just dy dx, we can just have this and that being factored in the parentheses. This is the right-hand side, so we have x cosine x plus sine x over this and that in the denominator, namely y cosine y plus sine y. And we are done. This right here is the answer. And that was number 21. And this is number 21. All right, number 22. Here we are going to differentiate natural log of x over y. And this is equal to e to the x y to the third power, like that. Okay, so implicit differentiation, but before we do anything like that, notice that we have a natural log of x over y. The truth is, we can break this down. We can write this as natural log of x minus natural log of y, so that we can just differentiate the first and then minus the derivative of the second. right? And of course, this is just the algebra. We'll just write down the rest. And here, we will just put down d dx to signify that we are differentiating with respect to x. Here we go. The derivative of natural log of x is just 1 over x. That's it. Minus the derivative of natural log of y is 1 over y, but the inside is y. The derivative of y with respect to x is dy dx. This is how we squeeze out the dy dx. Equals, here we have the derivative of this. Well, e to the whatever, you just repeat e to that whatever, x, y to the third power. And now, we differentiate the power. Yes, we do the product rule. This is x times that, right? So, the first function is x, and we multiply by the derivative of the second. Derivative y to the third power, we get 3y squared, and you know the deal, we have to have the dy dx. And then we add the second function, which is y to the third power, times the derivative of dx, which is just 1. So this right here is what we have. Well, let's see what we can do with all that. Man, how to simplify this? Well, we have a fraction with x and y, right? X here and y here for the denominators. I think it's a good idea to just multiply out everything by x, y so that we don't have to deal with the complex fractions later on. So we'll do that. And perhaps I'll just put down this in blue. Okay? So we are going to multiply everybody by x, y. So again, the point is so that we don't need to worry about the we don't need to worry about the complex fractions later on. All right, xy times 1 over x, we get y. And then minus xy times 1 over y, we get x. And this is still dy dx. And perhaps I'll just put on the xy right here. So we have xy e to the xy to the third power. And man, let's also multiply everything else right here. So check this out. Okay, let's just do this thing backwards, right? So it's this times that. Yeah? We did this times this already. Oh, man, draw the arrows is kind of fun. We did this part already. Now, we have to do this times that, but also this right here has to be multiplied inside. Okay? So here we go. X times x is x squared. Y times 3y squared, so we have the 3 right here, and then y squared times y is y cubed. Right? Yes. And then I will put this down, which is e to the xy cubed. And I will put down the dy dx. Good. Next, we do this times that, so we put down plus. We have x, y to the 4th power, and multiply by that. So it's e to the xy cubed. Just like that. Very good, huh? All right, now we have to do what we did before. I'm going to keep this on the right-hand side because I would like to add this to the other side. I want to keep everything positive, right? And now bring this to the other side. It's easier this way. So when we do that, let's see. On the right-hand side, again, we'll factor this out. We'll put it at the end. So we have the dy dx. Well, this was positive, so we just write down 3x squared, y to the 3rd power, e to the xy to the 3rd power. And when we bring this to the other side, it becomes a plus x. And this is being factored out right here already. So that's what we have. And for the left-hand side, this y is still just chilling right here. But we will have to move this to the other side. So we minus x, y to the 4th power, and then e to the xy cubed, like that. In the end, we just need to divide this on both sides and we'll be done. So perhaps I should be able to fit in here. So dy dx equals, this right here will be divided here. So this is on the top. So I will just write it right here. Y minus y minus xy to the fourth power e to the xy to the third power, and then divided by, well, perhaps we'll put this at the end. Just put the x right here. So we have x plus this part, 3x squared y cubed e to the xy cubed, like that. And let me just make sure I didn't do anything wrong. I didn't do anything wrong because I see the answer on my answer key. Good. Whew. So a slightly longer one, but it's not that bad. So take a look right here. All right, question number 23. Question number 23. This right here is a weird one. We have x equals secant of y, like that. And now you might be wondering, okay, can we just isolate the y right away by taking the inverse secant on both sides? Yes, you can do that. But what's the derivative inverse secant? Well, if you remember it, it's okay. You can just put on the answer. Or, I'll just tell you guys that I do know the answer. I'll just put on right here. Derivative of inverse secant of x. This right here is 1 over x square root of x squared minus 1. And does this look familiar to you guys? No, I'm not trying to show you guys my back. I am trying to show you guys my back, but this is actually one of the answers that we got earlier from one of the questions, right? You can let me know which question it was. Anyway, if you remember this, good. But if you don't, this is how you can prove it. I will show you. Right here, the y is not isolated. This is slightly more preferred because we do know the derivative secant x. Secant y in this case, yeah, actually. So we can handle the original secant. This is how. Okay, taking the derivative x is just 1. Well, derivative of secant, this is the original. We just have secant of the input times tangent of the input, and the derivative of the input, thanks to the chain rule, we have to multiply by dy dx. And now we can just keep this right here and divide both sides by this. So we get dy dx being equal to 1 over secant y times tangent y. Right, and you might be thinking, hey, this is not that bad at all. But here's the trouble. If you want to figure out the derivative of inverse secant x, well, if you want to just take the inverse secant x on both sides, the idea is that when you take the derivative of inverse secant of x, your answer should be in terms of x as well, isn't it? So now this is how you get back to x. Again, this question right here is to show you guys how to prove this right here, right? All right, so to handle this, well, we do know secant y is equal to x, which is the same as saying x over 1. And by looking at this right here, we can come up with a right triangle. So I will put down the right triangle right here. And the reason to do so is because we can put the angle here, that's y, and we can label the sides. And remember, secant is what? Secant is hypotenuse over adjacent when you are talking about right triangle. So that means x is right here and y is right here. And now, for the other side that's missing, well, the easier way to find this out is just you open the square root and you square the hypotenuse, which is x squared, and you minus the square of this side, which is 1 squared. By looking at this triangle, you can figure out whatever you want. Of course, for tangent as well. Here is the deal. In the end, you will see we have a 1 on the top over secant y is just x over 1, which is just x. That's good. And tangent of y, of tangent, this picture here is just the opposite, which is this, over the adjacent. Over 1 doesn't matter, so it's just that. So we can just put down square root of x squared, and then minus 1 squared, which is the same as just minus 1. That's it. That's it. So this right here is how you prove the inverse secant has the derivative being that, right? So this is one of the ways to prove it. I will show you guys how to prove the inverse tangent derivative by using the definition once we get here. All right, number 23. That was question number 23. Man, when can I drink the ninja milk? I don't know. So I'd like to tell you guys, this right here is seriously just running a marathon. So this is like almost halfway done. So mile 6-ish, right? That was question number 23, and now moving on to question number 24, of course. 24. And we have parentheses x minus y squared, and that's equal to sine x plus sine y. Like that. All right, implicit differentiation in action. So dx. Here we go. Right here, bring the 2 to the front because you have to look at the big picture. So power rule first, right? Bring the 2 to the front and the minus 1. So here we have 2. Open the parentheses. And then the inside stays the same, x minus y. And do the chain rule. Look at the inside and ask yourself what the derivative is. Derivative of x is 1 minus the derivative of y is dy dx. And notice that it has 2 terms, so you have to put parentheses. That's it for the left-hand side, and now for the right-hand side. This right here, you don't need to do the product rule. Just differentiate the first, which is going to give us cosine x, and differentiate the second. We get plus cosine y, but the derivative y is dy dx. So don't forget the dy dx right here, just like that. Well, we have to multiply this out. And based on how I come up with the, just multiply this out. Anyway, I think I multiply this out as well. So I will just multiply, I'll do this for you guys, this and that first. So I'll multiply this out this way for you guys. When we do that, I will keep the 2xy, 2 times x minus y. Right? I'll take this quantity times 1, which is still that, and then minus 2 times x minus y, and we have the dy dx. Right? And that is equal to the right-hand side, which the right-hand side didn't do a thing, so I just write it down. Cosine x plus cosine y, and again the dy dx right here. Okay, I would like to keep the dy dx on the right hand side so that I can make that positive, and I'll bring that to the other side. So perhaps I'll just write it down right here first. This right here stays, so it's 2 times x minus y. Bring this to the other side, which is minus cosine x, and that's equal to, well, bring this to the other side, it becomes positive 2 parentheses x minus y, and we add this with cosine of y, and then both of them have the dy dx, so factor it out, put it at the end, like that, right? And in the end, of course, we can just bring this to the other side by dividing, and that's pretty much it. So we'll do that. Finally, dy dx. The answer to that is this on the top. But of course, now it's the time to distribute. So we have 2x minus 2y, and then minus cosine x, and bring this to the other side, right? So I'll also divide that. This will be on the bottom. 2x minus 2y plus cosine y. So this right here is a plus. Right? This right here is a plus. That's it. Right? This right here is the answer. That was question number 24. And I think it's a fair time for me to change the marker. This time, unfortunately, I cannot do 100 derivatives with one marker. I don't have a fresh marker. Hopefully this one will work well. Ah, much better. Okay, that was question number 24. Okay. Oh, look at that. Look at that. Next one, we are going to find dy dx for the following. X to the y's power equals y to the x power. This is actually one of the really famous question. This is, the equation wise. Why? Because I have a video on this equation, how to solve for x and y that satisfies this equation, and it has a lot of use. Anyway, we are going to find the derivative right here. Well, this is the function. Y is also a function. So we cannot just do anything in the moment. Earlier, we did x to the x, and then we wrote the base x as e to the natural log of x. That will show you guys this way, right here. Right? We can do that. We can write x as e to the natural log of x raised to the y, and then we can write y as e to the natural log of y, and then raised to the x. We can still do that. But in this case, it might be easier if we just take the natural log on both sides to begin with. We would like to do some algebra first. And this is also a pretty good strategy whenever you have a function to a function power. Or maybe when you have a lot of functions multiplying together or dividing, you can take the natural log on both sides. You can use the natural log properties to bring things down. Anyway, enough talking. Here's the deal. This is y as a power. We can bring the y to the front, but do not minus 1, because we are not doing derivative. This is just the natural log property. Bring the y to the front, we have y times natural log of x, like this. Okay? And then similarly, we bring this to the front, we have x times natural log of y. Seriously, just like that. Okay? Now, we are going to differentiate. So put the d dx right here. It doesn't have any weird situations. This is just the innocent case. You can just use the product rule now. So here we go. Product rule in action, we keep the first function, which is y, times the derivative of the second. Derivative of natural log of x is just 1 over x. And then we add the second function, natural log of x, times the derivative of the first. Derivative of y is dy dx. Here is the dy dx. Aha. Then we add, we have this equal to. Then we have this equal to. Here we have the product situation again. Keep the first function, which is x, times the derivative of the second. Derivative of natural log of y is 1 over y times the derivative of y, thanks to the chain rule. Here is the dy dx again. Right? And lastly, we have to add the second function, which is natural log of y times the derivative of the first, which is just a nice 1 right there. Okay, so that's the idea. Well, right here, again, we see that we have an equation with fractions, so we have the x and y. So perhaps let's multiply everybody by this denominator and that denominator. Let's put down the x, y all the way at the end. Okay, so you guys can still see this one. Anyway, here we go. Just draw arrows for you guys. X cancel by y, and y becomes y squared plus this times that, so it's xy and then natural log of x and then dy dx. This times that, the y cancel, so we have x squared, so this is equal to x squared, and this is dy dx, and this is xy natural log of y, like that. And I'm back here. Now move this to the other side, move that to the other side, so we have this right here. I can just keep it xy natural log of x. Hold on, let me see how I subtract. Yeah, I did it this way, because that's what I put down for the answer choices. Of course, if you subtract the other way, that's okay too, and then you just get the backwards version, and it's actually equivalent, so that doesn't matter. Anyway, I will move this to the other side, so we have minus x squared, and we will, of course, factor out the dy dx, put it at the end, and this is equal to, we have this right here first, which is xy natural log of y, and then minus y squared, like that. In the end, divide this on both sides and we'll be done. So finally, dy dx equals xy natural log of y minus y squared all over xy natural log of x minus x squared. It has a pretty nice symmetry in my opinion, just like that. Very, very nice, isn't it? Yeah. First page done. Look at that, look at that, look at that. So page 4 actually, but the first sheet done. Man. So I'm afraid, man, this has a lot. It's okay. It's okay, it's okay. It's like, seriously, for the first one, for the first integral of 100 integrals, I didn't know if I was able to do it or not. Just like my first ever marathon, I was not sure if I was able to finish it or not. But I did. Just like I did finish the 100 integrals, right? And after I finished that, it's like, man, I just want to do more and more and more. It's just like, I've been running about, I have done 9 marathons in my life already. It's not a lot compared to the elite runners, but it's a lot for me, seriously, because I'm not like a good athlete in the first place. So, I'm enjoying it a lot. Anyway, number 26. We are going to find the derivative for inverse tangent. And the input is x times y, x squared times y, and that's equal to x plus y to the third power. Alright, so this right here is not so bad. I don't recommend you guys to take the original tangent on both sides though. We'll just keep this right here because the derivative in the end will be more algebraic rather than you'll see the like, inverse tangent whatsoever. I mean, you know what I mean. Anyway, go ahead and do the derivative. Here's the deal. Inverse tangent, right here, we get 1 over 1 plus, parentheses, you put the input right here and square that all the time, okay? So you have 1 over 1 plus, parentheses, x squared times y, and we have to square that. This is just a general form for inverse tangent when you take the derivative of that. But we have to do the derivative inside. So here we go. Derivative of x times y, so x squared, you keep it, and then you differentiate the second, so that will be dy dx. That's the derivative of y. And we add the second function, which is y, times the derivative of the first, which is just 2x. Whew, just like that. Not so bad, huh? Now, on the right-hand side, that's the even better news because it's not so bad at all. Derivative of x is 1, and you don't do product rule here. It's just a sum. So you just do the derivative of x, which is 1, and you add derivative of y to the third power is 3y squared dy dx. Just like that. Okay, again, we have equation with fraction, and I did clear the fraction before I go, so we'll see. This right here, if you look at and just work this out, this is 1 plus x to the fourth power, y to the second power, right? So I would prefer to just multiply everybody right here by that denominator, which is 1 plus x to the fourth power, y squared. Okay? And again, let me just show you guys. We multiply this right there, and this right here, and this right here. I only draw 3 arrows because this quantity is being multiplied by that. When we do this times that, this and that cancel, so we just have this. Over another thing is, you can just think about multiply this on both sides. Yeah. Anyway, so on the left-hand side, we get x squared dy dx, and then 2xy. So let's just put that down, plus 2xy. And that's equal to, I will do this times 1, which is just 1 plus, let me just put it down like this in blue. 1 times that, so we can just have 1 plus 4x, sorry, 1 plus x4, x to the fourth y squared, right? 1 times that. Then what we do next is we do this times that, but it has the dy dx. So I'm not going to multiply it out yet. I will just keep it as plus. This is 3y squared times this thing. Actually, let's do this. 3y squared times 1 is 3y squared. And then 3y squared times that is plus 3. And we have the x to the fourth power, y to the fourth power, like this. Okay? We'll take this and multiply by that. And then we have the dy dx all the way at the end. And notice I didn't distribute the dy dx, okay, for a good reason. You can do it, but it doesn't really matter. Let me see. It's actually a good idea. Let's just do that. Let's just do that. Why not? All right. So multiply this and that. So we have 3y squared dy dx times 1. So 3y squared, and perhaps I'll just put on dy dx right here. And then this times that, we have plus 3x4 y to the 4 dy dx. All right, so this is what we have. All right, and this is it for the calculus, and now this is just the algebra part. Anyway, I am going to move this to the other side, factored out the dy dx. So you see, here I'll open this right here is x squared. It has the dy dx. I will factor it out and put it at the end. I will move this to the other side, so it becomes negative 3y squared, and the dy dx will be happening at the end. And I will also put this to the other side. That will be minus, and we will have 3x to the fourth power, y to the fourth power. All in all, everybody will have the dy dx, so we just put down the dy dx at the end, like this. And then we have this, and that, so we just put 1 plus x to the 4, y to the second. Bring this to the other side, it becomes minus 2xy. Yeah, that's pretty much it. And then divide this to the other side, and we are done. So finally, dy dx equals 1 plus x to the fourth power, y squared minus 2xy, all over that guy, x squared minus 3y squared minus 3x4 y to the fourth, like this. And I would like to check my answer choice to see if I can find it. I have the other order again. So this is the trouble, like depends on how you want to. No. The way I did it is I moved this to the other side. So that's why you see the answer key is, that's why you see the answer choice has the x squared being negative. Anyway, this is the part that you just have to kind of work out the sign on your own. The way I did it is I put this to the other side, and I put these two on the other side. So the answer key, okay, or you can just write this down, dy dx. Let's try to see if we can do this in our head. I maintain this, and I bring this to the other side, so I have 2xy being negative, 2xy being positive. I move this and that to the other side, so I have minus 1 and then minus x4 y to the second, and then divided by, I kept this and that positive, so we have 3x squared and plus 3x4 y to the fourth, and then minus, I will bring that to the other side, so that's minus x to the second power. So that's pretty much it. It's the same as that, but they're just off by, just multiply negative. You get that. So it depends on how you move things around. So I'll box this because that's the one that I have on the answer key. On the answer choices, I should say. Anyway, let's see. Whew. All right, number 27. Here we have x squared divided by x squared minus y squared, and that's equal to 3y. How many of you guys ready to do the quotient rule on the left-hand side? Raise your hand. Good, nobody, because I don't like it either. This is what we do. Multiply both sides by this denominator, x squared minus y squared. Why? This times that will be gone. We will get x squared, and that will be equal to this times that. Just multiply it out. We don't have to do the quotient rule if we don't need to. So when we do that, you'll see this and that together, we will get 3x squared y, and this and that together will give us minus 3y to the third power. This equation and that equation are the same. Well, of course, you have to worry about the domain, but derivative right here, just focus on the derivative. Anyway, right here, we differentiate it. So ddx in action. On the left-hand side, this is everybody's favorite derivative equation. It's just 2x. On the right-hand side, okay, here we go. Product rule in action. First function, keep it. Multiply by the derivative the second. Derivative of y is dy dx, so just put that down. Plus the second function, which is y, times the derivative of the first, which is 6x, like that, right? 6x. Well, right here, we have to bring the 3 to the front, minus 1, and we have minus 9 y squared, and remember y is a function of x, so we have to multiply by dy dx, like that. Okay, so this part, I will just, of course, keep this and that on the on the right-hand side. Move this to the other side. So we get 2x. This to the other side becomes minus 6xy. And this right here is equal to, I can factor out the dy dx. I will write down 3x squared minus 9y squared and dy dx. Okay? All right, divide this on the other side. So we get dy dx. Keep in mind, this is on the top. This is right here, 2x minus 6xy, all over this right here, 3x squared minus 9y to the second power. Can we simplify? I think so, or did I not do it? No, we cannot simplify. On the top, we can factor out 2, but it doesn't do us any good. I didn't factor out anything. Yeah, just leave it like that. Because if you factor it out, we cannot cancel, so why bother, right? So that's it. All right, now I would like to do number 28. Side by side with number 27, you will see why. Okay, here we go. Number 28, we have e to the natural log of x minus, so e to the x over y, and that's equal to x plus y squared. All right, first thing first. You can take the natural log of both sides and get rid of the e. That's fine. But it doesn't really matter. You can just deal with the e. That's just as fine, okay? So I would just like to do the equation as how it is. Notice that we have x over y. With that, we have to just use the quotient rule. If you take the natural log on both sides, you can multiply by y and let me know how that goes. You have to use the chain rule a lot. So I think that's a trade-off, but up to you. Anyway, here, dx all the way across. Left-hand side, e to the xy, the derivative of that, we just keep it first, which is e to the x over y, and then multiply by the derivative of the inside. And we have to use the quotient rule. Here we go. Square the bottom function, which is y squared, like this. Right? So square the bottom function. And then we write down the bottom function times the derivative of the top. Derivative of x is 1. And then we minus the top function, which is x. And we multiply by the derivative of the bottom function. Derivative of y is dy dx. So it's like that. Whew. Done for the left-hand side. And then for the right-hand side, this is nice if you are willing to just keep the e to the whatever on the left-hand side, right? If you don't do the natural log. So here, derivative of x is 1, and derivative of y to the second power is 2y and the dy dx, like that. Okay? Now, let's do the following. Because again, we have an equation with fractions right here. So it's a better idea to just clear out the fractions right now. Let's multiply everybody by the denominator, which is just a y squared. So I will multiply this with the whole thing here, and then multiply and multiply. Yeah, just like that. Okay, so if you look at this part, this times that will cancel out, but we still have e to the x over y times this and that. Let's distribute it. This into here, this into here. So first, we will have y times e to the x over y, right? And then we have minus x. And then let's write that down first. E to the x over y, and then let's put down the dy dx. Usually have the dy dx all the way at the end. That's a good idea. Okay, that's it. And then on the right hand side, y squared times that is y squared times that is plus 2y third power, and then the dy dx. Okay, to make things positive, let's bring this to the other side. Let's bring this to the other side. So we get y e to the x over y minus y squared, and this is equal to, okay, I will put this down first, parentheses 2y to the third power. Bring this down, becomes positive, right, to the other side, positive x e to the x over y. And then both of them have dy dx, so I just put the dy dx all the way at the end, like that. Okay? Now, divide this guy on both sides and we'll be done. So we will have the dy dx equal to, here we have the y e x over y power minus y squared over, well, I think I like to put a similar term in the front, right? So I did have this right here go first. I just want to show you guys how I have the answer. I have this first, so I will just put this down, x e to the x over y plus 2y to the third power, like that. Okay? And of course, if you switch the word on the bottom, nobody will get mad at you. Just kind of pick the best answer on the answer choices. So that one is the implicit differentiation with quotient rule. This right here, you should not do the quotient rule. Okay? So that was 28. And 2 more, I can drink my milk. When I first saw his video that he said he had a energy drink, I thought he was joking because he always does that, right? But then I watched the whole thing, so oh my god, it was legit. So I ordered it right away because I used to watch him a lot when I was probably your age. Yeah. Right, so subscribe to Niga Higa. That's his channel's name. Niga, Higa. I'll have the link in the description. Why not? Okay, number 29. Number 29. X squared plus y squared minus 1 to the third power, and this is equal to y, like this. Okay, so let's just deal with this. And the good thing is that I didn't multiply out anything for the answer key. You will see what I mean by that. So let's go ahead and differentiate on both sides. Okay, here we go. On the left-hand side, look at this to the third power. So bring the 3 to the front, and then minus 1. So here we go. We have 3 parentheses. The inside stays the same. X squared plus y squared minus 1 to the second power. And then we multiply by the derivative of the inside. Open the parentheses because we have more terms coming. Okay, derivative of x squared is 2x plus the derivative of y squared is 2y dy dx. And then the derivative of minus 1 is just 0, so we are done. Yeah, that's it. On the right hand side, we have this, the derivative of y with respect to x is just dy dx. And you see, hopefully the notation makes sense. d dx of y is just dy dx. Okay, now simplify this guy. This is what I mean. I didn't multiply this out, or just keep this, okay? So, to clean things up, we will take this as the whole thing, multiply with this, multiply with that. So let's distribute it first. So, 2x times 3 is 6x. And then we have all that, which is x squared plus y squared minus 1 squared. Yeah. And then 3 times 2y is plus 6y. And then, of course, we write that down first before the dy dx. So let's put that down right here. And dy dx. And right-hand side, we still have the dy dx as well. Okay? Okay, you know the deal. Bring this to the other side. So you have 1 and all that. So perhaps I'll show you guys more work. 6x x squared. I know some of you guys can do this in your head, but I'll have to show you guys all the work. Here, right-hand side, this is like saying 1 dy dx. So we have a 1. And then this on the other side becomes minus 6y parentheses x squared plus y squared minus 1 squared. And then everybody had a dy dx right here, so factor it out. Now bring this to the other side by dividing, and that's it. So dy dx equals, that's on the top. So just do that. 6x x squared plus y squared minus 1 squared all over 1 minus 6y parentheses x squared plus y squared minus 1 squared, like this. Done. Okay, good. Number 30, my God, finally. But it's not any easier. Why? Because we are doing second derivative from number 30 to number 39. Why? Anyway, this right here, I will have to write down the question for you guys. We are going to find d2y dx2. And if you look at this right here, this is the second derivative notation. The idea is because, well, to get the second derivative, you just have to differentiate the first derivative, right? Well, as I said, we have to differentiate. This is the notation for differentiating. We have to differentiate the first derivative. Oops, dy dx. We have to differentiate the first derivative. And now you see, we have d and d, so that's d squared. That's just a notation. It's not really like d squared, but we put on d2y. That's how you say it, d2y. And on the bottom, you see you have dx and dx happening twice. So we have dx2. That's the notation for derivative, for the second derivative, okay? All right, what's the equation? That's the main thing, huh? We have 9x squared plus y squared equals 9. Okay. Here we go. We have to differentiate this twice. Why it's not isolated? It's okay. Just do implicit differentiation. Go ahead, d dx that. Now, on the left-hand side, this is 18, right? 18x to the first power, derivative this. And the derivative that is plus 2y. Y is a function of x, so we have the dy dx, like that. Well, the derivative of 9 with respect to x is 0, so this is equal to 0. Good. Now, check this out. I will have to move this to the other side. So we have 2y dy dx, and that's equal to, this to the other side becomes negative 18x. And we will just divide the 2y on both sides. So they cancel, and you just get dy dx equals, reduce that, you get negative x on the top, 9x on the top, right? 9x on the top over y, so negative 9x over y. And you see, this right here is the first derivative. We just have to look at this expression and differentiate that again, so we can get the d2y dx2. So let's do that right here. Let's just emphasize that, right? d dx, this right here, right? d dx, this right here. So we see right here we get d2y dx2. On the right hand side, we have to do the quotient rule again, just like the example that we did, number 28, I believe. Square the denominator. So parentheses y, square that. Okay, the bottom function is y times the derivative of the top. The derivative negative 9x is just negative 9, so this is the derivative on the top. Minus the top function, which is negative 9x. Top function, just write it down. Times the derivative of the bottom. The derivative of y is what? dy dx, isn't it? I'll put this down. Derivative y is dy dx. Okay, so you see that the second derivative is based on the first derivative and other stuff, right? But the truth is, if you look back, dy dx, look back right here. This right here is just negative 9x over y. So we can replace this right here real quick. So we see for the second derivative, we will end up, let's see, we end up negative 9y. Negative, negative, without any further explanation, it's just positive. 9x right here. And we can replace that. We can replace the dy dx with this. So I will do that real quick. Wait, I thought I turned this thing off already. It's the Wi-Fi that want me to connect. No, I don't want that. See? The Wi-Fi is telling me to update. Okay, anyway, this right here, just put it down right here, which is negative 9x over y. Okay? And we divide this by y squared, like this. So far, so good, right? Hopefully, that's the case. And, of course, again, this right here, we had a complex fraction, so perhaps we do the following. So the rest is just some kind of simplification. Okay, here we go. I multiply the top and bottom by y. Because, so that I can get rid of the complex fraction situation. And let's see, I should be able to fit in here. Let's see. This is going to give us negative 9y squared. And this is going to give us y and y cancel out. But 9 times negative 9 is negative 81. And we have the x squared. Yeah? Over this right here is y to the third power, like this. Okay? And the moment that you think, hey, we are done, but we are not. Because in fact, we can factor something out on the top. And things will work out pretty nicely. On the top, we can factor out negative 9. And you see, if we do that, here we get y squared. And we add, and here we get 9x squared, like this. We factor it out. And does this look familiar? 9x squared plus y squared. Check this out. 9x squared plus y squared. This right here is just equal to 9. So all this right here is just equal to 9. This right here is equal to 9. Of course, the order doesn't matter of the adding. So this is just equal to 9. Therefore, finally, we can simplify the expression to negative 81 over y to the third power. And this right here is it. Okay? This right here is it. Oh, man. This is number 30. So that means I have 3 more to go. This is going to take more than 6 hours for sure. Why did I do this to myself? This is going to be more than 6 hours for sure. Anyway, let me have the ninja milk. Ninja milk. So this is 2 hours and 14 minutes. Give this a timestamp right here. Man. Oh, so this is how it looks like. So it's like capital, like the Japanese drink, and it's sparkling. This is like sparkling. Can you guys see? Hey, it's pretty good actually. It tastes like capital, I think that's how you say it. The Japanese drink, and this is sparkling, and this is organic milk with flavor. So take a look right here. Okay. Ryan Higa's, right? Nika Higa's Ninja Milk energy drink. I don't know if this will really give me the energy to last for another, I don't know how many hours. Really good. Wow. Tastes really good actually. 112 calories per can, right? So you should, for the people, if you care about nutrition here, this is the nutrition label. I'll drink more. How many caffeine do I have? I don't have any caffeine. Huh? Oh, caffeine is 80 milligram. You can see right here. Caffeine is 80 milligram right here. And I get 1 gram of protein. Look at that. Oh man, I feel good. Tastes really good. Whoa. Okay, no time to rest though. That was just, as I said, question number 30. And now we'll drink the Ninja Milk. Tastes good. Tastes good. Okay, question number 31. Well, we just have to do second derivatives. I seriously... Is my clock okay? Man, if I have to do 4 more hours, I'll be going home around 10. Let me see if I can go home by 10 o'clock. I don't know. Okay, if I shut up and do it, I will. Huh. Okay, number 31 right here. Alright, differentiating. Actually, no. d2 dx2, meaning differentiate is twice. Okay, d2 dx2. d2 dx2. Differentiating whatever is inside twice. Here we have 1 over 9. Secant to the secant of 3x, just like that. Okay, so here is the deal. d2 dx2 means dx, sorry, ddx. Okay, so I will do this one right here, just to show you guys what we have to do. We have to differentiate of differentiating like this, and then 1 over 9 secant of 3x. So we look at this, do it inside out. So here we go. And perhaps for the inside, I'll just do the part in black, in blue. And then the final answer, I'll end it with black. Okay? So differentiate this part. Okay, this is not so bad. We have 1 over 9, it's just a constant multiple. Write it down, write it down, write it down. Now, differentiating secant of whatever, you put down secant of not whatever times tangent of the same whatever. But we have to multiply by the derivative of that whatever. Chen says so, not me. Multiply by 3. So that's pretty much the idea. Well, we can reduce this. That's just 1 over 3, so we will. This is going to be differentiating 1 over 3. And here we have secant of 3x times tangent of 3x. Now, differentiating this, product rule in action. This will be my first function. I'll keep it, which is 1 over 3 secant of 3x times the derivative of the second. Derivative tangent is secant to the second power, and the input is 3x times the derivative of 3. The derivative of 3x, which is 3, because of the Chen says so. Okay? So this is the derivative tangent of 3x. Now we have to add the second function, which is tangent of 3x times the derivative of the first. Derivative of 1/3 of secant to a third, secant 3x. You write down 1/3 secant. Actually, oh, I messed up with the color. Sorry. Let me do it again. I messed up with the color. Okay, first function times the derivative of second. Derivative tangent is secant second power of 3x. But we multiply by the derivative of the inside, which is the 3 right here. Now, we add the second function, which is tangent of 3x. Then we multiply by the derivative of the first, which is the 1/3. And the derivative of secant is secant of the input times tangent of the input. And the derivative of that input. So you multiply by 3 right here. So that's pretty much it. And now you see that 1/3 and 3 cancel for the first part, and this 1/3 and this 3 cancel for the second part. And we'll just put things together. Finally, the answer is secant to the third power, right? This times that, first power, second power, third power, and here we have the 3x like this. And we add, this is secant, let's just write down the secant first. Secant 3x, and tangent, so that's tangent second power, right? Second power 3x. And again, you can perhaps factor out the secant of 3x, but secant squared plus tangent squared, not so much you can do with it. So just leave it like that. In fact, that's what I did as well. That's the answer. Okay? This right here is the answer for it. All right. What's after 31? Of course, 32. But it's just another derivative. Second derivative. Number 32. Okay. d2 dx2 of, we have x plus 1 over square root of x. Okay. Do we need to use quotient rule? No, we don't, because thankfully the bottom is just have one term. So that means we can split the fraction nicely. So we will just have to differentiate, right, the second derivative, okay? X over square root of x, and then plus 1 over square root of x. Remember, the square root is like the same as what? 1/2 power. So perhaps I should have written this down as the 1/2 power. So right here, let's put on 1/2, if you would like. Well, that means what? Differentiating this twice. This is like saying x to the first power over x to the second power. So subtract the powers, we get just 1/2. So we have x to the positive 1/2 power for the first one. For the second one, we have x to the negative 1/2. Okay? And now, here we go. Notice I just put on ddx because I'm going to do the first derivative right here already. Let's bring the power to the front, -1, bring the power to the front, and -1. So, for the inside here, you'll see the first answer here is 1/2, and you have x to the negative 1/2. And let's just write it down as a power because we have to do the derivative again. Similarly, for the second one, we have negative though, negative 1/2. And then x to the negative 1/2 minus 1 is negative 3/2. Ooh, I don't know why I did that, but whatever. And then finally, you bring this to the front and do the derivative again. Right? I don't know why I thought it was a good idea to just show you guys a lot of derivatives, like even the second derivative. So I'm actually doing like 100 and like, I don't know, 20 derivatives right here. I don't know. Anyway, this times that, no more ddx, however, just the answer. This times that is negative 1 over 4, and this times that. Don't forget -1, don't forget -1. So we get x to the negative 3/2. Negative becomes plus 3 over 2 times 2 on the bottom, so we have over 4. And then this is x. Negative 3/2 minus 1 is negative 5 over 2, like that. Okay, you think you are done, but no, not yet. Bring the x down to the denominator and then work out the simplification. So you get negative 1 over 4, and this is x to the 3 over 2 power, and plus 3 over 4, and this is x to the 5 over 2. power. Can we get some common denominator and clean things up? Yeah. Well, this is 3/2. If I can get 5/2, this is the same as saying x to the 2 over 2, which is just x to the first power. But I'll put down as x to the 2 over 2. That's all we need, right? Well, all in all, you get 4x to the 5/2. And I didn't write it as a radical for the answer choices. We'll just keep the answer like this. And this right here is negative x plus 3. And I believe that is it. And I even have the, well, I didn't have the right order, but I'll put down 3 minus x, which is the same thing. Okay? So of course, perhaps I just write yes, 3 minus x over 4x 5 over 2 power, like this. Good. Man, this is so computational, like for the derivatives, they are just so computational. You have to do a lot of algebra. And I don't know why I was trying to come up with the questions, right? I said, maybe the question is too easy, so I make it harder. So I was just having like 100 first derivative. So let me make it harder. Let me put in some implicit differentiation. I did. Let me put in some second derivative. I did. Let me put in some definition of derivative. I did. Man, okay, number 33. Here we go. dx. And we are going to have, I'm in my dream, d2 over dx2. Right? Here we have inverse sine of x squared. Oh my goodness. Inverse sine of x squared. Of course, here is everybody's note, right? Everybody's favorite note. Okay, to differentiate inverse sine x. This right here is 1 over square root of 1 minus x squared. And maybe you guys can use the chance to kind of Google it to see if I did it right or not. But just help me out if you can tell me if it's right or not. Anyway, it's not funny, I know. Okay, here we go. Here is the input. But you see, I will actually just write down dx. Okay, because I'm doing one derivative already. Inverse sine, I get 1 over, open the square root, right? Open the square root and then the 1 minus the input and you square. The input is x squared, but you have to square this again, like that. Are we done? No, we still have to use the chain rule. Multiply by the derivative inside. Derivative of x squared is 2x. So that's what we have. Okay? Man, we have to differentiate what now? Differentiating 2x over square root of 1 minus x to the 4th power. Man, quotient rule. Put down the denominator, square that. So we have square root of 1 minus x to the 4th power, and we square that. Bottom function, put it on the top, which is square root of 1 minus x to the 4th power, times the derivative of the top. Derivative of 2x is just a 2. And then we minus the top function, which is 2x. And we multiply by the derivative of the bottom. It's a square root, so we first have 1 over 2 square root. I'll have a 1, keep that in mind. 1 over 2 square root of the inside, which is 1 minus x to the 4th power. But don't forget, the chain rule says we have to multiply by the derivative of the top of the inside. Derivative of negative 1 minus x to the 4th power, we get negative 4x to the 3rd power, like this. Okay? Just like that. Okay? Cancel. Yes. But complex fraction, we have this guy in the denominator on the top. No good. So let's multiply the top and bottom by the square root of 1 minus x to the 4th power. Okay? Yeah. All right, so multiply, and these are gone already, the square and the square root, so they are gone already. So let's see what we have. Okay, square root, they cancel when they multiply. So you have 1 minus x to the fourth power, but you have to multiply by 2. So you actually get 2 times the inside, which is 2. 2 times that is minus 2x to the fourth power. Okay? And then, let's see, this and that cancel out as well. Okay, 2 cancel out with this 2. Yeah? And negative times negative is positive. 4. And x to the fourth power. Yes. Over. How did I write the answer key? Okay, I have the third power. Okay. So this right here, I put it as the first power. So I write it 1 minus x to the fourth power to the first power. This right here, I wrote it as 1 minus x to the, sorry, this should have been a 4. This and that should be the same. So 1 minus x to the fourth power in the square root. So this right here is 1 minus x to the fourth power to the 1/2 power. Okay? On the top, we can reduce that. 2 minus, no, plus, this and that together, we can get 2x to the fourth power over, now, for the bottom, they have the same base. Just add the exponent, so we get 1 minus x to the fourth power to the 3/2 power. But I changed that to a square root form. So I will just give you guys a square root answer, which is right here. You have the over 2. That becomes the radical, the square root. So in the end, 2x to the fourth power over. This right here will give us a square root. And we have 1 minus x to the fourth power, parentheses that, and raise that to the third power. That's the answer. This is the answer. That's it. Number 34. d2 dx2 of 1 over 1 plus cosine x, like this. Quotient rule or not? No quotient rule. Good. Okay. Let's rewrite this as a negative power first. Let's put it here. d2 dx2. We can write it as 1 plus cosine x to the negative 1 power, like this. So let's do the first derivative. Oh man, I forgot to do the first derivative in blue over there. I'm sorry, but no, it's okay. I'll do the first derivative in blue right here. The inside here will be the first derivative. Right here, I will first bring the negative 1 to the front and then minus 1. So we get negative, parentheses, the inside stays the same, which is 1 plus cosine x to the negative 2 power. And then we multiply by the derivative inside, which is negative sine x. That's the derivative of the inside, like that. Right? Can we clean things up? Yes. We have d dx. Negative negative becomes positive, positive sine x, over 1 plus cosine x raised to the second power, like this. Now, we really have to do the quotient rule. You might want to do the product rule right here, but depends. So here we go. I will just give myself more space. Square the denominator. So let me put this down. 1 plus cosine x squared, but we will have to raise that to the second power. Put down the denominator right here, which is 1 plus cosine x squared. Don't forget it's a square. Times the derivative of the top, derivative of sinx cosine, and then minus the top function, which is sine x, times the derivative of the bottom. This right here, bring the power to the front, so we multiply by 2, parentheses, 1 plus cosine x to the first power, and then multiply by the derivative inside, which will give us negative sine x, like that. Oh man, let's see. Let's see, how did I simplify that? I did simplify the top, so we have to simplify the top. Oh, actually, I see how to simplify the top. Here, you don't have to really multiply these things out because we see this and that can be factored out. So we'll do that first. Can you see the factor tonight? Can you see the factor tonight? Okay, right here we have the first power, right? So we have 1 plus cosine x. But don't forget we still have this cosine x. Good. This is out. Negative times negative is positive. So plus, just emphasize, plus. You have the 2, and then you have the sine square x, like that. Yes. Good. Over. This guy is 1 plus cosine x to the fourth power only. Now, this and that can be cancelled. We have 3 more left. And that's pretty much it. On the top, we just distribute this, and that's cosine square, and this is 2 sine square, so we cannot combine anything. So finally, cosine x plus cosine square x plus 2 sine square x all over this guy, which is 1 plus cosine x to the third power. And then we are done. This right here is the answer. Why did I make the question so hard? All right, that's 34. Right, that's 34. Okay, 35. Question number 35. Second derivative, x times the inverse tangent of x. Go ahead and do it. dx. Put this down in blue though. First function, which is x, times the derivative of the second. That will give us 1 over 1 plus x squared. And we add the second function, which is inverse tangent, times the derivative of the first, which is just a 1. So that's what we have. Nothing too special. All right, now we have to differentiate. This right here, well, we can just put the x on the top, but we haven't taken the derivative for another time, so we just put the x on the top. And then this is just the inverse tangent of x. Well, just clean up. So this is the first derivative. Now, just do it. For the first one, let's use the quotient rule. So, square the bottom. So we will have 1 plus x squared, and we square that. Then, the bottom function goes to the top. 1 plus x squared times the derivative of the top. And then minus the top function, which is x, times the derivative of the bottom, which is going to give us 2x. And then we add the derivative of inverse tangent, which is 1 over 1 plus x squared, like this. Now, we are going to do some like little engineering, that kind of thing. Not so much though, it's just like, look at this part, look at that part, combine like terms. Okay, I see that. This right here is just 1 plus x squared times 1, just that, minus this times that is just 2x squared. That's good. But perhaps let's get some common denominator. So I will multiply this by 1 plus x squared and also 1 plus x squared. Well, thankfully this is just plus, so we can just add everybody on the top. So this is just u plus 1 times this is just 1, just all that. So that's pretty nice. Let's see what we get at the end. Parentheses 1 plus x squared, and then square that for the bottom. Check this out. X squared, 2x squared, and then minus 2x squared. Oh my god. Cancel this out. And on the top, we just have to do 1 plus 1. I think it's 2. Yeah. So that's the answer, I believe. Let me know if I get this right or not. So, oh my god, that simplifies pretty nicely, huh? Number 36. Number 36. We have second derivative of x to the fourth power natural log of x. Just like this. Here we go. Okay, for the first one, we have to use the product rule, right? So perhaps it's already done here. dx, parentheses, product rule in action. Keep the first function. Let me see what's the next one. Yeah, let's just first function, x4 times the derivative of the second, which is 1 over x. And derivative second. I'm not editing this video, Steve. Okay. Plus. Natural log of x times the derivative of the first, which is 4x to the third power, like this. Okay, good. Now, of course, this right here is just 3x, x to the third power, right? So, all in all, we are looking at to differentiate this guy together will be simplified into x to the third power, and this guy, oh my god, plus 4x cubed times natural log of x. Derivative again, why not? Derivative of this guy is 3x squared, and we add the derivative of this guy. This is the first function, 4x to the third power times the derivative of this, right? 1 over x. Plus the second function, which is natural log of x, times the derivative of this guy, which is 12x squared, like this. Okay, of course, this part, again, we can nicely simplify it. So it's just 2. 3 plus 4 is 7, and x squared, right? So this is 7x squared. Put the 12x squared first, so 12x squared, and then we have the natural log of x. And that's it. Nothing else. Nothing else. Nothing else. Yeah. Be really careful though, if you look at my equation number 36. There's no typo, but I just make a small change for the answer key. So, haha. If you are taking AP test, let me know. You know how the AP test, the multiple choice questions are. They are really tricky because the answer choices are very, very similar. Okay, 37. d2 dx2 e raised to the negative x squared power. One of my favorite function. Here we go. We have to differentiate the first derivative. And for the first derivative, we have this right here stays, which is just e to the negative x squared. But Chendu says we have to multiply by the derivative inside. The derivative of that is negative 2x, like this. Right? So all in all, we just have to differentiate. Let me just write it down again. Just have to differentiate negative 2x times e to the negative x squared. So let's do it. First function, you keep it, times the derivative of the second. Derivative of this is e to the negative x squared, and we multiply by the derivative of that because of the Chendu. So the derivative of that is negative 2x. I don't even know if I'm saying derivative correctly or not, but whatever. Anyway, we add the second function, which is e to the negative x squared, times the derivative of the first, which is negative 2. All right, finally, we clean things up. This and that give us 4x squared and e to the negative x squared, and this is minus 2 e to the negative x squared. And some people may want me to factor, oh, actually, I did factor that myself too, so I will factor it out because this right here can be factored in. So we will have parentheses 4x squared minus 2 and e to the negative x squared, like this. This is preferred if you need to set this equal to 0 and find the critical numbers. So, oh man, I cannot say this is it, but this is it for number 37. Man, this is... Okay, number 38 and 39, I will do them side by side. So here is number 38. So d2 dx2. For the first one, we have cosine of natural log of x. And in fact, you can do the integral of this. You can also do the integral of that, not just the derivative. And then I will do the 39 on the side. This is d2 over dx2, natural log of cosine of x, like this. Okay, we have two derivative equations on the spot. They look similar, but of course they're also very different. Let's look at this one first. Okay, differentiating. Well, we have to get the first derivative right here. Derivative of cosine of something. First, we get negative sine, and the input stays the same. And then what? We have to do the chain rule, the derivative of the inside, which is 1 over x. So I'll put on the over x like this. Yeah? Over x. Now, differentiate that guy. Quotient rule. Okay, here we go. Square the bottom, which is x, and we square that. X, and then we square that. And I will put down the bottom function right here times the derivative of the top. This is negative, so I will just keep that as negative. And then we have the derivative of sine. Do that, you get cosine. And the input stays the same again. But we have to multiply by the derivative of the inside right here, which is going to give us 1 over x. So that's it for the first part. Then we subtract the top function, and the top function has negative, so you write down negative sine of natural log of x. Okay? This is the top function. And then we multiply by the derivative of the bottom, and the derivative of x is just 1. So that's what we have. And check this out. X, and then this is over x. So this and that cancel out very nicely. And you will see that this is negative cosine of natural log of x, and negative times negative is positive sine of natural log of x all over x squared. All over x squared. And on the answer key, I put down the sign first because I put on sign over that, but I will leave that to you guys. Okay, so just do that. Now, for this one, here we go. Let's get the first derivative right here. Inside, I'll do that in blue. This time though, you have to remember, when you differentiate natural log, you first do 1 over whatever this is, which is cosine x. And then the chain rule says, multiply by the derivative of the inside. Derivative of cosine x is what? Yes, negative sine x, like this. Good. So, check this out. This is going to be just to take the derivative of negative sine x over cosine x. This right here is nicely equal to tangent x. Well, the derivative of negative tangent x is negative. You have secant square x. That's it. Which one did you guys like more? You see, you just switch the order of the input and the the inner function and the outer function. Say. Oh my god, that was number 39. I don't have to do like 2 derivatives for 1 question again. Man, good. Number 40. Here we go. This is a very good one. dx. I need more space. Negative secant square x. Number 40. dx. ddx is just one derivative, okay? Square root of 1 minus x squared, and we add x times inverse sine of x. Here we go. Just one derivative of the square root, we get 1 over 2 square root of the bottom, or of the inside like this, on the bottom, like that, right? And we multiply by the derivative of the inside. So we multiply by negative 2x. That's it for the first derivative for this part. And then we add. This part requires the product rule. That's why I have the dot. Keep the first function times the derivative of the second. Derivative inverse sine is 1 over square root of 1 minus x squared. Similar. And then we add the second function, which is inverse sine of x times the derivative of x. That's the first function. Now, check this out. Cancel, cancel. So if you write this down again, you will see this is negative x over, this is square root of 1 minus x squared. But here is plus x over square root of 1 minus x squared. And of course, don't forget, lastly, you have that inverse friend, right? Inverse sine of x, like that. Of course, this and that can be nicely cancelled out. Finally, you just have your inverse friend, inverse sine of x, like this, plus c. No, you don't have to. This is it. In Calc 2, you guys will have to know how to do this backwards. The derivative what will give you inverse sine. I'm not asking you what's the derivative inverse sine. I'm asking you the derivative what, which is this, will give you inverse sine. Integration by parts. I don't know who are watching the videos. My intention is, of course, for the students who are in Calc 1 and Calc 2, especially for the very last few questions, or maybe you haven't done calculus for a while and you are going to do like Calc 3 maybe, especially in the summer. If you just want to practice, you should do this. Maybe you are AP Calc students, just do it. Or maybe you're just like me, who just like derivative calculus and all that. Yeah, number 41. Okay, just one derivative, we're going to differentiate x square root of 4 minus x squared. Okay? No, just kidding. I'm not like in DC. All right, product rule in action. This is x times, so here we go, x times square root function, so we get 1 over, well, just do it. The derivative of this right here, put it in red, 1 over 2 square root of 4 minus x squared. However, use the chain rule, multiply by the derivative of the inside, and that will give us negative 2x. That's the first part. Then we add the second function, which is square root of 4 minus x squared times the derivative of the first, which is just a nice 1. Well, this 2 and that 2 can be cancelled. That's good. And we see that x times negative x, that's negative x squared over, this is square root of 4 minus x squared. And we have this part, which is plus 4 minus, let me do it on this, 4 minus x squared in the square root, right? Okay, imagine that you had to find the derivative and you have to set the derivative equal to 0 so you can find the critical numbers. Well, this is not what you preferred. If you need to find if the function is increasing or decreasing or not, this is not the formula you prefer. You want to add them together. With that said, we have to get the common denominator. So let me just multiply the second one by that, which is square root of 4 minus x squared on the bottom and also on the top, like this. And when we do that, you will see on the bottom is just square root of 4 minus x squared. On the top here is negative x squared, and this times that is just plus, and the square root just gone. We have 4 minus x squared, like this. So all in all, you get 4 right here. Minus x squared, so that's minus 2x squared over square root of 4 minus x squared. Like that. Good. Nice and cute, huh? Another done. 42. Okay, another square root. Differentiating square root of x squared minus 1 and over x. Here, we will be using the quotient rule. So it's kind of like the other opposite. Anyway, go ahead and square the denominator and put down the bottom function right here. Multiply by the derivative of the top. The derivative of the top is going to be 1 over 2 square root of x squared minus 1. X squared minus 1. And then don't forget the chain rule. Use the chain rule. Multiply by the derivative inside, which is 2x. And then minus the top function, which is square root of x squared minus 1, times the derivative of the bottom. So that's what we have. On the top though, again, 2 and 2 cancel out nicely, and we have x squared. But we have a complex fraction in this situation. So to handle that, let's multiply the top and bottom by the common denominator, which is just this. So multiply by square root of x squared minus 1, square root of x squared minus 1. And when we do that, on the top, this and that will cancel. We have x times x, which is x squared. And then this is going to be minus this and that, the square root will be out. So you just have a parentheses, and you will have x squared minus 1, like that. I haven't distributed, so yeah. And over, here you have x squared, and you have the square root of x squared minus 1. Now, x squared minus x squared is just bye-bye. Negative, negative is just positive 1, so we have 1 over this guy. X squared, square root of x squared minus 1. Like this. Okay? I'm going to fit number 43 right here. I switched the order. Why did I do that? That's interesting. I just switched the order of the x over that. So okay. dx. So this one I have x on the top instead, over square root of x squared minus 1. Let's see how the answer will turn out to be, okay? Okay, quotient rule in action. So here we will have to square the denominator, which is this one now. So put that denominator on the top right here first, multiply by the derivative of the top, which is 1, minus the top function, times the derivative of the bottom. And the derivative of the bottom is 1 over 2 square root of x squared minus 1, and chain rule, multiply by 2x. Cancel, cancel, right? That's cancel. That's out already. Good. However, this time though, again, get a common denominator. Multiply this guy. Get rid of the complex fraction. So multiply the top and bottom by square root of x squared minus 1. Let's see what this will give us. This times that will just have that, namely x squared minus 1. This times this part, this and that cancel, so we have minus x squared over here. This and that cancel, which is like saying x squared minus 1 to the first power. This right here is like saying x squared minus 1 to the 1/2 power. This and that cancel. On the top, we have negative 1, right? Over this right here, I believe I put in the radical form for the answer. And I did. So let's do this in our head. 1 plus 1/2 is 3/2. So the half is the square root. And inside, x squared minus 1 to the third power, like this. That's it. Number 44. I'm going to fit number 44 right here as well. Let's see. We are going to be differentiating. This one is a fun one. We have cosine of inverse sinx, like that. Okay, here we go. What's the derivative of cosine? Well, it's just negative sine, isn't it? And the input stays the same, so you just write it. Inverse sine of x, like this. However, chain rule, right? Multiply by the derivative inside, which is 1 over square root of 1 minus x squared, just like that. Well, sine of inverse sine, they pretty much cancel. You can just put it down like this. So you have negative x over this for the denominator. Wow, all the answers look kind of similar to each other, all the square root and all that stuff. Very nice, very nice, very nice. Okay? And I'm also going to fit in 45 here because this one is not bad at all. d dx, natural log of x squared plus 3x plus 5. So this is the input, and we have natural log, right, on the outside. So remember, it's 1 over the input, which is x squared plus 3x plus 5. And the chain rule says what? Multiply by the derivative of the inside. Keep in mind, it's 1 over that times the derivative inside. We can just put the derivative on the top. So here we get 2x plus 3. Done. Done. Man, I can do the natural log derivative like this all day long. Give me 1,000 of them. I will do it for you in 5 hours. No, don't do it. Don't give me 1,000. No, don't take it too seriously. That was me saying whatever. I don't know. Okay, what was that? Aha, number 46 now. That doesn't look like a 6. dx. This one is a tricky one. Inverse tangent of 4x. But we raise that to the second power like this. Okay? Here is the deal. Do not multiply this and say that's tangent negative 2. Okay? I would just say don't ever write. Seriously, don't ever write things like tangent negative 2 right here, 4x like this. Don't. If you want to say tangent, the regular one, tangent, and then raise to the negative 2 power, put that to the outside of the parentheses. Okay? This means you have the inverse tangent of 4x and then you square that. Okay? Don't ever write this. Seriously, just don't. I have a video on that. You guys can go check that out. That's like the worst notation. Anyway, here we go. What we do is do the outside, which is the power situation. Here we have 2 parentheses, the inside stays to the first power, and then multiply by the derivative of the inside. Derivative of inverse tangent is 1 over 1 plus the input square right here, right? So we have to have the 4x here, but don't forget we square that. Are we done? No. Chain rule. Multiply by the derivative of this, which is multiplied by 4 right there. Now, put the answers together. All in all, 2 times 1 times 4, which is 8. And then this is also on the top, so we have the inverse tangent. Do not bring that down to the denominator. This is the arctangent, the inverse tangent. So you just write it down like this. Over this right here is 1 plus 4 squared is 16, and then you have the x squared. This is like a really cool expression, huh? Okay. All right, number 47. We are going to be differentiating. Oops, here we have a cube root function, but cube root of x to the second power, like this. Do we do any chain rules? You don't have to. Here is how you do it. You just have to differentiate. Remember, whenever you have the index here for the radical, you can write that as a power. So you actually get x. This 2 is right here, and then over 3 for that. Seriously. Then we can use the power rule or the power rule. Power rule, I don't know. Anyway, here we go. We get 2/3 x. 2/3 minus 1 is negative 1/3, like this. And I rewrite it. I brought this down to the denominator, so we get 2 over 3x to the 1/3, which is the same as cube root of x. Okay? X to the 1/3, just like that. Good. All right, number 48. Another interesting one, d dx. Here we have sine of square root of x times natural log of x. Woohoo! My question is, can we find the derivative of some function that will give us this for the answer? Namely, find the integral for that. I don't know. Anyway, here we go. Sine is our outside function. Both of them are inside. It's not sinx times square root of x times natural log of x. No. Sine is the outside function times this two inside. So what we do is differentiating that's the answer. Differentiate sine first, which will get cosine, and the input stays the same, square root of x times natural log of x like this. And then multiply by the derivative of the inside. Okay, we need the product rule in action, so we will do that. Derivative of the inside will keep the first function, which is square root of x, times the derivative of the second, which is 1 of x, plus the second function, which is natural log of x, times the derivative of the first, which is 1 over 2 square root of x, like that. And now we just have to simplify this expression. I almost wanted to say sharplify, but like, that doesn't even make sense. Anyway, let's see. Well, square root of x over x, we can simplify that to be just square root of x in the denominator. So I think I will just write this down again. Cosine of square root of x and natural log of x. Again, this is just 1 over square root of x, right? Yeah. You can do whatever you want to simplify that. This is x to 1/2 power over x to the first power. 1/2 minus 1 is negative 1/2, so you have this, okay? Plus natural log of x over that, 2 square root of x. So this is, hope it's clear now. We just need a 2 right here. Multiply, multiply. So finally, the answer is, did I put that on the top as well? I certainly did. And I will do that as well. I put on this first though. The denominator is this, which is 2 square root of x. And for some reason I put on this first. I think because I just want to tell you guys this is the only thing inside of the cosine. So let me emphasize that by putting 2 plus natural log of x first, times cosine of square root of x, natural log of x, like that. So this is the input for cosine. In fact, in differential equation, you will see this kind of function, cosine of square root of x times natural log of x, all that stuff. Okay, so that's good. Number 49. An easy one, the dx of CSC. Not really though, but like, you just have to do it carefully, it will be easy. It's actually pretty easy actually. CSC, cosecant of x squared. So here we go. Differentiating cosecant, we get negative cosecant cotangent. So CSC, but don't forget the input has to stay the same. Cotangent. And then do what? Well, chain rule, derivative of the inside, 2x. In the end, put the 2x all the way in the front. Negative 2x times all that. CSC x squared, COT x squared. Done. Whoa, look at that. How easy that was, right? Number 50. I cannot fit in number 50. I will fit in number 50 right here. As I said, I like to fit in a lot of things onto one board or one scratch paper. That feeling is really good. Okay, that feeling is just really, really good. It makes me really satisfied. I know some of you guys are like me too. I think so. Anyway, here we go. Quotient rule. So, square the bottom function, natural log of x, square that guy. Bottom function is natural log of x times the derivative of the top. The derivative of the top is 2x. And then minus the top function, which is x squared minus 1, times the derivative of the bottom, which is 1 over x. Just like that. Well, you can distribute it, but you are going to get complex fractions. So let's just multiply the top and bottom by x. So we can reduce that, right? We can simplify that a little bit. In the end, x times this guy of course, we will get 2x squared, and then we have the natural log of x, like that. And then this and that cancel, so you can just distribute the negative nicely. So we have minus x squared and plus 1, plus 1. All over x parentheses natural log of x squared. Done. Okay. Oh, by the way, for the people who don't know, on Wolfgang alpha, when they say, okay, on Wolfgang alpha, when they use log, okay, they mean natural log. Okay. So if you are doing your calculus problems on Wolfgang alpha, get used to this notation. Anyway, that was number 50. Oh my god, halfway done. So it's going to take me about 6 hours something. And I'm afraid of the last 10 questions because, to be honest, they are the definition questions. So I don't know how long they will take. God, man, this is taking longer than I expect. I don't know. Hopefully, they have some easy questions coming up. Yes, I am having some nice questions coming up. Number 51. Differentiating tan to the x. Now you have two ways to do it. One way is just know how to differentiate any number, okay, for the base raised to the x power. In that case, if you remember that, it's just tanx, 10 to the x power, times natural log of 10. It's just always the number to the x power times natural log of the base. And of course, you can check the chain rule. The derivative of x is just 1, so multiply by 1. It's the same thing. This is the idea. And the reason why this is true is because we can look at the tan as the follow. Remember, ideally speaking, we like to work with space e. So we can look at the tan as e to the base, e to the ln 10. This is 10, okay? And of course, this right here multiply, well, raised to the x power, and you can multiply the powers, and you will get the dx. This is e to the x times natural log of 10, like this. And you see, it's very similar to the question we did. This right here, you just get e to the x ln 10 times, now we have to do the chain rule. The derivative of x ln 10. ln 10 is a number times x, so you just keep multiply by ln 10 like this. And this right here is just 10 to the x power. That's how you get the ln 10. Okay, like that. Okay, number 52. Number 52. Number 52, your order is ready. Please come to the window and pick up your order. I don't know why I'm saying things like that, but whatever, I just did. So we have this. Yeah. Okay, so this right here, it's a cube root. Maybe we are not familiar with a cube root, but it's okay. We can write that as the 1/3 power. So we will do that. Therefore, we are just going to differentiate. Actually, I will. I'll just do it here. We'll differentiate. Inside is x plus natural log of x to the second power, and then we raise this guy to the 1/3 power. Well, power rule in action. Put this all the way in the front, and then -1. So we see this is going to give us 1/3 parentheses inside stays the same. X plus natural log of x squared. What's 1/3 minus 1? Negative 2/3. So you just have negative 2/3 here, and you multiply by the derivative inside. Okay, yes, two things, so be sure you open the parentheses. Derivative of x is 1 plus the derivative of this. Well, we need to use the power again. Bring the power to the front, which is 2. Inside stays the same. 2 minus 1 is 1. But chain rule says we have to multiply by the derivative of this guy just to this though. Because this guy has the derivative right here. So do not close the parentheses. Do not multiply 1 over x with the whole thing. the 1 over x, which is the derivative of natural log of x, it's only for this part. So you have to close the parentheses like this, right? And how do I write the answer? This is not... Oh, okay. We have to bring this down to the denominator and just do the usual clean up because we'll end up with a complex fraction. And I should have more space here. Okay, here we go. This right here is on the top, so I will put it on the top. 1 plus 2 natural log of x times 1 over x. Right? Just bear with me right here for now. Over 3 in the bottom, on the bottom, and this guy also on the bottom. Negative, right? The 3, it's the cube root, so we have the cube root. Open that, and this right here, x plus natural log of x. This right here has a square, but don't forget we still have this square here. So perhaps I will make this 2 red, and I will square this guy red like this. Well, as I said, we have the 1 over x here. Let me multiply by the x in the front this time, because if I put it at the end, it looks like it's itself the square root. I mean the cube root, but it's not. Anyway, multiplying, we get x. That cancels, so we just get plus 2 natural log of x, right? And 3x. So you guys are okay, huh? 3x, and then the cube root of x plus natural log of x. This guy square, and then this guy, the inside guy, square as well. So this right here is the answer for that. Okay, pretty good. As long as it's not like second derivative. Man, now I don't know why I did that. Okay, number 53. Ooh, very nice. Just some little power function. Okay, power functions. So we have d dx x to the 3 over 4 power minus 2x to the 1 over 4 power. This right here is actually pretty common if you have to talk about how to sketch a curve, because you actually get some sharp turn and all that stuff. So yeah, just know how to differentiate this and how to find a critical number for this. Anyway, go ahead, bring this to the front, minus 1, minus 1. Okay? We have done this question very similar. We have done the question very similar to this. So anyway, we get 3 over 4 x to the 3 over 4 minus 1 is negative 1 over 4. Okay, negative 2 times 1 over 4, we get negative 1/2. And then x to the subtract, you get negative 3 over 4, like this. Okay, bring things down to the denominator. So here we have 3 over 4, and this is x to the positive 1 over 4 power minus 1 over 2, and this is x to the 3 over 4 power. How can we get the common denominator? Well, here I need to multiply by 2, so I can get a 4. But here I need to multiply by x to the 2 over 4. So I can get x to the 3 over 4. I know that's the same as x to 1/2. So, don't worry, I will fix that. I think it's better this way though. Anyway, when you do that, the bottom has the denominator being just 4x to the 3 over 4. And then for the top, this is 3. This guy is x to the 1/2, namely square root of x. Okay? And then minus 2, like that. And of course, I put down the bottom as a radical as well, so I'll just write it 3 square root of 2. Why am I keep using my finger to erase? Okay, 3 square root of x minus 2 over 4x to the 4 over 3 power, which is the 4th root of x to the 3rd power, like that. Derivative for this part. Oh, Log base 2 for the next one. Log base 2, log base 2, log base 2. Okay, shouldn't be so bad because we know our log properties. Anyway, here we are going to differentiate. Here is the log base 2. And we have x times square root of 1 plus x squared, like that. But I don't know how to take the log base 2 derivative. It's okay, it's similar to this. We can use log properties to take up that. In the log world, we like to work with natural log, namely ln. So here is how we can do it. We have d dx, okay? For log base 2, what we can do is just go ahead and do log. We'll just change this to ln. Just change this to ln, and then here we have the inside states like this: x square root of, and this is a multiplication, 1 plus x squared, like that. But you see, this is the little 2. That means you just have to divide it by natural log of 2, like this. Okay? So again, natural log of whatever divided by natural log of this number is log of base of this number of the input, like that. Okay? So log properties. Let me just put it down under the clock. This is log base b of x. Okay? This is equal to log of x. Well, any log works, but we're talking about natural log of x over natural log of b. And it's just the input is right here. It's slightly more complicated, but get used to it. Okay, now let's do this down. Now let's put this down right here. We have natural log of 2. It's just a number. And don't let this bother us too much. So let me bring that all the way in the front. That's 1 over natural log of 2, like this. Okay? And we are going to differentiate. We're going to differentiate. Well, here if you look at the part in black, we have natural log of x times natural log of square root, right? Product itself and natural log, you can break them apart. It becomes a sum of natural log. So we can write this as natural log of x, stop, and close that, and then plus the other natural log, and this part, square root of 1 plus x squared, like this. Okay? And of course, the reason to do so is because this way you don't have to use the product rule. And that's how you can actually prove the product rule as well, thanks to logarithm. Even better though, when you have the square root, again, this is the same as saying the 1/2 power, isn't it? So let me just change that. Okay, again, look at the square root right here. We look at it as the 1/2 power. We can bring the power to the front whenever we have a natural log, but do not minus 1. This right here has nothing to do with derivative. This right here is just a natural log property. So all in all, we will have to differentiate. Here is the natural log in the front, and then differentiate natural log of x and the 1/2 in the front, and the natural log of 1 plus x squared, like this. Enough algebra. Here comes the derivative. 1 over natural log of x. 1 over natural log of 2. Sorry, 1 over ln 2. Let's put down parentheses for the result of the differentiation. The derivative of natural log of x is 1 over x. Done. For this part. Plus 1/2. It's a constant multiple. You just keep it. And then differentiate this part. So we have 1 over the inside, which is 1 plus x squared, right, inside. But the chain rule says multiply by the derivative right here, which is 2x. And that's it. We can cancel this out. So that's pretty good. But I think I combined the fractions. I did. So take a look right here. This is pretty much it. But I just combined the fractions. And to do so, of course, we can just multiply this right here by this denominator, 1 plus x squared. And of course, do it on the top as well. And for this one, we need the x on the bottom as well. So we multiply the bottom by x, the top by x as well. So all in all, you will see the bottom. How did I write the answer? I put the natural log of 2 all the way at the end, right? So I put natural log of 2 at the end. I put down x first. So I put down x. And then 1 plus x squared. And then here is the natural log of 2. Okay, and then we just have to work out the top. 1 times this is just the inside. This is just 1 plus x squared plus x squared. So we have 1 plus 2x squared. 1 plus 2x squared. That's it, right? 1 plus 2x squared. Yeah. I see the answer on the answer key, so I'm good with my work, and I'm also good with the answer key. Pretty good. Take a look, take a look, take a look. I feel like I write bigger when I'm doing derivative than integrals. I don't know. If you guys find my videos helpful, let me know. Thank you, I appreciate that. You can simply let me know by press the like button. That would really help the video. Thank you so much though. Yeah. I'm having fun to do this as well. And most importantly, hopefully you guys do this on your own first and then check out the video. That's the main part, right? Okay, number 55, right here. Differentiating. Here on the top we have x minus 1 over x squared minus x plus 1. 3 terms on the bottom, but this is okay. This is still a quotient rule situation. So go ahead, do the quotient rule. Parentheses, square the denominator, x squared minus x plus 1, square that. And then on the top, man, I hope it's not so bad. On the top, we have to just keep the denominator and multiply by the function, the derivative of the top function, and then minus the top function, which is x minus 1 times the derivative of the bottom. The derivative of x squared is 2x, the derivative of minus x is minus 1, the derivative of plus 1 is 0. So that's what we have. Now, let's see. On the bottom, we have this x squared minus x plus 1 squared. I think I'm still writing okay. I don't know. Anyway, on the top, you have this times that, which is just x squared minus x plus 1. But we have to FOIL this out. So let me just keep the minus in red right here, and then I'll open the parentheses. X times this is, just do this in, x times 2x is 2x squared. Huh? And then this is minus x, and then this is minus 2x, and this is plus 1. Okay? And again, let's see. And we are going to finish this right now. We'll do the computations in our head. Well, actually, I'll still write things down for you guys. Well, okay, let's do it. X squared minus 2x squared is negative x squared. Okay? Next, negative x plus x is 0, but negative 2x is plus 2x. All right? Lastly, 1 minus 1 is 0, so we're done. So that's it, I believe. And yeah, that's it for the answer. And I left it like this and the answer choices as well. So that's it. Ooh, number 56. We have to not integrate. We have to differentiate 1/3, and we have cosine to the third power x, and minus cosine x 来 that? Well, keep in mind, this right here is cosine x to the third power, right? Cosine x and then to the third power. So perhaps I will just make it clear for you guys right here. We will look at this as cosine x to the third power right here, okay? So here we go. Differentiating this, you bring the 3 to the front and then minus 1. 3 times 1/3 is gone. Just 1 actually. So we have the inside, which is cosine x, but this time it's to the second power. And multiply by the derivative inside, which is going to give us negative sinx. And we are done for the first part, okay? And then here we have to minus the derivative of cosine x is negative sin x. So that's what we have. And now check this out. Here we have cosine, and let's put on the square right here. And this is negative sin x, like that, right? Negative sin x. And then we have the plus sin x, like this. Let's factor out the sin x to see what happens. When we do that, we have sin x, right? This and that, we factored it out to the front, so we have the sin x all the way in the front. Well, here we have negative cosine square x plus, this is out, but don't forget, we still have the 1 right here. Everybody knows, well actually, everybody knows 1 minus cosine square x is equal to sin square x. But I know negative cosine square x plus 1 will give you sin square x as well. 1 minus cosine square. So therefore, sin x times sin square x, all in all, we end up with sin to the third power x. And with that, we are done, but you guys don't see the equal sign. So let me write it down. Better for you guys. Okay, you see the equal sign, I'm happier. Okay, 56, now 57. Ooh, okay. E to the x times cosine x. Right? Here we go. E to the x cosine x. Again, you just keep it. Right? Just keep the e to the whatever. Then you multiply by the derivative of the inside, pretty much is this part, the exponent part. Multiply, here we go, product rule in action. First function, x, multiply by the derivative second, which is negative sin x, multiply by negative sin x. Add the second function, which is cosine x, times the derivative first, which is 1. I put on the answer before I tell you guys. That's pretty much it. What else did I do? No, that's pretty much it. Nothing too much we can do. So this right here, you just have to know how to write down the derivatives. And this right here is negative x sin x. And plus cosine x, like this. And with that, we are done. Okay, 58. This is done already. Number 50. Oh my god, this sheet is done actually. This sheet is done. 2 more sheets, but like this is the part that I'm afraid of. Okay, this is the part I'm afraid of. To be honest with you guys. Number 58. Anyway, ddx of x. And we have minus square root of x times x plus square root of x, like that. Well, do we need to use the product rule? No, because you can do the algebra. You can multiply this out yourself first. And better yet, check this out, this right here. This is a minus b times a plus b in that form, right? So the result is just a squared minus b squared. Namely, we'll get x squared minus square root of x squared, which is just x. So we just have to differentiate this instead. In another word, we can just say the answer is 2x minus 1. Done! Okay, next one, 59. We are going to be differentiating inverse cotangent of 1 over x, like this. Ah, man, I'm going to just see, I have to think about how to save space. 59, differentiating inverse cotangent of 1 over x, like that. Oh my god, what's the derivative of inverse cotangent? Don't worry, it's just negative 1 over 1 plus x squared, right? But you have to be careful of the input. Here we go. Derivative of inverse cotangent, you get negative 1 over 1 plus the input being squared. So here, 1 over x, and you square that. It's very similar to the inverse tangent. For the inverse cotangent, it's a negative right here. But don't forget we have to multiply by the derivative of the inside. Derivative of 1 over x. Well, it's like saying x to the negative 1. Bring the negative 1 to the front, you have negative 1. And negative 1 minus 1 is negative 2 for the exponent. X to the negative 2 is the same as saying over x squared, like that. And in fact, this also happens a lot. You should remember it. The derivative of 1 over x is this. You can put that down right away. That's pretty much it. We'll simplify, shall we? Negative times negative is positive. This right here, 10 equal, this should put down parentheses. Here we get 1 plus, this is 1 over x squared. But you see, this x squared is going to be multiplying with that on the bottom. So all in all, you actually just end up with 1 over this times that is x squared plus this times that is, of course, just plus 1. Hey, does this look familiar? Of course, this is the same as saying 1 over 1 plus x squared. But didn't I say this is the derivative of something? Inverse tangent, huh? Yes, in fact, this right here is the derivative of inverse tangent of x. Well, here's a question for you. When the derivative of a function is equal to the derivative of another function, does that mean that the functions are equal to each other? In this particular case, this is in fact the same as that. But in many cases, the functions might be off by a constant. Check out my other video for more detailed explanation, right? But in this particular case, inverse tangent of x, in fact, you can write it as cotangent, inverse cotangent of, you can write this as inverse cotangent of 1 over x. I will prove this for you guys another time. Waiting for my 100 trig identity or maybe trig problems that you have to know. Anyway, number 60. So anyway, number 60. Okay. I don't know if I can fit in here. Let's see. This is a long one. I will put it down here, maybe. Put it down here. Number 60. d dx x times inverse tangent of x. And we are going to minus natural log square root of x squared plus 1. Right? So just like that. But don't we see a square root? Yes, we do. So I'm going to write this as the 1/2 power. You guys know. So this right here, we are going to change that to the 1/2 power. But this is instead of the natural log. So can we put the 1/2 in the front? Yes, right? So all in all, I'm going to just rewrite this as minus 1/2 natural log of x squared plus 1. Okay? So they are the same. Now, let's get to work. Well, this part we need the product rule. So keep the first function times the derivative of the second. Derivative of this is 1 over 1 plus x squared. Right? And then we add the second function, which is the inverse tangent of x. Oh, sorry. We keep the second function. I should write down this part in black. We keep the second function times the derivative of the first, which is just going to give us 1. Now, for this part, we have to minus. This is a constant multiple, so we can just write it down. And then the derivative natural log of something is just 1 over of whatever this is, so x squared plus 1. But we are going to multiply by, because of chain rule, the 2x right here. Okay, so hopefully you guys can still see this. Yeah, that's pretty much it. 2 cancel. Now check this out. All the way in the front, we have x over 1 plus x squared. Next, we have this guy, which is inverse tangent of x. Lastly, we have minus x over x squared plus 1. What can we do? Yes, cancel, cancel. And we just get inverse tangent for the answer. Very, very, very nice. Very, very, very nice. Of course, this does not happen by accident. I set this up. The question is, can you go backwards? Can you find the derivative of what function will give you inverse tangent? Well, you just did. The derivative of this will give you inverse tangent. That's in Cal 2, so don't worry. So know all this. Let's see if I can fit number 61 right here. No, I cannot. So I will do the other one. Let's see. So you will see why I cannot fit number 61. Man, after this video, I will really have to think like twice or maybe 3 times to see if I ever want to do 100 differential equations. Because that's just, man, I don't know. Well, shout out to Arctan, right? Arctan, because he did 200 integrals in one take, 9.5 hours. Okay, go check out his video. I will also have his the link to his video in the description. He did it via a live stream. It's, I don't know. Wow, I'm speechless. Wow. Okay. Yeah, I enjoyed that video a lot though, because that video gave me that made me feel like how you guys are feeling right now. Like when you watch me like doing like 100 integrals, 100 derivatives. Like, yeah. So shout out to Arctan. I pretty much pronounced your name wrong. I'm so sorry. Arctan. I think Arctan. Yeah. Okay. Here we go. Number 61. Differentiating, and we have x square root of 1 minus x squared over 2, and plus inverse sine, man, of x over 2, like that. Let me write down the question better. X square root of 1 minus x squared over 2, plus inverse sine of x over 2, like this. Okay, first thing first, both of them have the over 2. Do not use quotient rule though, because over 2 is just a constant multiple. Perhaps it's better if we put the 1 over 2 all the way in the front. You know, that way it doesn't bother us too much. So that we can look at x times square root of 1 minus x squared, and then plus inverse sine of x. I think this right here looks slightly less intimidating. Yeah, I don't want you guys to feel like, oh man, I just made the question worse. Anyway, here we go. Put down the 1/2 all the way in the front, open the parentheses for the result of differentiation. Here is the deal. We have to use the product rule. Keep the first function, which is x, times the derivative of the second. The derivative of this is 1 over 2 square root of 1 minus x squared. But you guys all know the deal. We have to multiply by the derivative of the inside, which that will give us negative 2x. It's 1 times negative 2x. So this time I will just start to put down the negative 2x on the top. Save some space this way. Right? So that's the first part, and then we have to add the second function, which is square root of 1 minus x squared, and we multiply by the derivative of the first, which is just going to give us 1, like that. And then this one is just going to give us 1 over square root of 1 minus x squared. That's the derivative of inverse sine x. Now the question is, now what? It seems that we have to get some common denominator again. So we will get the common denominator, isn't it? So cancel this out first though. Right here, let's just multiply the bottom and the top by 1 minus x squared. I'll also multiply it right here. Okay? So we will see the answer right here is, well, the result is so far 1 over 2 times, here we have x squared. Well, everybody has a square root of 1 minus x squared for the denominator. So let's put that down. This guy has negative x squared. This guy we add, and just put down, let's just put on this guy, different color. This guy has negative x squared. First guy. Next guy plus. This times that is just 1 minus x squared, right? 1 minus x squared. Lastly, we have to add, this guy is just 1, so we have to add 1. That's about all. Now what though? Well, 1/2. Well, we can put the things down together already, so we will. Okay, here's the equal sign. Okay, here we go. 2 times this is 2 times the square root of 1 minus x squared. 1 plus 1 is 2. This times that is negative 2x squared. Okay, let's simplify a little bit. Of course, we can factor out the 2 and all that. So reduce the 2, so we get 1 minus x squared over square root of 1 minus x squared. Right? Just reduce the 2, just factor out the 2's, cancel out, okay? What can we do with this? This and that have the same base. This is to the first power over, this is to the 1/2 power. 1 minus 1/2 is 1/2, positive though. So you end up with square root of 1 minus x squared. Very good, huh? Yeah. In fact, this is another calculus 2 question. Can you find derivative what function will give you 1 minus square root of 1 minus x squared as the answer? I'll just do it here. 62, I want to have more space. dx. Here we have sinx minus cosx over sinx plus cosx, like this. Quotient rule in action. Go ahead and square the denominator. So we will square the denominator, sinx plus cosx, and here is the square of the denominator. Okay, the red pen is kind of like tired. Okay, so we'll see. Anyway, on the top, put this on the top. So this right here, we have parentheses sinx plus cosx, and then we have to multiply by the derivative of the top. Derivative of sine is cosx, and the derivative of negative sinx is positive sinx. Negative cosine will give you positive sine. Okay, so this is what we have. Then we minus the top function, which is sinx minus cosx, then times the derivative of the bottom. Derivative this is cosine. Derivative this is negative sine. So we have minus sinx right here. Wow. Whoa, man. Crazy looking expression, huh? Okay, let's calm down and we shall be able to, not really. I want to cancel things out. Let me just double check to see if I have it. Of course, you cannot just say I want to cancel things out without really making out the top one. Okay, I guess we really have to multiply things out because on the top, unfortunately, we cannot factor anything. If you switch this, it becomes positive. That's not, cannot really factor. I was thinking about to factor with difference of two squares, but you know what? Let's just deal with this. Let's just multiply things out. So here we go, sine times cosine, right? So sinx, cosx, and then sinx, so plus. I know this is just sine plus cosine square. I should have done that, but too late. And then this times this is plus cosine square x, and then lastly plus sine x times cosine x, yeah? So sine x cosine x, okay? Okay, now minus, multiply this out, we have sine cosine. This times that is minus sine square x. And then, I know I should have just used the binomial theorem. I seriously should have done that. Plus sine cosine, yeah? This is sine cosine. Can we see okay? Yes. Okay, so this is what we have. And all over the denominator, I will just write it down like this. Okay, I want to show you guys all the legitimate work. Okay, now have fun to simplify these guys. This guy is just 1. Okay, negative, negative. This right here is going to give us negative 1. All right? Oh, check this out. Check this out. Check this out. Sine x, cosine x. So that's 2 of them. Cancel, cancel. So just imagine this will cancel with that. This will cancel with that. In the end, we're just doing 1 plus 1 on the top. So altogether, we have 2 on the top. Very nice. Over this guy for the denominator. So I just put it down slightly more compact so that it does not look that intimidating. I believe that's the answer. And I do have that as the answer choice. That means I did it right. I know the answer, even though I didn't write it down. I know what the answer is. There's a nice pattern. I don't know if you guys figured it out already. You can leave a comment down below. And also leave a timestamp so I know you guys are watching this part. Number 63. Differentiating 4x squared times 2x third power minus 5x squared. Okay. It's a product, but should we use product rule? No, because we can do the product in the algebra world first. So let's go ahead, just do the good old days. Distribute. So 8 x squared times x to the third power, you add the powers, so x to the fifth power. This times that is minus 20, and you add the powers again, so x to the 4. Now we can just do the power rule right here. Nicely, easily. Do not do the power rule right here and right there. Let me show you. You see, this is the right way to do it. And you get 40 x to the fourth power. This is negative 80 x to the third power. With that, you are done. Okay, with this right here, you are done. Do not, right? This right here, do not just say, hey, this right here should give you 8x because that's the derivative of this. And then say, hey, this right here, the derivative of this is like 6x squared minus 10x. Don't do this because you can see that when you multiply this and that, this is not that. Right? This is not that. This is not correct. You can also do the product rule, but the product rule is, of course, much harder. It's not needed. It's not like super hard. It's just there's no need for it. Okay, so take a look. And as people often say, differentiation is like a mechanical work, right? So it's not hard. You can always just differentiate whatever you want. But the good differentiation are the ones you have to actually come up with nicely, like the ones that can actually simplify and has like some really compact answer, some really nice answer and all that. Anyway, 64 dx. We have square root of x times 4 minus x squared. We will do what we just did. Multiply, and then just use the power rule, okay? So, again, you can look at this right here as x to the 1/2 power. So let me just write it down, x to the 1/2 power. So we are just multiplying, so we still have to keep the ddx. X to the 1/2 times that is just 4x to the 1/2, and minus this times that, 2 plus 1/2 is 5/2. So we have x to the 5/2, like this. Now, power rule. The good old power rule, right? Okay, 1/2 times 4 is 2. And then this is x to the negative 1/2. Here, bring the 5/2 in the front. And minus 1, we get x to the positive 3/2, like this. Okay, this should go down to the denominator, so we will put it down in the denominator. This is 2 over x to the 1/2 power, and this is minus 5/2, and this right here is on the top, so x to the 3/2 power. Can we get some common denominator right here? And yeah, I combine the fractions again. So let's see. This right here needs this 2, so multiply the 2 right here and right here. This right here needs the x to the 1/2 power, so we multiply this right here, x to the 1/2 power, x to the 1/2 power. Okay, 2 times 2, 4, minus 5, x to the 3/2 times x to the 1/2. Multiply, you get x to the 4/2, which is just 2, right? For the power, x squared. Over 2, and x to the 1/2 power is just square root of x. Just like that. That's it. Okay, number 65. Differentiating square root of 1 plus x over 1 minus x, like this. Okay, here is the deal. Some people may tell you, hey, you can just code that to be y, and then take the natural log on both sides, and you can use the natural log property to reduce the right-hand side. You can do that. That's not that bad. But this is also not that bad if you just do it. So just do it, like Nike, okay? So here we go. To do this, 1/2 square root of the inside. You literally just write it down, 1 plus x over 1 minus x. And we have to multiply by the derivative of the inside, which requires the quotient rule. Multiply by, let's square the bottom. So parentheses with 1 minus x inside, square that. Bottom function here times the derivative of the top. Derivative of this right here is just 1, the inside function wise, okay? And then minus the top function, which is 1 plus x, times the derivative of the bottom, which is negative 1, like that. Told you it's not so bad. Now, check this out. This is what I will do. This right here, it's the same as saying square root of 1 plus x over square root of 1 minus x. I can bring this up. So we get square root of 1 minus x. Bring this up. And then like this, and then okay. And then divided by 2, square root of 1 plus x. Okay? And right here, let's see how we can simplify this. Here we have parentheses 1 minus x squared. On the top here though, this is just 1 minus x. And negative times negative makes it positive, so we have to just add 1, add x. Negative x, positive x cancel. 1 plus 1 is 2. Cancel. Finally, we can put this together. On the top, we have square root of 1 minus x over, let's put this down first. You can reduce more, but man, did I do that? I didn't do it for the answer key. Did I do that? Yeah, I didn't do that, but I could have done that. But like, I don't know, this and that we can have reduced it more, but up to you though. Anyway, that's okay. So 1 over that, so I will have this, and then it was 1 plus x. I will reduce it, and I'll change it on my answer key because I feel that's better here. Anyway, this is like 1 minus x to the second power, right? But as I said, we'll reduce this a little bit because they have the same base. Okay, so this right here is the 1/2 power, and this is like 4 over 2 power. Okay, so when you reduce, of course, you'll end up with 3/2 power right here on the bottom. So all in all, you have 1 over this right here, square root of 1 plus x times square root. You get 3/2 power, so you have 1 minus x in the square root, and you raise that to the third power right here. Okay, so I will change that right here. I'll change that. On the answer key, I just had this, but I think I should do it like that. Okay, same base, just reduce it. All right, number 66. This is a really fun one. I will be able to fill in this right here. Number 66, differentiating sine of sinhx. Sometimes you can do a lot of them, but 2 of them is okay. Anyway, here we go. Start from the outside. Derivative of sine is cosine. Okay, derivative of sine is cosine. And the input, you keep it. You just keep it. Okay, you keep it. But the chain rule says you have to multiply by the derivative of the inside. Derivative of sine x is cosine, and you have the x. And if you look at the inside right here, the derivative of x is just 1. So multiply by 1 doesn't really matter. The truth is, you are always using the chain rule, but sometimes the chain rule does not matter. And on the answer choice, I put down this first. So cosine x times cosine of sine of x. So we put sine into cosine for this part, and then this is just cosine x multiplying with them. 4 hours. Okay, number 67. Okay. dx 1 plus e to the 2x over 1 minus e to the 2x. Yeah. Okay, of course, quotient rule in action. So here we go. Square the denominator before we forget. So 1 minus e to the 2x like this, and square that. And then we put down the bottom function right here, which is 1 minus e to the 2x. Right? This is the bottom function times the derivative of the top. Derivative 1 is 0. Derivative e to the 2x, you write down e to the 2x first, but you multiply by the derivative of 2x. Chain rule says so. So multiply by 2. Then we just minus the top function, which is 1 plus e to the 2x. And then multiply by the derivative of the bottom. Derivative of 1 is 0, but derivative negative, so this is still negative. And you have e to the 2x stays like this. And then you multiply by the derivative 2x, which is the 2, like that. Okay. Now let's see if we can simplify this nicely or not. Right, take 2e to the 2x, multiply in, okay? So multiply this into the parentheses. This times that, we get 2e2x. And then this times that is negative 2e, and you add the exponents, so you have 4x for the exponent. So that's that part. Then negative times negative is positive, so be careful with it. So we do this, and also in the meantime we do this. So negative together become positive. So this is 2e2x times positive 1. So this is plus, okay? Plus 2e to the 2x. 2e to the 2x. And then positive times that is also positive. So you have 2 plus. This is again plus 2 e to the 2x times e to the 2x is e to the 4x, just like what we did over there. And you have some nice cancellation that's about to happen right here and here. Cancel them out. And we can also combine things, right? This and that can be combined. So all in all, 4e to the 2x. And you're adding, so you keep the e to the 2x term. You just do the coefficient, the 2 times 2. The 2 plus 2 is 4. And then the bottom is parentheses 1 minus e to the 2x square. And we are done for that one. Okay, I'm going to fit in 68 right here. Believe it or not. I believe myself. I hope. d dx x over 1 plus natural log of x. Another quotient rule example. Okay, I will do it right here, otherwise I will be running out of space. So square the denominator, so we have 1 plus natural log of x, and we square that. And we put the bottom function up, which is 1 plus natural log of x, multiplied by the derivative of the top, which is just 1, minus the top function, which is x, times the derivative of the bottom, which is just 0, and then plus 1 over x, so it's just 1 over x, like this. This right here is, of course, just minus 1, so you will see this right here is just 1 plus natural log of x, and then this is, again, as I said, minus 1 over this guy. So this is a very nice question, because in the end, 1 minus 1 is 0. We end up with ln x over 1 plus ln x squared, like that. And with that, we are done. I have a question just now. How can I integrate this and then get back to that? That's a pretty nice question. Maybe do some use substitution. This is a hard one. I will go back to this and then do the derivative right here. Okay, so this is number 68. All right, here we go. The next question. All right, this is an extreme fun one, right? Not because of the number, but rather the actual question, okay? X raised to the x over natural log of x power, like this. Let me tell you, the answer to this right here is x to the x over natural log of x power. And we are done. Wow, what is happening? How can you have the derivative equals to the function itself? There's only one function that can make this happen. And yes, this is e to the x. This is how we do it. Look at the base. Remember, we have x. This is the function. And this power is also a function. Ideally speaking, we want to work with base e. So we do this. This is d dx. This x right here, that's right here as e to the natural log of x, right? And then we raise that to the x over, I know, you see it now, huh? Right? Because now, when you multiply the powers, the natural log of x will cancel. So in the end, you just have to differentiate e to the x power. Right? The natural log of x will cancel. We just have to differentiate e to the x. And of course, e to the x will give you e to the x for the derivative. And of course, for this particular question, let me just write it as x to the x over 1, x to the x over natural log of x, just for fun, for that crazy looking expression. Okay, hopefully nobody gets too mad on this one. Number 70. Let's see. Differentiating natural log, and we have a square root. Right? So this is a natural log, and the input is the square root. And inside here we have x squared minus 1 over x squared plus 1, like this. All right? Shall we do some algebra first to simplify? Yes, we totally should. So I will do the algebra right here. d dx. As you all know, this right here is the 1/2 power. And now this time, let's just do a lot of the algebra in our head, okay? 1/2 power can be bring to the front. And the natural log of a quotient can be split into a subtraction. So first you will have 1/2 natural log of this input, x squared minus 1. And then 1/2 times the other one. So we have minus 1/2 natural log of the bottom, which is x squared plus 1, like this. All right, so let's just do the derivative now. 1/2 is a constant multiple, so just keep it right here. And the derivative of ln of something is just 1 over that thing, right? So 1 over x squared minus 1, but we multiply by the derivative inside, which is 2x, the chain rule says so. And right here, minus 1/2. Again, 1 over the derivative, this is x squared plus 1 in the denominator, multiplied by the derivative inside, which is 2x, like that. And check this out. This and that cancel, this and that cancel, and we just have this minus that. So I will just write this down for you guys. This right here is x over x squared minus 1, and minus x over x squared plus 1. Well, if you want to combine the fractions, which we will, let's just multiply this one by x squared plus 1 on the bottom and also on the top. And multiply this one right here by x squared minus 1 on the bottom and also on the top. Now, let's see. I will have the space right here. Let's see. Both of them have the same denominator. This is a minus b times a plus b, difference of two squares. If you multiply out this and that, we end up with x to the 4th power minus 1. All right? And the top wise, you see this right here is x to the 3rd power. Let's put it down in black. That in red. X squared times x squared is x to the 3rd power plus x minus parentheses this times that. Let's just distribute so it becomes easier. Minus x times that, which is negative x cubed, and then minus x times negative 1 becomes plus x. Yeah, so plus x. In the end, once x to the 3rd power minus x to the 3rd power can be cancelled, x plus x is 2x over x to the 4th power minus 1. We are done. So it's a very nice one. So it's kind of similar to number 65, but this one you do have the natural log already, so that's what it's meant to be, right? 71. Okay, so this question aren't so bad. It's just that I put like some second derivative and also implicit differentiation earlier. That's like, oh man. Anyway, inverse tangent of 2x plus 3. Here we go. Inverse tangent, you get 1 over 1 plus, and you have to square the input right here, right? So put down 2x plus 3, and we square that. And what else do we have to do? Yes, chain rule. Multiply by the derivative of the inside. Multiply by this 2. Okay, so now let's see what we get. On the top, we have 2, of course. On the bottom, this is the 1 plus. Let's square this out. Binomial, right? So this is 2x squared, so it's 4x squared. Right? 2x, you square that. You also square the 2, so it's 4x squared. And then the next term is plus 2 times this times that. 2 times 2x is 4x times 3 is plus 12x. And lastly, you add 3 squared, which is plus 9. So it's just like that. On the bottom, 1 plus 9, we can do that. So on the top, we have 2 over. So again, 1 plus 9. So here we have 4x squared plus 12x plus 10. Let's put a 2 in the middle. It looks better this way. Reduce, reduce, reduce. We can factor out the 2 and reduce it. So you see, if we factor out the 2, it becomes 2x squared plus 6x plus 5. And then we can reduce this and that. Very nice. In the end, the answer is 1 over 2x squared plus 6x plus 5. And with that, we are done. Okay, cotangent to the fourth power of 2x. Number 72. I don't think we need too much space for this one. So number 72. Differentiating, as I said it, cotangent to the fourth power of 2x. Right? Okay, here we go. Look at this right here as cotangent of 2x and then to the fourth power. So perhaps I'll just write it down right here. Cotangent of 2x, like this, and then to the fourth power. Okay, here we go. Put the power to the front, minus 1. Okay? All right, so we get 4. And the first part is cotangent of 2x to the third power. And then the chain rule says multiply by the derivative of this. Derivative cotangent is negative cosecant square, and we keep the same input like that. But the chain rule of the chain rule says we have to multiply by the derivative 2x, which is 2. Multiply by 2. So it's technically like this, if you like. This is a 2. Because this whole thing is a derivative inside. That's why I put a red parentheses like that. If you put it right here, it's fine too. It doesn't really matter that much anyway. Finally, we have the answer. 2 times 4, and then that's negative. So we have negative 8. This right here, cotangent third power 2x, and then cosecant square of 2x. That's it. Complex fraction. Oh my god, complex fraction. Okay, that's 73 dx. And hopefully, you should do enough derivative equation so that you can get confidence. Like you can differentiate anything. This right here, we start off with a complex fraction, but do algebra first. Do algebra first so that our calculus life will be much easier. So right here, let's multiply the top and bottom by x. So that we'll see this right here is just d dx. On the top is x cubed over x plus 1. And now this is just a nice quotient rule question. So square the bottom. Let's put down parentheses with x plus 1 in the square that. And then the top, put down x plus 1 times the derivative of the top, which is going to give us 3x squared, and then minus the top function times the derivative of the bottom. Derivative of the bottom is just 1, so that's what we have. Cleaning things up a little bit, multiply this out, we get 3x cubed plus 3x squared, and then minus x cubed over parentheses x plus 1 to the second power. This and that can be combined. So we will, this is 2x cubed plus 3x squared. Hey, it's just the reverse. Cool, huh? This right here is x plus 1 to the second power. And with that, we are done. Not so bad, not so bad, not so bad. 3 more sheets. Oh my god. 20 something, I don't know, man. 28 questions. I have to look at this carefully because I just want to save paper, so the printout is like tiny. So this right here, 70. Let's see. I'll go under the. No, I will just erase. I will not be lazy. I will erase. I will erase. That's like, I will survive. I will survive. I don't know. Man, I remember, I heard that music, I will survive, when I was running marathon. I will survive. I will survive. I know, even though it's not meant to be like for like running or so, but like it's just, it fits like just say I will survive. I will survive. Number 74 right here. Differentiating d dx, e is e, x over 1 plus x squared power. So for this one, we just have to do the outside and then like the quotient rule and all that. So first, e to the whatever, the derivative for that is just e to that whatever. So e to the x over 1 plus x squared. Then multiply by the derivative right here. So multiply by, and we have to use the quotient rule. So we see that we have to square the denominator, which is 1 plus x squared, and square that. Multiply, well, on the top right now, we put on the bottom function 1 plus x squared, and multiply by the derivative of the top. Derivative x is 1, so multiply by 1, minus the top function, which is x, and multiply by the derivative of the bottom. Derivative of 1 is 0, derivative of x squared is 2x, so we just multiply by 2x. So that's pretty much it. Now we just have to clean things up like we always do. Just like I will have to clean my hand later on. So yeah. Anyway, here we go. This is just e to the x over 1 plus x squared. And how did I write that? Oh, I put that all the way on the top. Oh, it's okay, later. Anyway, put it like this right here. So this is 1 plus x squared, and square that. This right here is 1 plus x squared, and then minus this and that is 2x squared. So here is the answer. This is how I wrote it. I put this on the bottom only, so 1 plus x squared, and I put this on the top. So I actually had this first. E to the x over 1 plus x squared, okay? And then, of course, multiply by 1. This is going to give us negative x squared, and with that, we are done. Okay, just like that. Next one, number 75. d dx. Here we have parentheses with inverse sine of x inside, and then raised to the third power. Please, please, please do not put down sine with a negative 3 power right here. Okay? If you ever write sine negative 3 power like this, I don't know if you are saying this or are you trying to say sine x to the negative 3. We don't know. Don't do this. This is just so bad. I know this is the one that's the worst, but just don't do it like that. And for the regular calculus course and whatsoever, when you have this negative 1 right here, it means the arcsinh, okay? Anyway, here we go. Power rule first. Bring that to the front, minus 1. So we have 3 parentheses inverse sine of x raised to the positive 2. Okay? And then multiply by the derivative inside. Derivative inverse sine is 1 over square root of 1 minus x squared. I will just put that right here. Just like that. Okay? So with that, we are done. Number 76. Number 76. dx. I should start training for my marathon too, by the way. haven't started running. I have been going to the gym, but haven't been running yet. So my cardio needs work, right? And this minus natural log of parentheses secx, like that. Okay, good. So again, whenever you have the power right here, it's a good idea to write it as secx and then raise that to the second power. Anyway, here we go. Bring the power to the front, minus 1. 2 times 1/2 is just 1. So you have just this secant, okay, this secant x to the first power. So let me just emphasize, this right here is from here to the first power. And then we multiply by the derivative of the inside. Derivative secant x is secant x times tangent x. That's the first part. Then we work on this part. We minus, we did the derivative of this already, we minus this part. The derivative natural log of something is just 1 over of the inside, which is secant x. And again, we multiply by the derivative of the inside. Derivative secant x is secant x tangent x. Well, what's happening? Here we can cancel the secant x. That's nice. And perhaps right here we can do the following. This right here is, of course, secant square x. And we have the tangent x. And then minus, this right here is just tangent x. So that's good. And you see, both of them have tangent x. Let's factor it out. So again, this and that, we are going to factor it out. So that's in the front right here. And then we will end up with secant square x and then minus 1. What's secant square x minus 1? This right here is nicely equal to tangent square x. So all in all, we have tangent to the first power times tangent to the second power. So we will end up with tangent to the third power x. Very, very nice. Very, very nice. As I said, I've set out a lot of these questions so that they have some really nice simplifications. Otherwise, the derivatives, they aren't so much fun. Next one, this is a fun one. It's actually a rather famous one. Natural log of natural log of natural log of x. It's just a lot of people will do this kind of derivative question. Anyway, here we go. First natural log tells you you have to put down 1 over, this is the inside. You put it down in the denominator, which is natural log, and then natural log of x, right? And then the chain rule says, multiply by the derivative of the inside. This natural log says you have to do 1 over the inside, which is natural log of x. And then the chain rule says you have to multiply by the derivative of this. Derivative of natural log of x tells you you have to put the x in the denominator. Right? That was in the denominator, like that. So that's pretty much it. In the end, we just write things down nicely. 1 over this x goes first, and then natural log of just x goes next. And lastly, natural log of x, like that. So this is it. Dr. Payam also did a video on this guy. And this is the beginning of the Chengdu. So if you guys haven't seen the video, go check that out. Right? Ninja milk. Number 78. We are going to be differentiating pi to the third power. Please pause the video and give this a try first. Okay, good. The answer is equal to 3 pi squared. Easy, right? No! The answer to this is just equal to 0. Why? Pi is a constant. When you raise a constant to a third power, it's still a constant. When you do d dx of pi to a third power, you get 0 for it. That's it. If you do that, then you got tricked. And usually, this is a pretty tricky question for the AP. Well, I'm not sure about the AP test or like your AP class maybe. Your AP teacher might do this to you. Yeah, I did this to my students too, so I don't blame them. All right, number 79. I want to fit this right here. Okay. Oh my god. The ones I'm scared, they are coming. The hyperbolic, they are not so bad, but the definition, they are coming pretty soon. Actually, for this one, I'm going to erase. I'm going to erase. I'm going to erase. Oh. I will erase. I will erase. Okay. Restroom break. I'm going to just clean my hand at least one time. Like seriously, it's just bad. Just all the markers and all that stuff. So I will be back. Feel much better. I personally prefer chalk 10 years ago. Nowadays, of course, I use markers. But the downside is markers is really dirty. It's dirtier than chalks. If you have a bad one, of course. I mean, like, yeah, anyway. Okay, number 79. Here we go. Differentiating natural log of x plus square root of 1 plus x squared. I'm going to write this down better for you guys. Okay, so here we go. Maybe I shouldn't be using my hand to erase the board. That's why it's like my hand was so dirty. But anyway, here we go. This right here, do it carefully though. I mean it. First of all, natural log of something, tells us to do 1 over whatever the inside is, right? So just put down x plus square root of 1 plus x squared. So that's nice. Then we have to do the chandu. Now, as you can see, we have 2 terms, but you guys cannot see because the marker is not so good anymore. Change this to... For Monica, if you're watching, let me tell you, I have a pink pen as well. Check this out. But I'm not using it. I'm using a black pen, of course. Blackpenredpen, of course. Anyway, so it has 2 terms. So I'm going to open the parentheses. Hopefully it's better. And the derivative of x is 1. And we are going to add the derivative that it's not so clear. The derivative of square root is 1 over 2 square root of 1 plus x squared, like this, right? However, we have to multiply by the derivative of the inside for the square root of that part. So, in this case, a common mistake is that people just close the parentheses and they multiply by 2x and then they distribute. No. The derivative of this is you just multiply right next to this part. Okay? So this right here is for that derivative. And after we have that, close the parentheses and we'll see what we can do right here. Check this out. 2 and 2 cancel. That's nice. And right here, let's go ahead and combine the fractions. So when we do that, let me just multiply this guy by this, which is square root of 1 plus x squared. And of course, we do the same on the top, like that. And after we have done that, we will see this is 1 over x plus square root of 1 plus x squared. Okay? I feel like my handwriting is getting worse and worse. I'm sorry. 1 over x plus square root of 1 plus x squared. Slightly better, huh? Hopefully. And we multiply this by, check this out. The bottom here, they have square root of 1 plus x squared as the denominator. So just put that down one time. On the top, this times that is just square root of 1 plus x squared. Plus, this is just an x right here, right? So of course, you see that this part and this part, they should be in the parentheses. And the nice thing is that they are the same, even though the order, but the order of addition does not matter. Therefore, we can just cancel them out nicely. And in the end, we end up with the answer 1 over square root of 1 minus, so 1 plus x squared. This is it. Very nice, isn't it? Maybe easy, maybe you don't, but it's okay. Number 80, this is the time that I will explain it to you guys. Yes, this right here. From number 80 to number 90, it depends if you have covered the hyperbolic functions or not. If you haven't, you can skip this part. If you have, watch this part, of course. Anyway, differentiating sine with an h next to it. This is not sine and the h as a constant. This is called the hyperbolic sine, okay? And the input is x, like this. And to make it more fun, let's talk about the inverse hyperbolic sinx. Okay, the inverse hyperbolic sine of x. And again, this right here is the input, this right here is the name, and we want the inverse of it. So it's like that. And I'll tell you guys more about what the inverse and all that stuff is. Well, the truth is, this right here, the answer is that. Because you notice this right here, if you have the regular sign, sorry, let me just write it down right here. I'll do it, and I'll write it down. Okay, I have no idea what this is. Let me just say it like that. Okay? Well, how can I figure this out? 2 ways. First way, I can do the following. I can say that y equal to the inverse hyperbolic sinx, like that. Okay? And the reason I want to do this is because hopefully we know the regular hyperbolic sine better. Well, if so, we can just take the regular hyperbolic sine function on both sides and we will end up with this. And then we can do implicit differentiation. This is how you can figure out the derivative of inverse functions. Okay, when we do that, here is the deal. When we differentiate hyperbolic sine, we get hyperbolic cosine. So we have hyperbolic cosine, namely cosh. If you have a friend named Josh, you know, that's not cool enough. Cosh is better. And by the way, this is sinx. Anyway, this right here is what? Anyway, I'm sorry about Cosh and Josh. You know, Josh are cool as well, but you know, just in math only. Okay. Anyway, the derivative of hyperbolic sine is hyperbolic cosine, namely cosh, just as cool as just as cool as Josh. There we go. I don't know. Maybe if you are nearby and if your name is Josh, if I still have this, right, I'll offer you one of this. So it's in my office, okay? If you're watching my video, if your name is Josh, just bring your ID to my office. I will offer you one of the Ninja Milk, okay? Anyway, the derivative of this is that, but y is a function of x, so multiply by dy dx, isn't it? And on the right-hand side, the derivative of x is 1. Right? Implicit differentiation. So from here, the good thing is that you can see, let me put it right here, dy dx is equal to, of course we can divide cosh of y on both sides, so we end up with 1 over cosh of y, but here is the trouble. What is cosh of y? Again, if you are trying to differentiate this, and this is in terms of x, our answer should also be in terms of x as well. So this is what we can do. We are going to use identities. So let me just put down some note for you guys. Okay, for the hyperbolic trig functions, they are just on the hyperbola instead. And cosh is the x value and sinx is the y value. And we start with x squared minus y squared equals 1. Okay, you can check out my other video for more detailed explanation. But all in all, cosh square of anything, right? Let me just put down t for the input also, and then minus sinx square of t. This right here is equal to 1. So you can see that we can just put this onto the other side, and we get cosh square t is equal to 1 plus sinx square t, like this. And of course, you just take the square root on both sides, so we end up with cosh t, and you want this to be square root of 1 plus sinx t, like this. This is an identity. But here is the deal. Technically, when I take the square root on both sides, I should put down the plus minus. However, the way that we define the hyperbolic function is that we want cosh to be on the right-hand side, the hyperbola on the right-hand side. So if you look at x squared minus y squared equals 1, we just want the right-hand side. Namely, we just want x to be greater than or equal to 1. Okay? And again, cosh is the x value, sinx is the y value. That's why you have this identity right away. So in fact, you don't need a minus, just like that. Another thing you can see is cosh, the exponential definition, or the parametric way to define it, is e to the t plus e to the negative t over 2. So in fact, we are still dealing with like exponential function and all that. They aren't so bad. Anyway, so what am I talking about? Cosh of y is just equal to, let me just put it down here, okay? We want the x to be there. Okay, cosh of y, by this right here, we just want the square root of 1 minus sinx, so sinx square. There's a square right here. Sinx square of the same input, which is y, like that. And of course, we still have the 1 on the top, like this. I'm running out of space, man. This is not. Let me try it again. I'm sorry. 1 over square root of 1 minus sinx square of the same input, which is y, like that. Well, sinx of y is what? Sinx of y is x. Therefore, wait, hold on, this is a plus, man. Sorry. Cosh of y is square root of 1 plus sinx square of the same input. Okay? And what's sinx of y? Sinx of y is x. So all in all, we end up with 1 over square root of 1 plus x squared. Okay? So that's it. The answer to this is just 1 over square root of 1 plus x squared. Okay? And the truth is, okay, this right here, it's exactly the same as that. Okay, it's not off by a constant, it's exactly the same. And you can do that by doing some algebra for so, or you can check out the video for it. But anyway, they are exactly the same. So to differentiate this, if you have this version for it, you can just differentiate that, which we did it already. So this is it. And remember, let me just say, recall. Remember the regular version for the inverse sign. If you have the inverse sign, and this is the regular version, not the hyperbolic version of x for the input right here, you get 1 over square root of 1 minus x squared. And there's no typo. Earlier it was my bad, but this is it. Okay? You see, this is the minus, and here you have the plus when you have the hyperbolic version of it. Very cool, very cool, very cool. So when I do the 100 trig identities, perhaps I will just include some of the, what's that called? Hyperbolic trig identities as well. Anyway, number 80, that's the same as number 79 technically, was secretly. Number 81. For the rest, I will just kind of show you guys the things that you have to know along the way, okay? d dx, e to the x times sinhx, and this is the regular version, okay? Sinh of x. Well, cosh is this. Sinh is just a minus in between. And then the input is just x instead because we're using x. So to differentiate this right here, we can skip the product rule because this is e to the x. And again, for sinh of x, this right here is nicely equal to e to the x minus e to the negative x all over 2. So, of course, we can just distribute the e to the x first and do the algebra, and then we can just be happy, right? Okay, when we do that, let's put the 1 over 2 all the way in the front. And then we have the differentiation. We haven't differentiated yet. E to the x is e to the 2x. E to the x times e to the negative x is e to the 0. So just minus 1, like that. Now for this one, 1/2 all the way in the front. Differentiating e to the 2x is e to the 2x. But the chain rule says we have to multiply by the derivative of 2x, which is 2. And the derivative of minus 1 is 0, so it doesn't matter. 2 and 1/2 cancel each other out. So finally, the answer to this is nicely equal to just e to the 2x. Very good, huh? 82. Okay, hyperbolic secant of 1 over x. Oh my god. Hyperbolic secant, okay, of 1 over x. That looks like a, let me just write it down better. Hyperbolic, I don't want to have space. There we go, of x. No, it's 1 over x. Okay, like that. Well. Well, the truth is, I told you guys about cosh and sinx. We'll be using them along the way. This right here, yes, you are thinking, it's secant h and then tangent h, right? Kind of, but you're missing the negative sign. Let me show you. This right here, yes, you are thinking what exactly this is. This is exactly the same as 1 over cosh, okay? Hyperbolic secant is the same as hyperbolic cosine, 1 over hyperbolic cosine. And then the input stays the same right here, of course. Then we can write this to the negative 1 power. This is dx. Cosh of 1 over x, then raised to the negative 1 power. This means 1 over. This does not mean the inverse cosh, okay? So again, know your notations, all that. Right here, we can bring the negative 1 to the front, minus 1, and all that. So we have negative, parentheses, cosh of 1 over x to the negative 2 power right here. And then we have to multiply by the derivative of the inside. The derivative of cosine is negative sign, but the derivative of cosh is positive sinx. Okay? There's no typo. The derivative of cosh is sinx. And you still keep the input. And of course, we still have to do the chain rule right here. The derivative of 1 over x is negative 1 over x squared. This is the one I told you guys. You should know it by heart. Let me prove it to you guys real quick. When you differentiate cosh t, you differentiate this e to the t, which will still give you e to the t. Differentiating this, you get negative e to the negative t. Over 2 is still over 2. This right here is exactly that, which is exactly just sinx of x, right? Just if you use a different input, of course. Anyway, this is the idea. But of course, we simplify this a little bit. That's positive. This goes down to the denominator. This stays on top. So you have sinx of 1 over x. This right here is the same as saying cosh of 1 over x, right? Cosh of 1 over x. And another cosh of 1 over x. Yeah? And the reason I want to do that is because just like the good old days to prove the derivative of the secant, you see that right here. This is 1 over that, which is, by definition, the hyperbolic of the secant and of the input, which is 1 over x. This right here, yes, is the hyperbolic tangent. So you have the tangent. And the input is 1 over x. And with that, we are done. Very, very nice. Oh, I forgot the 1 over x. Oh, I forgot the x squared. I forgot this guy, the x squared. Okay? I forgot this guy. X squared right here. So we have to have the over. This x squared is still in the denominator. And with that, we are done for sure. All right, that's 82. Now, 83. Let's see, just for fun, I want to fit in here. 83. dx of cosh of natural log of x. This is not so bad because we can just put the natural log of x in here, and we can take care of business. Check this out. Do the algebra, ddx. So putting natural log of x again in here and here. So we end up with over 2 is still over 2 on the bottom. So let's put that down. And we have e to the natural log of x. So e to the natural log of x. And then for the other part, we have the plus e to the negative, okay, natural log of x, like this. Well, we can simplify this and just have to do it carefully. Because, for example, e to the natural log of x, they cancel out nicely. But this and that, it does not cancel nicely yet. You have to put the negative right here. So you end up with e to the natural log of x to the negative 1 power, and then cancel it out. You have to make sure this is right here is clean. It has to be just a positive 1, technically. So bring that to the front, so you have that. So we see this right here, it's actually just to have the 1 over 2 all the way in the front, and then ddx. First part is we just have to differentiate x. Second part, we have to add it with x to the negative 1 power. So this is all we are differentiating. So here we go, 1/2 all the way in the front. Put down the parentheses for the result of the derivative. The derivative of x with respect to x is 1. The derivative of this is -1 over x squared. And you can just get a common denominator real quick. In the end, we end up, let's see, 2x squared on the bottom, right? And then this is x squared minus 1 times 1 is still x squared minus 1, like that. Whoa, look at that. I told you this should be able to fit in there. Let's just take a look, take a look, take a look. Okay. Let me know if you guys like the hyperbolic trig function more or the regular trig function. And also let me know what kind of derivative I should be doing. Please do not ask me to do like x to the x to the x to the x to the x. I did them already actually. I actually should have done that, but like, yeah. Yes, I will be doing 100 limits. And I have a lot more ideas, but it also takes a lot of preparation and energy and also time. And yeah, so I'll try to see if I can do them as soon as possible. Number 84, I kid you not, I switched the natural log and also the cosh. You can see, okay? Yeah. So 84. dx of natural log of cosh of just x. All right, go cosh. Okay, here we go. Natural log of whatever, this one, we cannot do the algebra in the sense that do not write it as e to the x plus whatever, all that. Doesn't really help. Check this out though. Because we can actually just answer the question in the hyperbolic trig function world. The derivative natural log of something is just 1 over whatever that is, so just write that down. Then, take the derivative of the inside. Chen says so. Multiply by the derivative cosh is sinx, and it's positive, so just multiply by sinhx. Guess what? You're done. Because, actually, you're not done yet. You can write this as sinx of a cosh, which is tanhx, or hyperbolic tangent of x. That's it. The identities are similar, but they are not exactly the same, so be careful with that. Number 85. I'm not like super happy because I know the hard ones are coming. So yeah. Anyway, sinx, oh man. You have to make sure the h is not too far apart from the sin, otherwise it looks bad. 1 plus. We did this version, question number 2, okay, long time ago. But this is the hyperbolic version of the question. Here we go. Horrible, sorry. Okay, here we go. Square the denominator. So put a parentheses and then with 1 plus cosh x inside, right? Square that. And now on the top, you of course put on the denominator 1 plus cosh x times the derivative of the top. The derivative of sinhx is just cosh x. And then minus the top, which is sinhx, times the derivative of the bottom. The derivative of the cosh x is positive sinhx. So you just multiply by sinhx like this. Can we expect some kind of cancellations? Well, watch to find out. Here we continue. This times this times that, cosh of x. This times that, of course, we write it as cosh square, right? Just like the trig function, you put a square right here, of x. And then minus, this right here is sinx square x. All over, this right here, parentheses 1 plus cosh x and square that. Yes, very good. This right here, as I mentioned earlier, it's nicely equal to 1. And we just have 1 over 1 in that, right? So you see, I can put down the 1 right here first. And this feels like deja vu, but it's not exactly. Anyway, this is equal to, okay? This is equal sign, you can see now. Over this guy, parentheses 1 plus cosh x squared. Cancel this, cancel one of that. So finally, we get 1 over. Finally, we end up with just 1 over 1 plus cosh x right here. And we are done. Number 86. This is one of my favorite one. So we are going to differentiate. Okay. The derivative of secant is secant x times tangent x. But can you give me the derivative of what function will give you secant x? In fact, we saw it earlier, but we are going to see it again right here. Check this out. Differentiating inverse hyperbolic tangent, and this is the inverse hyperbolic tangent of cosine. Okay. In fact, I said it wrong. The derivative of cosecant is equal to negative cosecant times cotangent. But can you tell me the derivative of what will give us cosecant, or maybe a negative version of it? Watch to find out. Anyway. So this right here, I will just tell you guys what the deal is. Okay. In order to do this, okay, you will have to know the following. So here's some notes on the side. d dx of the inverse tangent, and this is a regular version. Okay. This is 1 over 1 plus x squared. Well, take a guess of what the derivative of the inverse hyperbolic tangent of x is. No, it's not a negative sign right here. That's inverse cotangent that will do the work. This right here, we get 1 over 1 minus x squared, like that. Very, very nice. So, same idea, but, just do the work right here. Same idea. Okay, so to differentiate inverse hyperbolic tangent, we have to have 1 over 1 minus. We will have to square this guy. So I will put a parentheses with cosine x and square that. This is cosine x, okay? And we multiply by the derivative of the inside, which is negative sinx. Now, check this out. This is just 1 over. This is 1 minus cosine square x. And perhaps I can put a negative sine x on the top like this, right? But what's this? We saw it earlier. This right here is just nicely equal to sine square x. Okay? This is just sine square x. 1 minus cosine square is 1. 1 minus cosine square is sine square. What's on the top? Sine x. So can we just cancel? Yeah. This is going to be negative 1 over sine x. In another word, we get negative cosecant x. So, in fact, if you want to find out the derivative of what will give you cosecant or secant, you can use the inverse hyperbolic tangent to help you out. Right? You can just have to think about what other things you have to do with this, so you can end up with the derivative being secant or cosecant, and maybe a negative version just multiplied by negative. Anyway, that's the answer for that. 87. Man, d dx. I haven't done any product rule and all that for the hyperbolic, huh? Don't worry, I am going to do it. X times inverse hyperbolic tangent of x and plus natural log of square root of 1 minus x squared, like this. Well, you guys all know the deal. This right here is the 1/2 power, so I put that all the way, not all the way, please right here, right? So I will just change that for you guys. 1/2 natural log of this guy. And now let's get to work. Here is the deal. Product rule right here. X times the derivative of the second. It's right here. So we multiply by 1 over 1 minus x squared. Chen says you have to multiply by 1, but you know you don't have to. 1 multiplied by 1 doesn't matter. And then you add second function, which is inverse hyperbolic tangent of x. And you multiply by the derivative of the first, which is just 1. So that's what we have. Now we add the derivative of this part. This is just 1/2 times the natural log will give you 1 over, and you put the inside in the denominator. And the chain rule says multiply by the derivative right here, which is negative 2x. Just like that. This and that. Again, cancel out. You guys will see why I say again. This right here, x over 1 minus x squared. This right here, plus inverse hyperbolic tangent of x. This right here is negative though, right? Negative, okay? So minus x over 1 minus x squared. This is positive, this is negative. Of course, they can say bye-bye to each other. Finally, we end up with the inverse hyperbolic tangent of x. And this right here is your nice answer. Very, very nice. Similar looking than the regular inverse tangent x. We did that earlier as well. Okay, I am going to do the next two side by side. Which one? You guys are seeing this right here, right? I'm going to do the next two side by side. So I will have to erase the board. And again, I'm not so happy because, well, I'm kind of happy because it's almost done, but like the hard ones are coming, so I'm not exactly like super happy. This is like, I don't know, whoever decides the course, they put like uphill at the finish line, and that's really mean, okay? I would rather have the uphill than the first 3 miles or so, and just have it done with it. Yeah. If you run, you know what I'm talking about. Anyway, number 88. I'll put it down right here. Okay, here we go. dx. We are going to be differentiating inverse sinx, okay? The first one right here is inverse sinx. And the input is tangent x, okay? I am going to just treat myself better. I would like to have a better marker right here, so I can feel the writing experience is better. So I will use this one. Much better, okay? So, number 88, dx. Inverse sinx of regular tangent x, like this. Yeah, hyperbolic together with the regular. So, you are going to see what's going to happen. And on the contrary, on the other hand, I'll say, number 89, we will differentiate the regular sine of hyperbolic tangent x. Ooh, what in the world is happening, huh? So again, I'm just looking at the questions. I just want to make sure that I wrote down the correct question. Now, start with this one. Here we go. Inverse sinx is 1 over square root of 1 plus, it's plus, okay? And then you put this right here, and you square that. So tangent square. And then what else do we do? Well, we write the, just let me write down the tangent x better. And what else do we do? We multiply by the derivative of the inside. Chen says so. Derivative of tangent x. This is a regular tangent x. We get regular secant square x. Okay? So it's just like that. Okay, this is good, but is there anything that we can simplify? Yes, because 1 plus tangent square, this right here is nicely equal to secant square as well. So you are looking at the square root of that, which is just a secant x in the denominator. All in all, you just have secant square x over secant to the first power x, right? After you take the square root and also the square, they cancel. And of course, we just try not to deal with the absolute value. Don't worry about it whenever these things happen. For now, if you want to be more technical, you have to look at the actual domain and also the x values that you are talking about. But for this one, just cancel it out. Yeah. Anyway, this and that, cancel one of them out, and you end up with what? Secant x. The derivative of this will actually give you secant x. We have seen the derivative of some function will give us secant x earlier as well. Okay? Like, I don't know how many hours ago, but yeah. Anyway, let's take a look at number 89. Take a guess what the answer is. Okay, we'll see. Okay, this is the regular inverse sign. So we get 1 over square root 1 minus. This right here, we have the parentheses with tangent, with the h. So it's a hyperbolic tangent, okay? X, and we square that. And we multiply by the derivative of the inside. Derivative of the hyperbolic tangent, yes, is the hyperbolic secant square x. That is true. You can prove that with whichever way that you want. But what is this? Yes, an identity. Yes. This right here, it's also the same as hyperbolic secant of x, but you have to make sure it's a minus. 1 minus tanhx square is actually inverse hyperbolic, is a hyperbolic secant x square, right? Square. And just like that, you take the square root. So you are looking at, on the top, hyperbolic secant square x over, on the bottom, is just to the first power. So hyperbolic secant of x. Cancel, cancel, this is 1, so you have hyperbolic secant of x. So cool, huh? You just put the h somewhere and you can get the h somewhere else too, like that. Very, very, very nice. Okay, the last multiple choice question. Let's see, I will put it down right here. 90 dx. Here we have the inverse hyperbolic tangent of x over 1 minus x squared, like that. Okay? Don't be too excited, we are not doing integral. You don't do substitution for this. But we'll do quotient rule for this. Okay, here we go. Right here, we square the denominator. Here we square the denominator. On the top, we put 1 minus x squared, the denominator right here, and then multiply by the derivative of the top function, which is 1 over 1 minus x squared, like that. And then we minus the top function, which is inverse hyperbolic tangent of x, times the derivative of the bottom, which is going to give us negative 2x. Okay? And again, this x is the only input for the inverse hyperbolic tangent. Well, this and that cancel nicely, so we don't have to worry about the complex fraction situation. We just have a 1 right here. Negative times negative, okay? So plus 2x, and this is the inverse hyperbolic tangent of x. And then on the bottom here, we have this guy, which is parentheses 1 minus x squared square. And with that, we are done. We are done with all the multiple choice questions. I'm not so happy, as I said. Even though I'm almost done, but like I know the hard part is coming, so I will have to calm down. I will have to make sure I can get ready for the next 10 questions. I don't know how long it will take. It's 5 hours only. It's not so bad. 5 hours and 40 minutes. I just saw the timer. But the good news is, last page. Okay, ladies and gentlemen, welcome to take the derivative with definitions. So number 91, right? So we are going to be differentiating ddx again, x to the third power. I know the answer, you know the answer, everybody knows the answer, but do you remember how to use the definition for the answer? No, you don't. Then watch out, okay? And you just have to make sure you follow direction. See, a lot of students, they lose points for this kind of questions on the exams because they don't follow direction. If the question say use the definition, you have to use the definition. Otherwise, you're not going to get any points, okay? Seriously. Don't be cute and say the answer is 3x to the second power. No. You have to show the work on the exams. So you have to remember, okay? You have to know that. And why do you need to know this? Well, that's how you can prove things with definitions. Anyway, here we go. This is the function. This is the input. The x is the input. Well, you take the limit as h goes to 0. And remember, the difference quotient is f of x plus h minus f of x all over h. So you put x plus h into x right here. So you open a parentheses with x plus h here, and you raise that to the third power, and then you minus this right here is just that. So it's x to the third power. And then you divide it by h like that. Okay? Now, you can just multiply this out. You can also try to factor it, but I think multiply is easier for this situation. You can actually use the difference of 2 cubes to factor it, but up to you. Anyway, you have to write down the limit as h approaching 0. And when you multiply this out, you just do it somewhere. I'll show you just to make sure that we know what we are doing. Okay? X plus h. X plus h, x plus h. So for the first two parts, of course, you just multiply this out. So you end up with x squared, and then you get xh plus another xh. So you have two of them, 2xh. And lastly, you have h squared, all right? And you have to multiply it one more time, so x plus h. So you do this times that, which is, okay, let's do this times that, which is x squared times x, which is x to the third power. And x squared times h, so it's plus x squared h. And then this times that is plus 2x squared h. And this times that is plus 2xh squared. I know the Pascal's triangle, I know the fast way, but I just want to show you guys all the work because I know not all the students know about this, okay? So, lastly, this times that is x times h squared, and then this times that is plus h to the third power, like that. All in all, we can collect like terms and put the result right here. So, when we do that, we'll see this right here is x to the third power, and let's see, this is x squared h, and we have two more. These two things can be combined. So all in all, we have 3 of them. So we plus 3x squared h. And we see that this and that are like terms. 2 plus 1 is against 3. So we put on plus 3 xh squared. And lastly, we have the plus h squared. No, h to the third power. Right here. This is the first part, right? And then we have to just minus x to the third power. And now, we'll just literally minus the x to the third power. That's good, huh? And as you can see, everybody on the top has an h. So you can factor it out, and good things are about to happen. So check this out. Here we have the limit as h approaching 0. Factor out the h, and we have 3x squared. And then factor out the h, we have plus 3xh. And then factor out the h, we have plus h squared. And then this is all over h. What can we do with the h's? Cancel them out. Cancel this out. Lastly, remember x. Okay, remember x is the variable. remember that we are taking a limit as h going to 0, so we just put 0 into all the h, the remaining h. And you see, when you cancel this h and that h, there's no more 0 over 0, so no nothing, okay? No worry. Okay? So you have 3x squared and plus 3x times putting 0 in here, and lastly you put on plus 0 squared. This is 0, that's 0. Yes, we get 3x squared. Okay? And we are done. This is actually not that bad. I know. Yeah. I wasn't going to do this in the first place. I know, I'm sure some of you guys are going to say, hey, where's the definition of derivative? Yeah, so I feel I have to. So, anyway, this right here is 3x squared. Let me see if I can fit in one more right here. Number 92. I'll give you guys another type of the question. This is another one that we did in the first couple questions. I'm not going to bother to look it up because I'm just going to finish this and I want to go home. Anyway, dx square root of 3x plus 1. Here is the input, which is x right here. So you are going to plug in x plus h in there and then do the rest. Anyway, take the limit as h going to 0, putting x plus h right here. So we have the square root 3 parentheses x plus h and then plus 1. And then minus that function, which is just square root of 3x plus 1. And everybody is divided by h right here, right? So my h is okay, yeah. I just want to make sure I'm okay. Now, we are going to just see how to simplify this kind of limit. To do so, when you have square roots, keep in mind, if you plug in 0 into h right now, you get 0 over 0. One way to simplify this kind of situation when we have square root is to multiply the top and bottom by the conjugate. So that's the usual strategy. So we will do so. So multiply the top and bottom by the conjugate, which is just this plus that. Square root of 3x plus h plus 1, and then plus square root of 3x plus 1. And then, of course, do the same thing on the bottom. So parentheses square root of 3x plus h plus 1 plus square root of, I like to keep my color consistent, and then the 3x plus 1, like that. Okay, here is the good news. To multiply out the top, it's not so bad because you are in the form of a minus b times a plus b. So this is going to give us the following. We still have the limit as h approaching 0. Well, on the top, we just have to do a squared minus b squared. A squared is just the inside. Well, in the meantime, let's also distribute that part. How's that? Actually, let me just keep it as how it is. 3 parentheses x plus h plus 1. Okay? A squared. And then minus b squared. Okay? B squared is just this thing square. And that's just going to give us the inside. And let's put parentheses because I will have to distribute the negative in a second. That's what we have, right? And for the bottom, just go ahead, write it down again. Because remember, the point of multiplying this conjugate is to fix the top. So just multiply out the top. And for the bottom, just leave it like this and wait for good thing to happen. So you will see the good thing will happen. This right now, let's just multiply it. We get 3x plus h, 3h, and then plus 1, and then plus square root of 3x plus 1. It actually doesn't matter if you multiply that or not, but whatever. Anyway, right here, here we go. This right here is 3x plus 3h plus 1 minus 3x minus 1, yeah? Can we reduce? Yes. You literally cancel the 3x, and also the 1 minus 1 is done, yeah? And now check this out. On the top, we have just 3h left over h times this quantity, this is a 3 times h. So we can just divide the h out. So we divide this out. Okay? Cool. So no more 0 over 0 situation. We just have that 3 on the top. And now we can just put a 0 into the remaining h, which is only this one here. Keep in mind, we still have this 3 right here, though. Okay? We still have this 3 right here. So this 3 right here. 3 over, well, I put in 0 into h. So we have square root of 3x plus 3 times 0 plus 1, and then plus square root of 3x plus 1, like this. Don't forget this 3. This is how you can show that you need a chain rule. You need a 3. In the end, of course, this right here is just 0, and you have 3x plus 1 inside here in the square root, and they are the same square root. So we can have 3 over 2 square root of 3x plus 1. And we are done. Okay? That's why you see we need a chain rule. We need to multiply by the derivative of the inside 3x plus 1, which is going to be the 3 right here on the top. Okay? Chain rule matters. Number 93. I need more space. No, not really. I'll see. I will try to fit in 93. It's seriously a lot of fun to just try to fit in a lot of like crazy computations and all that things. 2x plus 5 in the denominator. Anyway, here we go. Limit as h approaching 0. Here is the x. So I will put down x plus h in here. So we have 1 over 2 parentheses x plus h, and then plus 5, and then minus 1 over 2 x plus 5. And all over h, like this. Now, take the limit as h approaching 0. I cannot regret, but I will try to just deal with this. We are going to multiply the top and bottom by the LCD. Okay? So, yeah. I don't know if I have enough space. Okay, we have done a lot of LCD already, so let's not show work for this one, okay? So, I will just show you guys what we can do. Here is the deal. H on the bottom, H. You multiply the top and bottom by this and that, namely the LCD. And when you do that, you pretty much have parentheses with this, namely 2 parentheses x plus h plus 5. That's this denominator. And then you multiply by 2x plus 5. Yeah? And then, remember we are multiplying this and that on the top and bottom. When you have this multiply with the top, you have this right here only, because this and that will cancel. Just multiply out, you know. You pretty much have 2x plus 5 right here. And then minus, you pretty much have this right here. So just do this and do that. That's the fast way to do it. Minus parentheses, and here you have 2 parentheses x plus h. Why don't I distribute? I don't know, man. Anyway, this is what we have. Now, let's just clean things up. This right here is 2. See, this is why why don't I distribute? I don't know. Okay. I'm not tired. I can still do this. All right, so here we go. 2x plus 5 and minus, you see this is 2x plus 2h, but it's minus, so because minus 2x minus 2h, yeah? Okay? And then minus 5, okay? And you see 2x, negative 2x cancel, 5 and negative 5 cancel. You have the negative 2h. This h and that h, hey, we can cancel it out again just like over there. So be sure you cancel out this right here, and you cancel out this right here. It's the Adidas sign, you know, 3 cancellations. And you get the negative 2 on the top. Don't forget about that. Now, on the top, we have negative 2 left. On the bottom, we're putting 0 for the h right here. That's about all. So we get parentheses 2x plus 0 and plus 5. And this right here is another 2x plus 5. Of course, if you distribute, it's the same thing at the end. This right here is just 2x plus 5 and 2x plus 5. On all, we get negative 2 over parentheses 2x plus 5 to the second power. Now, you can see that this kind of quotient rule, or if you bring this to the negative 1 power, all that, and also the chain rule, they all work legitimately. All right? Don't be afraid of using the definition of derivative. This is like all the calculus teacher, the things that we want to tell the students. Okay, for the next one, I will have to erase the board. I put on this is too long, so yeah. One over x to the second power, right? Number 94. Again, I'm not so happy because the harder ones are coming, but it's okay, we can survive. Here we go. X is right here, so we are going to write it down. I'll put it down right here, why not? I think it saves some more space. The limit as h approaching 0, and we will just have 1 over parentheses x plus h, square that guy, minus 1 over x squared over h right here. And let's practice what we did over there, okay? So, this right here, you multiply the top and bottom by this and that, namely the least common denominator. Limit as h approaching 0. Well, you put this right here, put this right there. So, we get x squared minus, you put this right here, so it's parentheses x plus h squared, okay? And then the bottom is just h in black times this and that. So I will put down x squared first, parentheses, and we have x plus h squared, like that, okay? Here it's a common mistake. Some students, they just like to cancel this out and then cancel this out. And no, you are forgetting the minus sign between. So don't do that. Don't do that. You can do the difference of two squares. You can factor it out and you can simplify it. That's okay. But I find it easier to follow in the sense that if you just multiply this out and then just reduce. So that's what we will do. So let me just write it down again. This is the limit as h approaching 0. And we have x squared. And this is minus. When you multiply this out, this is just going to give you x squared plus 2xh plus h squared. And we have all this, namely h times x squared times x plus h squared, like all that. Now be really careful, you have to distribute this. So it's actually negative x squared and then negative 2xh and negative h squared. Well. This is x squared, this is negative x squared, so they can be cancelled. On the top, they have the h left, so we can factor out an h. So, let's see, this is the limit as h approaching 0. When we factor out the h, we will have negative 2x minus h to the first power, like this, over this h times x squared times x plus h squared, like that. So good. The moment you cancel the h with the h, so good. Now we can just put a 0 into the rest of the h and we'll be done. And then just simplify if you need to. On the top is negative 2x minus 0. On the bottom, this is x squared times x plus 0 in here, and we square that. Well, on the top is negative 2x. On the bottom, this is x squared. This is also x squared. multiply them, we get x to the fourth power. This and that can be cancelled. Finally, we get the answer -2 over x to the third power. I know what you guys want me to do. I know, I really do. ddx. Hey, this is just x to the -2 power, isn't it? Why don't I just do this front -1 and we get -2 x to the -3, which is the same as that? I know. I know. Yeah. Let's drink some ninja milk and then we will all know. But anyway, use the definition. Use the definition. Okay, now these are the questions that I'm like I didn't put any easy one at the end. I will just show you. Sine x, okay? Here is the input x, sine of x. They are not so bad, it's just a lot to write. Especially once it's like 90-something question, it's just tiring. Anyway, take the limit as h approaching 0. On the top, we have sine, open the parentheses. Here we have x plus h, minus sine of x, like this. This time, be really careful. We are using h as a variable. It's not sinx, okay, not yet. No, we don't do definition with the sinx code. No. Just regular sign, okay? Anyway, this is over h. Here is the deal. Do not multiply the conjugate, do not get whatever. The way we do is, look at this right here. We have the angle sum formula for sine, so we'll do that. With that said, this right here is a limit as h approaching 0. Let me just tell you guys that. Sine of a plus b is sine a cosine b plus sine b cosine a. So here, sine of x plus h, let me write it down. We have sine of x times cosine of h. And for this one, I really have to put a parentheses just to make sure that you guys don't, this is not cosh anymore. Cosh left us already, okay? This is not cosh, it's cosine of h. Cosine of h. And then plus sine of h, okay? Sine of h times cosine of the first, which is x, like this. This is the angle sum formula for sine, the regular sine. And then minus sine of x, like this. All over h, right here. So this is all good. Now, here is the deal. If you take a look, let's see. This one has sine x. This one has the minus sine x as well. This is what we like to do. I'm going to pair this up with this. Okay? And you see the following. When you are talking about h is approaching 0, that means we're in the h world in the limit sense. Okay? That means x, it's like you can just bring to the front. It's not affected by the h. So I would like to write this down for you guys. Perhaps, as I said, it's not hard. It's just a lot to write. Let me write it down. This is the limit as h approaching 0. I'm going to put this and that together, but because both of them have the sign, so I can factor out the sine of x, isn't it? Okay? And right here we have cosine of h. Cosine of h minus 1 after we factor that out. And then we have this over h, of course, because the denominator is over h. And then we can say we plus, I'm just splitting the fraction right now. Here we have sine h cosine x, but let me write down the cosine x right here. Let me just write it down like this. Sine h cosine x. And this is also over h. And we are taking limit for this right here, right? Now, by the limit laws, we can say the limit of the sum is the sum of limits if both limits exist. And also, the limit of the finite product is the finite product of the limits if the limits exist. Okay, so I did say that. And now I'm going to write it down in action for you guys. What I mean by that is I can say the limit of this plus the limit of that. Okay, and again, h approaching 0, the x doesn't matter, so I can put the sine x in the front first. Sine of x right here. And then I'll just focus on taking the limit as h approaching 0, and we're looking at this part, namely cosine of h minus 1 over h. Okay, and then we are going to add, we are taking the limit of this guy. Okay, we're taking the limit of this guy as h approaching 0. But notice, here we have the cosine of x. In the h world, the cosine x doesn't matter, so we can just put that in the front. Right? We're not looking at the, there's no h right here. And then the leftover right here is sine of h over h, like that. All right, now this is the part that has a lot of the controversy. This is the most controversial part. What's the limit of this? What's the limit of that? Especially this one. I call this the limit. You don't do L'Hopital's rule to figure out this limit. You don't do like derivative Taylor series whatever to do this, because we're trying to figure out the derivative sine x. If you want to use L'Hopital's rule, you have to know the derivative sine x in the first place, but we don't. So let me just tell you guys in blue, this limit right here, okay, this limit right here is equal to 1, okay? And this limit right here is equal to 0. One way you can do it is you can just let, for example, h equals 0.00001, and you put it into here and put it into here, and you'll see the number is approaching 1. That's the limit. The limit is 1. Of course, you have to just do even more zeros, and you'll see it's approaching 1. I will be much happier if you do this kind of things right here and say the answer is 1, rather than, hey, L'Hopital's rule and all that stuff. No. And keep in mind, h right here has to be in radians. Why? I will let you guys know later on. I will do another video for it. So this is one way to do it in the, just use a calculator for it quickly. Or you can also do geometry, okay? Or secondly, just put on or, do some geometry, okay? And I do have a video on this right here. And I actually have a t-shirt with the geometric picture, the picture that you need. I will have the link in the description for you guys. The triangles, the sector, and the connection between sine, theta, and tangent theta, all that stuff. And squeeze theorem. Do geometry and squeeze theorem. Okay? So, hopefully you guys are okay with this little explanation, and then I will just continue to figure out my derivatives. Alright? Alright, finally you see that sine of x times 0, this is all gone. 0. 1 times cosine x. Finally, this right here is just cosine x. Ladies and gentlemen, the derivative sine x is cosine x. I know. And then what I'm going to do next is I'll show you guys how to prove the derivative of secant x with the definition. Take a look. And then remember these two limits. I'm not going to give you guys too many explanation anymore because I did that already. Right? Man, that's the part that's like, it's hard to convince people in the it's called circular reasoning, so it's kind of weird. It's yeah. Okay. Number 96, secant x. Okay. Number differentiating. Because I've been using derivative secant x a lot, I don't know if I have been doing it right or not. Maybe I should go back to redo the whole thing if derivative secant x happens to be like, I don't know, tangent to the 5th power, I don't know. We'll see. Anyway, here we go. The here we go. The definition of derivative. We take the limit as h approaching 0, And as you can see, this right here is our input. So we have secant of x plus h, and then minus secant of x all over h, right? Well, we don't really have a nice formula for the angle sum for secant because we usually look at secant as 1 over cosine, so we'll do that. That's the deal. So here, this is the limit as h approaching 0. This right here is 1 over cosine of x plus h minus, this is of course 1 over cosine x. And this is why I didn't do cosine, because we are seeing cosine right here as well. Now, let's do the following. I'm just going to multiply the common denominator, and then I'll tell you guys how to expand this in the meantime too, okay? So multiply the common denominator. So this time I will really just put this down for you. Cosine of x plus h times cosine of x. And here, cosine of x plus h, cosine of x, right? Here we have the limit as h approaching 0. Man, my limit is like getting worse, so the limit as h approaching 0. This times that, of course, we just have the cosine x on the top, and that's why I told you guys earlier for the complex fractions situations. Now, when we have this times that, of course, the cosine x cancel, we have minus. And let me just tell you, for this part right here, we can expand it, and the way to do it is we get cosine of the first angle, which is cosine of x, times cosine of h, cosine of the second angle. And then, if it's a plus, it's weird, right? If this right here is plus, in fact, here it's minus. You have to just remember that, okay? Or you can see the proof for it. You will have a video for that as well. And then secondly, you do sine of the first and the sine of the second. Yeah, so just like this. Okay, so all over, this is the h all the way in the front, and we have this part again, so you just write it down again. Man, it's a lot, I know. Cosine x, cosine h, minus sine x, sine h. So that's that part. And then, of course, we still have the cosine x right here. Right? So hopefully you guys are okay with all this. And maybe I will just might as well change the cosine x in blue. So this is just some of the prep work for that. Now we have to just kind of play around with all this. Yeah. Here is the deal. We are going to split things up, right? And you see, when h is approaching 0, in fact, you still end up with 0 over 0 situation if you just plug in 0 into all the h. And again, just like what we did earlier, we can take out the parts that has nothing to do with the, what's that, the x, with the h and all that stuff, okay? So, how should I split this in a nicer way? Let's see. Okay, man, as I told you, this is just a lot to write. So unfortunately, this has to stay inside of the limit. So it's that, but this can go out. But here is how I will split this, okay? So I'll multiply this in. And check this out. I have the cosine x, so we can factor that out. And then we can pair things up. The hard part is to pair things up the right way. Okay. This is like the limit law to the finest. The limit of the product, the finite amount of product, it's the finite amount of product of the limit. So here's the deal. I'm not going to touch the h. I'm going to split this. In fact, if we have h equal to approaching 0 right here. This is just cosine x. Likewise, this is just going to be 0, so this is good. So this is one part that I can do. So I would like to just take the limit of this part. I will show you. Limit as h approaching 0. And let me just forget about the top for now, okay? And also the h. Just not do that for now. So I would like to look at this 1 over this whole thing here. Okay, this whole thing here. Man, perhaps I should have just written like that, huh? Oh man, let's see if I should do that. I should totally do that. Man, I should totally do that. So mad at myself. H. I am going to just keep this right here. You'll see why. So h cosine of x plus h, and this is cosine of x. So what I will do is, I'm just going to put down this right here first. Okay, so we have 1. We have 1 over, I just want to put this down right here, okay? So this is cosine of x plus h, cosine of x. So that's the first part. I want to just keep it as how it is. And I will have to multiply by the following. The limit as h approaching 0, and we will see the rest. So you see, I am putting down this part right here. So this right here is just the one that with h in the denominator. I put on this 2 in the front already, and that's going to be nice. Now I will have to just pair the top on the top. I just have to pair the top nicely on the top. Here, cosine x minus cosine x, cosine h, right? I will just factor out the cosine x right here. So I will put down cosine x, and this is the cosine x, cosine x. And then, parentheses, this will be a 1 minus cosine h. Good, huh? Yeah, of course it is. Good. Then, this is negative, and this is negative. So I should have done it like this. Negative times negative becomes plus. So we have let me just write it down again, like plus. And you have the sine x right here times sine h. And I think you guys know where I am going. Yeah, that's pretty much the idea, right? So for this part, in fact, as I said, if you can figure out a limit, go ahead and do it. And that's pretty much the limit law. Putting 0 into the h, we will end up 1 over cosine x plus 0 cosine of x. And that's it. Right? This is the first part of the limit. Let's just ignore that for now. And now if you look at this part, of course, let's just do it like this, okay? Save some space, save some time. Just like what we did earlier. The limit as h approaching 0, this is going to give you 0. So this is nothing here. So multiply by 0. And this is going to give you 1. So we end up with just sinx right here. So it's plus sinx. Right? Sin h over h, the limit of that will be 1. So it's just sinx remaining. So it's like this. Now we see that all in all, we just have sinx on the top over, this is of course cosine x, and this is another cosine x, and this is 1 times that, which is, we can pair this up as secant x. Pair them up, we get tangent x. Very nice. Right? Very nice, very nice, very nice. So that's it. The derivative of secant x by the definition. I'm not going to do the derivative tangent by definition because I'll give you guys something better. Anyway, number 97. I will have to erase all this. How are you guys doing? Are you guys still watching? Are you guys still doing good? Let me know. Alright? Now, Number 97, right here. No kidding. I will show you guys for the first time on my channel how to differentiate, how to find the derivative of the inverse sine of x with the definition of derivative. Here we go. This right here is x. And, sorry, that's a bad one. Here we go. By definition, we take the limit as h approaching 0. And now, this right here is the inverse sine. So we have the inverse, right? And this inside is x plus h. And then we minus, of course, the original function, which is the inverse sine of x, like that. You don't put a plus h. And then all over h, right? Here is the hardest part. It's like, how in the world can we simplify the top? Well, we just have to do the angle addition identity, kind of like backwards. I will show you what I mean by that. So let me just make a note right here. This time though, we want to look at the angle difference formula, because whenever we are taking the inverse trig function, it represents an angle, right? So you see, we have the first angle minus the second angle. That's what we have to look at. So in fact, I will have to look at sine of A minus B. These two angles are being subtracted, okay? So that's the key. Well, if you look at this one right here, let me tell you, the identity right here is sine A cosine B, and you minus sine B cosine A. And usually I use the alpha beta, but you know why so serious about like this right here? It's 97 already. Okay, here is the deal. This right here, it's an angle. I will put it to be the inverse sine of x plus h. Hold on, let's do this right here. Let's do it right here. Okay, so we're good with this identity, right? And now you see, this right here is sine of A minus B. So we are just going to take the inverse sine on both sides. Take the inverse sine here, and take the inverse sine right here. So that this and that will cancel out. And don't worry about the domain, because right here, everything is small right here, right? You see, x plus h. And we can, yeah, just negative pi over 2 pi. That's good. Anyway, so this is good. And you will see that right here we can come up with A minus B, and this right here is going to give us inverse sine of sine A cosine B, okay? And then minus sine B cosine A. So I think this is believable. Now, what I'm going to do is I'm going to let A equal to inverse sine. Again, this is meant to be an angle. Right here, inverse sine of x plus h. And of course, B will just be inverse sine of x. And guess what I'm going to do? Of course, I will just put all the a's right here. Yeah, it's too many arrows though. I think I'm not going to draw arrows, otherwise it's too confusing. Right? But here is the trouble. If I put inverse sine of this in here, yes, it's easy, they can just cancel out like this. But for the cosine, it does not cancel out nicely. It's okay though, this is what we can do. Of course, we all know sine square of theta plus cosine square theta is equal to 1. Well, we can move this to the other side, and we can just take the square root. So in other words, cosine theta is equal to square root of 1 minus sine square theta, right? Okay, so you might be wondering, shall we put on the plus minus? Technically we do. But let's just do the positive version first, okay? Anyway, so what I'm going to do is right here. What I'm going to do right here is inverse sine, and this right here is the same as saying sine A, and instead of cosine B, we can look at this as the square root of 1 minus sine square B, right? Just like this. And And again, let's just deal with the positive version first. The way you can do it is that you can just say let x equal to, let x approaching 0 plus, and you can say that's positive, positive. I think that's how you can do it. Or you can just restrict the domain, and then the other one should be symmetrical, this minus minus, and you can be able to factor out all that stuff. I think that should be it. So let's just do this part, and then the other part, you guys do it. Anyway, for the other one, minus sine b, and this is cosine a. We don't like that. We write here as square root of 1 minus sine square a. So this is the version that I'm going to use. Now, let's do this right here. Come back here, and we take the limit as h approaching 0. Let's see what we have right here. Well, I am going to put this right here as the a. Put it in here. So I will just do it one by one for you guys. Okay, put it one here. All right. When we do that, you see sine and inverse will cancel. That means we just have x plus h left right here first. And don't forget, we still have the inverse sine right here. So I will write it down for you guys. We still have the big inverse sine right here in the front. And the first thing that we get right here is x plus h only. So I will just put in x plus h, right? And then we will do this, put it here. This is the b, put it here. And we have the square root. Sine and inverse sine will cancel. So you end up with just x right here and to the second power. So you multiply this by 1 minus x squared, like that. All right? And then continue. You do the same. When you do the same thing, this time, this right here, put it here. It's just x because sine and inverse sine cancel. So it's just x. So that's a minus, by the way. So we have minus just x. And then lastly, we put this in here, and it's pretty much the same speech. We get square root of 1 minus parentheses x plus h squared, like that. Okay? And then this is still all over h. So this is how you play around with the angle difference formula. Right? So check this out. We still have the inverse sine, all that stuff. Right? Are we good? Hopefully. Hopefully right now we're all good. But the next one, I know a lot of you guys will not be so happy about it. But I'm going to do it anyway. Recall the limit as any angle theta. Okay? It can be h, but let me just use any angle theta. Sine theta over theta, this right here is equal to 1. Okay? Here is the deal. If you would like, you can look at this as the limit as theta approaching 0 of sine theta. This being equal to the limit as theta approaching 0 of just theta. You can look at this as the limit of the top over the limit of the bottom, and then multiply limit of that on both sides. We divide the same thing. Okay? Yeah. Lastly, what I'm going to do is, based on this, I will tell you the limit of theta approaching 0. I'm going to take the inverse sine on both sides. And of course, they're continuous, so we can do that. And when we take the inverse sine on both sides, that means the limit as theta approaching 0 of theta, this right here is equal to the limit as theta approaching 0 of inverse sine theta, like this. So what am I doing? Well, look at this one and look at it backwards. What's saying is that, hey, if the inside right here is small, even though you're inside of the inverse sine, you can just forget about it. Check this out. H approaching 0. If you're putting h approaching 0 here, you're putting 0. This is just actually the same as that. So inside is actually approaching 0 as well. So this is legitimate. Let me put this down. This right here is the limit as h approaching 0. You can just drop the inverse sign because again we have the inside is approaching 0. So we can just put this down. X plus h square root of 1 minus x squared. And then this is minus x square root of 1 minus, excuse me, because it's being so many hours, right? And then this is all over h, right? So again, that. And now, seriously, you don't have to do, you should not do L'Hopital's rule on this. You should do geometry for this. And then based on that, you can come with all this. And the picture is like this, okay? This is the picture. So you get this right here. You can get the triangle, and you can get the arc, and you can get a tangent. And you can, do some series theorem to figure it out. 100 limit. I'll promise you I'll do that in my 100 limit video, but not now. So hopefully this is legit, okay? Okay, this is pretty good because this is pretty algebraic. There's no more like inverse sine or regular sine whatsoever. And the good thing is, if this is algebraic, now we can just do the usual thing, right? Do the conjugate. So multiply this right here with the bottom by the conjugate. Namely, we just do x plus h times square root of 1 minus x squared plus x square root of 1 plus x plus h squared. This right here. And also put that one on the bottom right here. Square root of 1 minus x squared plus x square root of 1 plus parentheses x plus h squared, like that. This is life. On the top, this is actually not that bad to multiply it out because it's in the form of a minus b, a plus b. You guys should know that right here, not right by now. So here we go. So we will just have this being squared, namely x plus h being squared, and this thing squared, which is just 1 minus x squared, okay? And then minus this and that, so you pretty much just have x being squared and this right here being squared by itself, which is 1 plus parentheses x plus h squared, like that. And multiply out the bottom, okay? So here we have, no, don't multiply out the bottom, and then just, rewrite the bottom. X plus h and square root of 1 minus x squared plus x square root of 1 plus x plus h squared. Yeah. Man, why is this so... Let's see. Is there any fast way to cancel this guy out? I feel there should be a fast way to cancel the top. Let's see. There, I think is. All right, so just the top, okay, just the top, and just the top, because I don't want to write this guy down again. So if you take this guy and then distribute it, okay? So let's see what we get. We should get just the top, okay, equal sign, just algebra. So x plus h squared, yeah? And then minus x squared times that guy. So x squared times x plus h squared, yeah? Next, we take this guy, distribute. So we have negative x squared. And then minus x squared. Ah, yes. I see this guy now. Okay. We're good. X squared times that guy. So x squared times x plus h squared, like that. Okay. You're kidding me. This is minus? Wait, they don't cancel out nicely. Let's see. Did I make a mistake somewhere? Hopefully not. I am afraid so. I did make a mistake. Okay. 1 minus x squared. This right here have been 1 minus 1 minus, okay, 1 minus. Because remember, it's 1 minus cosine square, and then you take cosine to be the inverse, all that stuff, right? Well, sorry, 1 minus sine square. So that should have been a minus. So this right here should have been a minus. 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 So, you see, this times this is okay. Negative times this guy, it becomes a plus. Thank all my subscribers. Alright, so, okay, hopefully you guys are okay, okay? If you want to watch how to do this, of course you should be able to do all that. Anyway, this and that cancel each other out nicely. And having, we did this, so that's, let me not do anything fancy, let me just multiply this out. This is x squared plus 2xh plus h squared, and then this is minus x squared, so this and that cancel out again. And you see, I can factor the h. So we get 2x plus h, like that. This is what's happened on the top. Alright, so I will just do this one legitimately, okay? This right here is the limit as h approaching 0. This is on the top, alright? So we have h times 2x plus h. Okay? And we have the h all the way in the front. Okay, here we go, x plus h. And then this is the square root of 1 minus x squared. And plus x, 1 square root of 1, man, this minus. And then x plus h squared, like this. Oh my god. Cancel out this h. Oh, cool. And now, of course, we just have to plug in 0 into all the h. So, putting 0 in here, we get 2x plus 0 over, okay, don't panic. This right here is just x plus 0. This right here is square root of 1 minus x squared. And then we add x times square root of 1 minus parentheses x plus 0 square. Yeah? Man, I just want to put up 2x plus 0. Finally, we see on the top it's just 2x. On the bottom, check this out. This right here is x times that. X times the same thing. So you have two of them. Namely, you have 2x times what? Square root of 1 minus x squared. And what happened with the 2x? Bye-bye. Bye-bye. We get 1 over square root of 1 minus x squared. Oh my goodness. How long did this take me? Oh my god, man. So, as I told you, this is why I said, oh man, I don't know if I was ready for this or not, but this is it. This is it, okay? This is hopefully from here to here, you guys are feeling okay. You guys think this is really legit and all that, right? So good. 10 o'clock already. Man. All right. Number 97. Inverse tangent of x was the definition. Alright, so without wasting any time, number 98, dx, inverse tangent of x. Right? So here we go. Take the limit as h approaching 0. And again, this right here is h. So this is x. This right here is going to be the inverse tangent of x plus h, and then minus inverse tangent of x. And then this is all over h. So what do? We do the same thing as what we did earlier. Therefore, right here, we will just do the tangent situation. And again, I want the tangent subtract, the angle subtraction formula. So you look at tangent of a minus b. This right here is equal to, let me just tell you guys what the answer is, okay? This right here is equal to tangent of a plus, okay, this right here should be a plus. Sorry, tangent of a minus, right? Minus tangent of b over 1, here's a plus. Tangent a times tangent b. okay? And you know the deal. What we do is we'll just take the inverse tangent on both sides. Okay, take the inverse tangent on both sides, so they will be gone. And then, of course, for this a, we'll just make it to equal to inverse tangent of x plus h. And then for the b, we'll just make it equal to inverse tangent of x. And it's pretty good because we can just throw in everything and then we will be happy with it. So you will see that right here. This, the top, okay? We still write down the limit as h approaching 0. Okay, put this right here. Right here. Don't forget, we still have the inverse tangent, but you know what we are going to do. Yes, that's later though. Inverse tangent. Tangent A, if A is this, of course, tangent and inverse tangent, they cancel. Namely, we just get x plus h. So on the top here, we get x plus h. I'll put it down in blue, x plus h. And then we have the minus. And of course, we put this right here for that. So we have minus. And this in here, tangent, inverse tangent will cancel. We'll just have minus x over. Same thing. So it's just going to be 1 plus. This right here will give us just x plus h. And lastly, this part will just give us x. So that's the beauty. And I think you guys can see what is going on already, right? And this right here is all over h. This right here is all over h. Yes, I will tell you, the limit as angle theta goes to 0 of tangent theta over theta. This right here will also give you 1, and you can do the same trick like what I showed you earlier. But again, you can do this geometrically. What I want to tell you is that we can just drop the inverse tangent legitimately, right? It's a legitimate work. So here we have the limit as h approaching 0, drop the inverse tangent. But perhaps let me just write the 1 over h like this times the blue part right here. So no more inverse tangent because of this right here, okay? So here we have x plus h. Oh, can just cancel them out. So we just have h right here. So just the blue part right here. So just the h over 1 plus parentheses x plus h times x. Yes, yes, h cancel out. And then you put the 0 in here. So, ladies and gentlemen, in the end, we get 1 over 1 plus. This right here, if you put 0 here, you just get 0, you just get x times the other x, you get x squared. Ah, much better, right? All right. Couple more questions and we'll be done. Of course, you guys can see I haven't eaten anything yet, but yeah. All right, so the last two, we are going to prove the product rule and also the quotient rule. So here we go. By definition, of course, 99 dx, just two random not random generating function. General functions, I have two general functions. I don't know what they are. Anyway, enough talking. Here is the deal. Limit as h approaching 0. This is x. They are the input. So, first part, we have f of x plus h times g of x plus h, right? And then minus f of x times g of x all over h. How in the world can we prove this guy? Well, this is one of the examples that you have to add something and then subtract something to make things work. Let me show you. Of course, we have to know the derivative of f and g, that they do have to exist. Remember, what does it mean to have a derivative? the definition of derivative f prime of x, this right here is the limit as h approaching 0, f of x plus h minus f of x all over h. Like that, yeah? That's the definition of f prime of x. And that's the one we have been doing already. Well, I somehow see that we have the f of x plus h. Let's see if we can do the following to make this work out nicely or not. This right here is the limit as x approaching 0. We have the h right here. This right here, it's kind of similar to the idea when we're doing the derivative of sine. You want to kind of factor out the function part that doesn't have the h. This right here has the f of x. And I also want to have the g to be involved. This is what we are going to do. Perhaps I will have f of x plus h times g of x plus h. Okay? This right now looks pretty symmetric, but what I would like to do is perhaps let me minus f of x plus h. And you see, when you do that, you can be able to factor this out. Well, in the meantime, though, I would like to just multiply by g of x without the h. And the idea is kind of like you can just pick this with that, this with that. And there's also a geometric proof that you can check that out. You can check out Dr. Pan's video for that. But it's been 6 hours and 20-something minutes, so let me just finish this so I can go home. Thank you, okay? Right here, you cannot just subtract something. You also have to add it back. So you add it with f of x plus h times g of x. So this is still equivalent than the original. And then minus f of x, g of x. And you can see that it will be a pretty well-balanced thing to do. Okay, I'm just going to look at the first part. And keep in mind, these guys, they all have the h in the denominator. So look at this guy with the h. And is there anything that we can do? Well, let's see. Both of them have the f of x plus h. I'm going to factor it out, but I cannot take it out to the limit. So I could just stick with it. The limit as h approaching the limit as h approaching 0. Let me just factor this guy out, which is f of x plus h, and that's it. Times the limit. Perhaps I'll put this down in red. I still care about the color. The limit as h approaching 0. I will do this minus that over that. And you see, that will be the g prime if you just change over the f to g from here. That's very nice. So let me put down g of x plus h minus g of x all over h. So if you just ignore this part, just factor this out and then write this down. That's the first part. That's very good. Now we add to do the same limit, but for this one, we can factor out the g of x. And this one right here, you don't have to do this because it's just g of x. You can put it outside of the limit without any worry. And then the leftover is exactly what we have right here. So we multiply by the limit as h approaching 0, and this minus that, so f of x plus h minus f of x all over h. Now, this right here, f has to be continuous, otherwise you cannot have limit, right? So you can just put a 0 right here nicely and just f of x plus 0. It's just f of x actually. Yeah, so it's all good. This right here is just f of x, namely the original function, times this right here is the definition of g prime. So it's just g prime of x. This right here plus g prime of, no, this right here is just g prime. This right here is just g of x. This right here, though, is f prime of x. So we multiply by f prime of x. And guess what? We are done. Ladies and gentlemen, the product Prada rule, okay? The Prada rule. Man, I've been saying Prada rule for the whole video. I feel so bad now. I am wondering if I should do the next one or not, which is the quotient rule. Or should you guys do it? Man. Okay, I will do this. I will do this, okay? Number 100, dx f of x over g of x. You guys do it. This right here will be the bottom one square, and then the bottom one times the derivative of the top one, which is f prime of x, and then minus the top one, which is f of x, times the derivative of the bottom one. This right here is it. Well, the hard part is you have to figure out what to add, what to subtract, and well, just set it up. You guys can do it. Get a common denominator. Just multiply the top and bottom by the common denominator. You end up with like complex fractions. I hope you guys are not so mad because I am not doing that one. I don't know. I feel so bad if I don't do it though. I will do it. 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 Man. Okay. Ignore that. Number 100. Number 100. Right here. We are going to be proving the quotient rule, d dx, f of x, g of x, and dividing. Here we go. Go ahead, write down the limit as h approaching 0. And on the top, here we have f of, you see the input is x and x here. So that means we have f of x plus h over g of x plus h. And then minus the original, namely f of x over g of x, or over h, like that. Well, let's just multiply, let's just fix the, what's that called? The complex fraction situation first. So multiply the top and bottom by the denominator, which is g of x plus h, g of x, and g of x plus h, g of x. So you guys can see this is rather similar to the secant, right? So that's why I've been putting down, why I organize all the worksheets right here. So this time, I'm going to just put that as a limit by itself for the denominator right here, because you guys have seen the secant situation, right? Hopefully. So 1 over this and that, okay, just the blue portion. G of x, like this. 1 over, all right? Now, for the part, for the leftover, this is the limit as h approaching 0. Okay, when you multiply this and that will cancel, so you have this following. F of x plus h times g of x. Yeah, this times that. And then minus f of x. And times this, which is g of x plus h. Like this. Let's see if it's correct. It is correct. And O over h, right? So that's the one that we have. And now perhaps let's take care of this part first. Right here, you can see that if we put 0 into h, what do we get? This will give us 0 here. So we end up with g of x times g of x. Namely, we get 1 over g squared. Namely, the bottom one and you square. Right? So that's that part. And now, for this one, of course, you know what's coming. You are going to take the limit as h approaching 0, and you are going to find something to add and find something to subtract. Well, the same thing to subtract. Okay, so h right here, hopefully it should be enough space. This right here, f of x plus h and g of x, right? And this right here is minus f of x, g of x plus h. Yeah. Now, I want to have the derivative come up to help us out, right? So, remember, you should be able to factor things out and all that. What should we do? Here, we are going to minus. You may want to try to factor out the g of x first. So I want to g of x. In the meantime, if you want to have the derivative form, you want to have f of x plus h minus f of x times g of x. So this way, you can factor out the g of x. Don't just add. Don't forget to, don't just subtract. Don't forget to add it back. So f of x, g of x. This is what you have to do. Now, it's just how we write it down nicely. This right here is 1 over g of x. And we are going to square that. So perhaps I should still keep this in blue. Why not? 1 over g of x square. Okay, so we'll do this. I'll just write it down. I will factor out the g of x. Okay, so this is the parentheses. We factor out the g of x. Let's just write it in red, man. This times that, write it down as g of x. Take the limit of the remaining, which is the limit as h approaching 0, and we have f of x plus h minus f of x all over h, right? Next part, we add why is this adding? Why is this adding? Uh-oh. F of x. Oh, don't worry. I almost had a heart attack. Okay, we're good. Okay, right here, f of x and f of x we can factor out. So we still add, okay? For now, still add. This right here is this right here is f of x. F of x right here, okay? Factor it out. And then we have the limit as h approaching 0. Now, this is g of x minus g of x plus h. Did you see something kind of weird? Yes, okay? This right here is not what we preferred. It's okay, just factor out a negative. So we can get g of x plus h minus g of x. This negative, man, scared me. All right, all in all, let's write down the top right here, right? So we have g of x times this right here is the derivative, right? So derivative of the top. And then this right here, right? It's a minus, right? Plus times minus, so it's a minus. And we have the function f of x. And this part right here is g prime of x. All in all, divided by the bottom function, square. And we are done. This is 100 derivative. But you guys know, I have another one for you guys. This right here, it's the adult power rule. I will try to fit in here. Right? So I will try to fit in here. Ladies and gentlemen, 101. This right here is the adult power rule, meaning that you put a 3 right here. Titration, okay? Titration, okay. Don't worry, what does this mean? I will tell you. This means, okay, if you have the 3 right here, it means x times x times x. But when you have this 3 right here, this means we differentiate x to the x power like that, right? Well, again, we have the base is x. We don't like that. So we are going to look at the derivative. Well, this right here is just e to the natural log of x. Raised to the x power, but we can put that in the front, so it's just x to x right here, like this. And now I will write this down for you. We can differentiate this guy already. Perhaps I will just do it here. I think I should be okay. Why did I write it so big? All right, again, this is e to the natural log of x, and then this is x to the x, right? Okay, here we go. E to the whatever, we just get the same thing, right? E to the that whatever times, well, product rule in action. First one, we have x to the x. That's the first function, and we multiply by the derivative of the second, which is 1 over x. And then we add the second function, which is natural log of x. But do you guys remember what's the derivative of x to the x? Maybe you have to go back to watch the video, huh? I will tell you, it is x to the x, but this is kind of weird, it's like going down like this, times, let me see, it's 1 plus natural log of x, like this. Alright, so no kidding. Now, this right here is what? Well, if you look back, it's just x to the x to the x. So this is x to the x to the x. X to the x to the x. And notice, this guy has x to the x, and this guy also has x to the x. So I'm going to factor that out right here as well. Okay, right here I have 1 over x. Right here I have natural log of x. Perhaps I will distribute this in. So we get plus natural log of x, right? And then plus natural log of x times natural log of x. Ladies and gentlemen, natural log of x squared. Done. Oh my god. Take a look, take a look, take a look. Oh my god. I did 101 derivative. This is 6 hours and 30 minutes. The longest video I have done so far. This is, man, whoa. Whoa. Right, thank you guys so much for watching. And again, download the file. And I have the other file for you guys as well. And of course, I'm going to put on my Marathon medal for the 100 derivatives. So funny, this right here, I PR'd this 4 hours and 22 minutes or so. Yeah, that was when I was much younger. And this right here also PR'd it. This right here, 6 hours and 37 minutes. Oh my god, this is just amazing. Alright, so hopefully you guys all find this video to be helpful, and leave a comment down below and let me know if you guys have any questions. And yeah, give me a like. Thank you guys so much. If you guys enjoyed this video, just give me a like. Thank you. And then again, this video is dedicated to my upper bound students, especially summer 2009 at UC Berkeley campus, right? And Mr. Muniga Lamumba, thank you so much for giving me the chance to become a teacher. And okay, I love my girlfriend Jia, and of course, man, this is so wonderful whenever I finish this. Yeah. Okay, as always, that's it.